This is the Ivankiv district of Ukraine in Eastern Europe. Once part of the mighty Soviet Union, it became a world of ghost towns and hastily abandoned cities. It's one of the most radioactive regions on the planet, with over 2,500 square kilometers deemed uninhabitable. All the result of one of the world's worst engineering failures. In 1986, a routine safety test went devastatingly wrong at the Chernobyl nuclear power plant, and a series of explosions spread clouds of deadly radiation across Europe and beyond. Safety teams rushed to cover the wrecked reactor with a rapidly constructed concrete box. The emergency measure was a temporary fix to contain the danger. But now, 30 years on, the structure around the damaged reactor is at serious risk of failure, threatening the whole of Europe once again. So some of the greatest engineering minds from around the world have come together to design a unique solution. A giant protective container known as the new safe confinement.
It's enormous. It's 108 meters high. If you're British, it would cover St. Paul's Cathedral. If you're American, it covers the Statue of Liberty. If you're Italian, it would cover the Colosseum, and if you're French, it's 3 times the weight of the Eiffel Tower.
This is absolutely a one-of-a-kind structure. It is, in fact, the largest man-made, movable land structure ever built. Weighs 36,000 tons, 257 meters wide, and has a length of 160 meters. It's huge, and no one has ever built anything like this before.
But this is more than just a building. It's a machine designed to facilitate one of the most important ongoing engineering projects in history. Dismantling and cleaning up the destroyed reactor. A task which could take at least 100 years. Designed to withstand a century of bitterly cold Ukrainian winters and scorching summers. A 25,000-ton steel frame supports the giant metal panels which slide over the existing shelter, creating a barrier to stop radioactive dust from escaping. With an uninterrupted floor area of 43,000 square meters, it's big enough to park 8 jumbo jets. Simon Evans is one of the project's overseers.
The role of the new safe confinement is twofold. Firstly, to confine the old reactor so it can ensure you minimize any future releases of radiation. And secondly, to provide the infrastructure to start taking the old structure apart and put into a safe and secure long-term condition, because 96% of the lethal radioactive inventory is still sitting inside that building, so it had to be secured.
Heading up the team of project managers is Mac McNeil.
The structure that was built over the reactor was constructed in 6 months following the actual disaster. Because it was such a radioactive environment, the people who worked on it could not use traditional construction methods. So the structure itself was never a very stable structure.
To be able to dismantle it, the old radioactive building must be entirely covered. But this provides a seemingly impossible engineering challenge on a scale never attempted before.
I think this is one of those projects that people thought could not be done.
So how do you build a self-supporting structure capable of enclosing a volume of 1 million cubic meters? The answer lies with techniques pioneered almost a century ago. Once upon a time, airships were seen as the future of aviation. Mechanical engineer Dan Dickrell is boarding a 21st century blimp in search of an historic key to the seemingly impossible challenge faced at Chernobyl.
Oh, that's a strange sensation of just like lifting up. We're just floating.
When it comes to blimps, size matters. The bigger it is, the more weight it can carry.
Aircraft of this size present a big problem. It's huge. Where do you store it? Where do you build it? And to solve that big problem would require a very innovative solution.
That solution would come from Czech-born airship pioneer Carl Arnstein. To build and house his mighty machines, Arnstein designed an unprecedented new hangar and built it in Akron, Ohio.
Oh, this is it. This is the Akron Air Dock. It's built in 1929. At the time, it was the largest single room on Earth. It's a massive structure. You really don't have a sense of it until you get in here.
The Akron Air Dock is 360 meters long, 100 meters wide, and 65 meters high, with a floor area of 36,000 square meters.
We could fit the Statue of Liberty from side to side and the Empire State Building from end to end with just a little bit sticking out. The reason why that's possible is because the air dock's volume is entirely usable. There are no internal support columns. It makes this a fabulous space.
It's this type of uninterrupted floor space that the engineers at Chernobyl needed to build to contain the reactor. So how did Arnstein achieve it?
The roof is supported by 11 parabolic steel arches. This keeps the floor completely clear of internal columns. This was a massive leap forward in long-span construction.
But the vast size of the hangar presented a serious problem to its structural stability. Steel reacts to changes in temperature. On a small scale, it's hardly noticeable, but in the then world's biggest room, it could have catastrophic consequences.
So when the sun hits the steel structure, it causes it to expand. So Arnstein designed the building to breathe. So this is the leg of one of the arches. Down at the bottom, there's a foot. Now the footer is floating. It's not rigidly connected to the ground. And this is the key innovation that allows the building to expand and contract as it heats and cools. If it was rigidly connected to the ground, the building would essentially rip itself apart.
But that wasn't the only problem caused by a hangar this big.
The rumor was this building was so large it'd create its own weather system. The temperature difference between inside and outside would cause clouds to form and condensation to build up on the steel structures, raining down water on the workers below. To solve this, they installed massive window banks to help equalize the temperature between inside and outside, solving the rain and weather problem. The air dock was a masterpiece of long-span building engineering, and the techniques used in its design and construction, which seemed radical at the time, have become commonplace in constructing a building of its size.
Engineers at Chernobyl must adapt this concept to create something big enough to contain the decaying carcass around the reactor, or they risk another nuclear disaster. Mac McNeil, the lead project manager, has clearance to enter the restricted area near the failed reactor.
Now what you're looking at here is the structure that was built over the reactor very hastily in 1986, after it blew up. Over the last 30 years since the accident, the structure itself has continued to deteriorate You can see a lot of corrosion on it, showing the effects of weathering. And when you think of it, how huge this structure is, the dimensions of this new safe confinement are really spectacular.
Like Arnstein's air dock, the structure of the new safe confinement relies on the power of the arch. The metal framework is made up of a series of 16 arched trusses, standing at over 100 meters high.
Those steel structures, very, very large, they are all bolted together. There's no welding on it. And there are over 600,000 bolts that hold it all together. It's a very, very complex structure, but it has to be because of the size and the overall weight of the arch. When I arrived at the project, my first reaction when I walked under it was how huge this thing is. I mean, how tall, how wide, how long. It was a feeling that got your attention.
And unlike most other construction projects, failure to complete it puts lives at risk.
It's an immensely time-sensitive project because the longer you delayed, the more dangerous it became. Careful around here.
As the head of the project for its financiers, Simon Evans has special security clearance to go even deeper into the old reactor complex, to the heart of the disaster.
It's an enormous facility and very, very complex and very difficult to find your way around.
Security's tight due to the unspent nuclear material still present. The amount of time he can spend here is carefully controlled.
Judgments are that you have around 200 tons of material sitting inside Unit 4, inside the sarcophagus, which is probably about 10 meters to our right, fortunately through lots of walls of thick concrete. This is the heartbeat of the old reactor, the control room. The job of the controllers was to monitor constantly the power in the reactor to make sure the levels were stabilized. And what happened at the time of the accident was they lost control of the reactor. It was certainly the worst ever uncontrolled release of radioactivity in the history of nuclear power, and many, many times worse than Hiroshima. So I find this a very haunting place, to be honest, almost a monument to the importance of doing things safely.
Designing this vital structure is one thing. Building it in a nuclear disaster zone is another.
Working in this environment presented immense challenges for us. The biggest challenge, of course, is radiation.
And in the race to prevent another catastrophe, a seemingly impossible engineering challenge.
Once the top part was built on the ground, the problem was how to lift it.
The new safe confinement in Chernobyl, Ukraine. 10,000 people from 30 countries are working on the design and build of this vital structure, which will protect Europe from leaking radiation. Simon Evans is one of those running the project.
The new safe confinement is the world's largest land-based movable structure and probably constructed in the world's most contaminated place.
Following the 1986 accident, almost 100,000 people were evacuated, and over 2,500 square kilometers around the plant was declared an exclusion zone.
Working in this environment presented immense challenges for us. The first thing we had to do was clean the site, and then we had to make sure that we had all sorts of support facilities in place to enable many thousands of workers to come in over many years. The biggest challenge, of course, is radiation.
Radiation levels vary around the Chernobyl site. Higher doses of radiation for extended periods of time can be fatal. This means that time workers spend in the most radioactive places has to be carefully monitored. Something project manager Cyril Fargier has experienced firsthand.
The difference of radiation level between this place and really nearby the reactor is huge. To give you an idea, here a worker can work the whole year and not reach the limit. Whereas very close to the reactor, working 1 hour, we would reach the yearly limit.
The solution the team came up with was to build the structure away from the reactor. They identified an area of less radioactive land and planned to carry out the main construction here, then move it into position over the reactor. But even here, the time the workers could spend on site was limited. So the decision was taken to construct the enormous roof section at ground level.
The obvious advantage of erecting on the ground is it's much easier in terms of productivity to work close to the ground, whereas working at 100-meter high, it makes a big difference.
But by solving one problem, they created another.
Once the top part was built on the ground, the problem was how to lift it. The heaviest section was around 8,000 tons.
With traditional cranes ruled out on safety grounds, could the groundbreaking pioneers of the past provide a solution? Physicist Dr. Andrew Steele is in Munich, Germany, looking for answers that may help the team in Chernobyl. Almost 50 years ago, the city was preparing to host the 1972 Olympic Games.
Wow, check this out. At the centre of that Olympics was this almost 70,000-seater Olympic stadium, draped in this incredible cable net structure. At the time, a cable net structure this big had never even been proposed, let alone built. And the scale of this thing is just overwhelming.
436 kilometres of steel cables were strung between 58 steel pylons to support a huge canopy composed of 8,000 plexiglass panels.
Although from down here it looks like this roof is just floating over the seats, making it look this effortless is actually a huge engineering challenge. The roof was constructed in sections, and each one of those sections weighs well over 1,000 tons, presenting engineers with a problem. The plan was to construct those individual roof sections down on the field there, and then lift them up into position once they've been completed. And this presents quite literally an enormous challenge if you want to try and do it using a crane. You'd have had to position that crane outside the stadium, and as you can see, that means it would have had to have been absolutely huge. Engineers were going to have to devise a radical solution, which had never been tested at this scale.
Just like the engineers at Chernobyl, the German team needed to find a way to do some heavy lifting without using cranes. In the 1930s, renowned French engineer Eugène Freycinet pioneered the use of hydraulic jacks as part of his methodology to pre-stress concrete to build longer bridges. The team in Munich had a theory that the hydraulic jacks that Freycinet used to apply tension could also be used to lift such an enormous weight.
Engineers decided to use an adapted and relatively untested version of Freycinet's system, known as strand jacking. This was a bold move. Strand jacking had never been used for a project of this size.
With the opening ceremony of the Games looming, in June 1971 the engineers held their breath as the new technique was tried for the first time on this grand scale.
In total, 139 strand jacks were used to lift each of these sections of roof into place. And the way that these jacks works is they've got a couple of different anchors or wedges. One is fixed at the bottom, and that's going to be represented by my right hand here. And the other at the top is mobile. It's attached to a hydraulic ram, and that's going to be my left hand. So if I want to lift that weight down there, the first thing I've got to do is release this anchor at the bottom. Then the hydraulic ram does its stuff. And then when that gets to the top of its stroke, the clamp at the bottom grabs onto it again, which then means the hydraulic ram can move down, grab on, and then repeat. A great advantage of this strand jack system is that you can use them in conjunction with one another. So if you want to lift a heavier weight, you can use loads of them together in tandem to get them to do exactly the motion that you need.
Once completed, the enormous stadium roof covered an area of 74,000 square meters, at the time making it the largest cable net structure in the world.
Sat here, you can really see the genius of the design. It's an absolute engineering marvel. And today, strand jacking has a vital role in the world of heavy lifting. It's a remarkably simple solution, but it's an incredibly effective one.
But can the Chernobyl engineers, racing to prevent another radiation leak, use this technique to solve their giant problem? How to raise the roof?
So the optimized solution that we chose was to design and fabricate special lifting towers, and on top of each tower we install a platform with jacks.
With the strand jacks positioned on top of the lifting towers, cables with a high tensile strength are run down to the roof section. When powered, the jacks pull these cables, lifting the 8,000-ton section of roof.
Each jack had a capacity of a maximum 900 tons, and we had over 40 strand jacks activated simultaneously to make this operation.
A computer-controlled system ensures this crucial maneuver is pinpoint accurate.
All the 10 lifting towers lift the structure in an evenly way, okay, very smoothly. So we had the tolerance and accuracy every point within a few centimeters. So, but to get this accuracy over 260 meters, that's a very high precision.
The next sections of the arch were attached to the roof using giant hinges, and the whole thing was jacked up even higher. Once it had topped out at 108 meters, it was time to repeat the whole process for the second part of the arch.
There is excitement when you start an operation like this. You're even more excited at the end of the day when the mass has reached its altitude and is secured and everybody is safe and we have completed on time. It's totally a unique engineering work.
The framework was now taking shape, but the team still had some serious challenges ahead.
It was the most complex and precise engineering ever envisaged over such a site.
And they were battling against the clock to prevent another disaster.
Timing was critical to get the reactor covered. The concern was that it could collapse.
In the Ukraine, a race against time for the international team who've united to build the incredible new safe confinement to contain the damaged leaking reactor at the Chernobyl nuclear power plant. Costing over €2 billion, the giant arch is large enough to completely contain London's 96-metre-high Big Ben. Mac McNeil heads up the project management team.
Timing was critical to get the arch in place, get the reactor covered. It is not a stable structure, and ultimately the concern was that it could collapse. Of course, that could release another cloud of radiation, which no one wanted.
However, before the mighty arch can be moved over the reactor, the structure has to be clad. But finding a suitable material isn't easy.
We need a material that will last 100 years because the arch has a mission now, which is to do the deconstruction of the shelter. And that process could conceivably take a very, very long time.
They need something capable of containing some of the most lethal materials on Earth, and that would last a century of extreme conditions in this radioactive wasteland. For as long as man has been building, He's wanted to protect the results of his labours from the elements. The Egyptians applied a liquid membrane to the pyramids to try to protect them from the waters of the Nile. The other method is to add a protective layer on top of the structure, such as straw, tiles, or cladding. But all of these have a limited lifespan. However, something more enduring was on the horizon.
This is incredible. What a breathtaking view. The New York City skyline. It's so exciting to be up here in the city that I live in.
Professor Eric Lima is discovering how a case of one-upmanship led to a major innovation that could help engineers in Chernobyl.
In the 1920s and the 1930s, the city was gripped by skyscraper fever. Architects and engineers were outdoing themselves to try to build the highest buildings. I like to think they had drafting tables and they were drawing and they were saying, let's go higher. Why? So that they could be the highest in the United States and the highest in the entire world.
At the southern end of Manhattan, 40 Wall Street was under construction and looked set to become the world's tallest building. But just over 8 kilometers away in Midtown, automobile tycoon Walter Chrysler had other ideas.
Okay, what you see is the really cool, iconic building is the Chrysler Building. It was designed by William Van Allen, right there. The most iconic building, in my opinion, in New York City. Such a cool building.
But it wasn't on course to be crowned the world's tallest.
But Van Allen, he had a plan. Secretly, he obtained a license to bring a long, tall point, a needle, that he was going to put on the top of his building. But the problem was, it's going to be exposed to all the elements. Rain, wind, sleet. How do you make sure it doesn't rust?
It's the same problem facing the engineers in Chernobyl. For his solution, Van Allen turned to a new German innovation. In 1911, metallurgists Philipp Monartz and Wilhelm Borchers built on recent advances in non-corrosive steel used in cutlery to create an architectural version of steel almost entirely resistant to the elements.
So this scrubby is made of steel. The main component of steel is iron. Now, when the iron is exposed to oxygen in the air and moisture, there's a chemical reaction. That reaction makes iron oxide, otherwise known as rust. Monartz and Borchers discovered that by adding other elements, most importantly chromium, to this mixture, they were able to make an alloy that was much more resistant to corrosion than anything that had come before. Today, we call that mixture stainless steel. To prove just how resilient this material is, I've set up a little experiment here. Here's our steels, regular steel, stainless steel. We're going to replicate what decades of corrosion could do in just a few minutes.
The two versions of steel are soaked in vinegar for 2 minutes, and then to activate the simulation, they'll be placed in hydrogen peroxide.
All right, here we go. We're going to move them over. First, we're going to move the regular steel into the hydrogen peroxide. Then we're taking the stainless steel and bringing it into the hydrogen peroxide. And almost immediately, you can see the rust forming and you see streams of it coming off. You can see the reaction taking place. That's rust, that's iron oxide. It looks totally gross, actually. And on this side, crystal clear stainless steel.
The chromium added to the alloy reacts with the oxygen to form a film a few atoms thick. This protects the material from other oxygen atoms contained in rainwater, which would react with the iron, causing rust.
Monartz and Borchers discovered a metal that would go on to revolutionize the world.
Days before the grand opening, William Van Allen's spire, clad in this cutting-edge material, was erected on top of the skyscraper in just 90 minutes, crowning the Chrysler Building as the tallest in the world, pipping 40 Wall Street to the post.
When the Chrysler Building was being constructed, stainless steel as a material was almost completely untested architecturally. And yet, when you look at it, over 80 years now, it's completely withstood the trials of time. Today, that metal influences almost every part of our daily lives.
In Chernobyl, engineers are putting stainless steel to an even greater test. Protecting the world from another nuclear disaster.
So there are a little more than 87,000 square meters of stainless steel covering the exterior of the arch. That's why you see the shiny appearance of the arch when you look at it. The interior is also covered in stainless steel. We don't want this cladding material to deteriorate.
Sandwiched between two giant spans of stainless steel are multiple layers of other materials, all carefully chosen to help contain the radiation. But getting the equivalent of 12 football pitches of gleaming stainless steel onto the outside of a 108-meter high arch isn't easy.
The material actually was put in place using workers that we called alpinists because they had to be in full, almost mountaineering gear, suspended from the roof of the arch to put all these in place. They're absolutely mind-blowing.
With the crucial protective cladding in place, it's time for the most difficult part of the operation. But how do you move such a vast building in some of the most radioactive conditions on Earth? It's a huge moment for all involved, including Simon Evans.
This is the most unique part in many respects because along this beam, 36,000 tons of steel was slid over a destroyed nuclear reactor. It's hard to imagine it now, but it was the most complex and precise engineering ever envisaged over such a site.
If the old reactor building is disturbed, it would have catastrophic consequences. So it's essential this runs smoothly. Project manager Cyril Fargier is on hand for the operation.
So you can see here the skidding beams. On these skidding beams, we had a Teflon pass. On top of it, we had what we call the skidding shoes with a stainless steel interface, which allow a very small friction coefficient when we were pushing the arch.
But even with Teflon-coated skidding beams, it still takes a lot of force to move 36,000 tons. That force comes from a technology already used to lift the structure, hydraulic jacks.
So we had the jacks which are pushing horizontally, and also there was jacks perpendicular to the beam in order to monitor and to compensate any slight deflection of the beam.
In late 2016, the operation begins.
Watching the process was surreal in many respects because you could look at it from a very micro level and you could see the pistons moving very slowly and the whole arch seemed to object to moving because the noise it was making was like 10,000 fingernails on a blackboard. Yet when you looked up and saw this enormous structure over, did you really sort of start to feel the immense engineering that was in these pistons pushing?
Basically, we were doing up to approximately 100 meters per day, but sometimes less. It's not a race. The objective was to do it in safety and in quality, and not to create any stress in this huge structure.
As the structure approaches the old reactor building, it is the tensest moment of the operation. Carefully designed cutouts ensure the end wall clears all the protrusions from the reactor roof.
So when the arch reaches final position, we were able to complete the enclosure.
After 7 days of painstaking skidding, the structure's in its final resting place.
Sliding the arch was nerve-wracking, but when it had reached its final position, I'll confess I did feel a little bit emotional about it because it was such an epic moment.
It's extremely exciting because I believe right now in the world there is no such a project. So amazing in terms of size, dimension, challenge.
But the team still face the biggest challenge yet in their quest to put right what once went wrong.
This is where all of the action occurs, taking apart a structure so that you don't cause a collapse, which would then release contamination.
Just how do you dismantle the most radioactive building in the world? Ukraine, the heart of what was once the USSR. It's taken 8 years of construction, with 1,200 workers on site every day, to create the new safe confinement, the largest land-based mobile metal structure on Earth. Capable of withstanding temperatures as low as -43 degrees Celsius and wind speeds of around 300 kilometers per hour, this almost impenetrable barrier stands between the failing nuclear reactor and the Earth's atmosphere. But it not only encloses the reactor, it's also designed to dismantle it.
Inside the arch, there are 2 bridge cranes that go forward and backward across the whole length of the arch.
The 2 96-meter-long bridge cranes move along the east-west axis. Hanging from them are 3 tool platforms, which can move along the north-south axis. This enables tools to be remotely maneuvered to anywhere in and around the old reactor.
What we have here is the robotic mobile tool platform, and from this platform will be hung about 10 different tools that can cut, grind. There's some vacuuming tools, cut grabbing tools. So this is really the workhorse of the whole new safe confinement, because this is where all of the action occurs. In a sense, it's taking apart a structure very carefully so that you don't cause a collapse or further damage to it. You want to take it apart very methodically, and all of that needs to be well planned, so it will take many, many years to do that.
As the dismantling process may take over 100 years, the surrounding structure and the machinery need to be able to withstand not only the high levels of radiation, but any corrosion caused by humidity. The area most at risk is the giant metal framework. Unlike the stainless steel cladding that surrounds it, this is made from carbon steel, which, if left untreated, could be prone to rust.
So on a typical steel building, you would probably have to do a lot of maintenance of the steel to maintain its corrosion resistance. And here in this structure, we just don't have the opportunity to do that. You have the radiation conditions, you have this huge volume, so it was very important that the structure itself be able to resist corrosion for the design life of the arch.
But what can they use to protect this essential structure from decay? It's an issue that's been faced in the past.
Yeah, great day to be on the water.
Engineer Dan Dickrell is in Maryland in the United States, discovering how the US Navy countered their own corrosion problem, to see if it holds any clues for the Chernobyl team.
So this is actually a very surreal scene, these jutted remnants of wooden ships sticking up the Potomac River here in Mallows Bay, home of the largest shipwreck fleet in the Western Hemisphere, sometimes called the Ghost Fleet.
When the US entered World War I, hundreds of wooden vessels were specially built to help the Americans get across the Atlantic.
The problem with the war being over, there was no use for them. So ultimately, they were just left to slowly decay in the environment.
It was a huge waste of resources. So, at the end of World War II, they weren't going to make the same mistake again. And a plan was formed to put almost 1,000 steel ships into storage.
How do we keep these ships preserved for future use? How do you keep the steel from corroding and oxidizing in a saltwater environment? Well, that required a technological solution. Luckily, one man had the answer.
American chemistry professor Walter A. Patrick patented a method to process silicon, a chemical element found in sand, to mass-produce silica gel, a substance which had a quality needed by the US Navy. Which may also help the team in Chernobyl.
This is the USS Iowa, an excellent example of a battleship from the Second World War. She entered service in 1943, saw active combat duty, but was decommissioned shortly thereafter and placed into reserve. If you look at her, she's in amazing condition, very well preserved. How is that possible? For a 75-year-old, she looks great. Well, it's all down to this stuff right here, silica gel.
Each silica particle is covered in pores, which water molecules are attracted to. Once all these spaces are taken, it can't hold any more water. But there is a solution. When silica is heated, the water is driven off, and it can start trapping water again.
Silica gel plays a huge part in everyday life, keeping food, electronics, and clothing free from moisture.
It's also a crucial component of the system used to preserve this ship. Desiccant dehumidifiers draw moist air over a rotating wheel of silica. This attracts the moisture, allowing dry air to be circulated. When the wheel turns, the waterlogged silica is exposed to a heating element. The water detaches and is drained away, and the dry silica can start the process again. By installing dehumidifiers on the mothballed ships, the Navy engineers were able to lower the humidity and prevent them from rusting.
Oh, this is the old communication center. All this stuff is very sensitive to moisture. Still in actually really good shape.
Thanks to silica, the reserve fleet was kept in great condition and ready for speedy reactivation. In Chernobyl, engineers have taken the same method and implemented it on a grand scale.
The ductwork you see brings in air that comes in from the outside and is forced through the dehumidifiers, which then reduce the moisture content of the air. The key component, the actual drying material, is silicon.
This monumental system recirculates almost 500,000 cubic meters of air every hour to maintain 40% humidity, a condition under which carbon steel does not corrode.
If this system weren't here and operating, then the structure of the arch could be subject to corrosion over a period of years.
The dehumidifiers are the final historic piece of the jigsaw that makes this modern engineering dream a reality. The new safe confinement has been safely constructed on one of the most contaminated pieces of land on the planet.
Well, I feel very inspired, slightly humble and very proud.
You know, it takes a lot of human ingenuity, a lot of good engineering design, a lot of very thoughtful planning, and always, always attention to safety.
The unprecedented and ambitious project stands as testament to the Herculean effort of a truly international team.
It's an immense example of what the international community can do when they all pull together with a shared objective.
I think being a part of that legacy really gives me a feeling that I have contributed something to the people of Ukraine, to the people of Europe, and perhaps to the people of the world as well.
By building on the work of the inspirational pioneers of the past, upscaling and breaking new ground themselves, the engineers have succeeded in making the impossible possible. The North Sea, separating Britain from Northern Europe. Its waters stretch over 750,000 square kilometers. It's a famously hostile environment. Storms bring 6-meter waves whipped up by 110-kilometer-an-hour winds. Challenging conditions for one of the world's busiest shipping areas, whose traffic must also navigate shifting sandbanks. It seems an impossible place to build. But these awe-inspiring natural forces are irresistible to a group of intrepid engineers. Around 20 kilometers off the British coast, an ambitious project is taking these waters on.
It's a hostile environment, and it presents a major challenge for any kind of engineering construction.
But this is an unprecedented engineering marvel. The London Array.
London Array is the world's largest offshore wind farm.
175 towering turbines capture the energy of the wind and convert it into record-breaking levels of electricity.
On an average year, the wind farm produces over 2 billion units of electricity. That's enough to power 500,000 UK houses.
Captain Nick Coville is part of the team making this immense wind farm a reality.
To give you some idea of how epic this is, the area of London Array is a greater surface area than the city of Manchester.
It's an army of giant spinning windmills that cover more than 100 square kilometres.
Right now we're about 87 metres above sea level. You can see the rotor behind us, so each blade length is 58 metres. Standing out on these machines, it really does make you feel what a unique place to be.
London Array's turbines reach almost 150 metres above sea level. Each blade is almost as long as a jumbo jet's wingspan. Embedded in 650-ton foundations, they feed into 200 kilometres of cabling. 2 offshore substations send all this power to the mainland, where it provides enough electricity for 500,000 homes. But engineering on this scale at sea has never been done before. And this unpredictable environment throws up huge construction challenges.
It was a really ambitious plan to build a wind farm here. It's quite tidal restricted. There's a lot of change in tidal height, so there's very high currents, a lot of moving sandbanks.
The brutal marine environment also takes its toll on any technology.
If a piece of equipment fails, we're working to a very, very small weather window. We can't nip to the local hardware store and get another one.
But above all, in the middle of one of Europe's most extreme locations, these turbines must somehow generate year-round power on an unparalleled scale.
We need to generate electricity 24 hours a day, 7 days a week in this remote offshore location. It's an unforgiving and unpredictable environment.
Out here, the challenges are enormous. But the team must do whatever they can to keep the blades turning. So how is it even possible to harness the power of the wind? Dr. Andrew Steele is on the windswept coastline of Scotland, searching for the relics of an idea that sparked an engineering revolution.
This 18th century salt mill is one of Scotland's best preserved windmills. The principle behind a windmill is simple. By taking a linear motion from the wind, spinning those giant sails and creating a rotary motion, you can then use axles and gears to take that motion to wherever you want to use the energy.
This windmill would have once had large sails. Its rotation was used to pump seawater onto the land for the production of salt. It was a technology that hadn't changed for thousands of years. Simple horizontal axle windmills were used to power irrigation pumps in China as early as 200 BC. The first evidence of a wind-powered machine is a wind wheel organ, designed by ancient Greek Hero of Alexandria.
Oh yeah!
And in Persia, vertical axle windmills with reed sails were commonplace, something that is thought to have been spotted by European crusaders.
Ooh.
In the 11th century, Middle Eastern farmers were already using sail-driven mills to drive mechanisms to grind corn for food. And it wasn't long before crusaders and merchants had brought these ideas back to Europe, and the Europeans had adopted them to build windmills like this one.
But around the turn of the 19th century, one man felt wind power had a lot more to give. Just like today's engineers at the London Array offshore wind farm, Scottish engineer James Blythe was determined to generate electricity from wind power. And in 1887, in his back garden on the coast, he built the world's first wind turbine to power the lights in his cottage. But it's said his neighbours weren't impressed. They considered electricity the work of the devil. Andrew Steele, however, has managed to track down a place that welcomed Blythe's innovation.
Although Blythe's design didn't prove popular with the locals, he did manage to find a new home for it here at Sunnyside Hospital, or as it was known then, Montrose Lunatic Asylum.
With electricity supplies in this era notoriously unreliable, Blythe proposed adding his new wind turbine invention.
Today, all that's left is this building, but to explain the engineering principles behind it, I've got this. As you can see, this thing is made up of a load of half cylinders, and that means they catch the wind like a cup, and as they spin around and around, get faster and faster. And the axle goes through this big wheel, through this belt to this smaller wheel, then it's connected in to an old washing machine motor. Now, a motor and a generator are basically reversible. In a motor, you obviously put in electricity and get out motion. You can just wire that up backwards and put in motion and get out electricity, and that's exactly what happens here. Out of this cable.
Andrew is using a slot car game to demonstrate the transformation from kinetic wind energy to electricity. But today's light winds call for a bit of improvisation.
Okay, see what this thing can do. Well, I think that's a pretty clear victory for Red, and we made it work.
Blythe attached his generator to an accumulator, an early form of rechargeable battery, and his invention was an instant hit.
Blythe's design was so successful that it actually stood here and powered Montrose Lunatic Asylum for 30 years before it was demolished.
London Array's 175 turbines are over 10 times taller than Montrose turbine, reaching 147 metres from base to blade tip. While Blythe used horizontally rotating cylinders, the Array uses 58-metre-long vertical blades to squeeze as much electricity as possible out of the North Sea's powerful winds. The vital job of ensuring the turbines remain operational falls to a specialist team of engineers. When they're called into action, they must first make the over 20-kilometre journey out to sea.
We have 175 offshore power generation plants, so we need to send people offshore to keep all of the turbines running all of the time. It's quite an extreme job. The guys have to be tough and they have to be capable of meeting physical demands.
They have extraordinary access to the hidden inner workings of these incredible structures. Today, Senior Operations Technician Ronnie Hill must carry out essential maintenance to the turbine known as Echo 19.
Hi Rob, it's Echo 19. Can I take control please under AWP?
Yep, that's all copy 013, and there's no restrictions.
Before work can begin, he must access a control panel on the lower platform to bring the blades to a standstill.
So you can already hear it's starting to slow down. There we go.
Each giant tower contains an elevator to assist team members like Senior Engineer Ed Hall with at least some of the 70-metre ascent.
So that's the lift part of the journey over. It's quite a challenge just getting access to the point of work. Yeah, now we've got to climb up.
The heart of the turbine is known as the nacelle. A 10-metre-long stainless steel enclosure, the nacelle houses the machinery needed to produce electricity from the blades.
Not many people get to see this part. It's very unique. This is the nacelle of a turbine where all the action happens. So this is where the power is getting generated and transmitted. We have the rotor at the front with the blades. So that rotational energy is transferred through a gearbox. And behind me we have the generator where the electrical energy is produced.
The energy from the turbine's blades can produce electricity in as little as 12 km/h winds. The turbine blades rotate an input shaft at up to 13 revolutions per minute. A gearbox makes the output shaft spin more than 100 times faster. A generator then converts this increased kinetic energy to electricity.
So the task we're given today is lubricating the main bearing. Those are like bearings in your car. Over time they wear out. The more we lubricate it, the longer it keeps going, the more power we can produce. This is what we're here to do at the end of the day. There we go. These machines, they don't stop. Summer, winter, Christmas Day. They've still got to run, we still need electricity.
Constructing just one of these mega structures is a huge engineering challenge. So how do you make 175 of them when your building site is the North Sea?
Not only do you have challenging seabed conditions, you also have different depths. It's a challenge from start to finish.
These 175 turbines make up the world's largest offshore wind farm, the London Array. For Head of Operations Graham Dawes, it's a perfect location for a bumper harvest.
Around the coast of the UK, we have more wind energy than pretty much the whole of the rest of Europe.
Spanning an area of 100 square kilometres. These 150-metre high turbines are kept operational 24 hours a day, 7 days a week, to produce 2.5 billion units of electricity a year. Each of these massive marvels is made up of mammoth components.
The tower itself in two parts weigh around about 200 tonnes each. 3 blades per turbine. Each one of those blades is around about 25 or 30 tonnes each. And then the cell, the part that goes onto the top of the wind turbine, they can be up to 300 tonnes.
But constructing this army of giants in the unforgiving North Sea is the biggest battle of all.
The weather conditions can be very variable. We can have mist and fog as we have today. You can have nice flat counties, and you can also have storm force conditions rolling in without warning. Constructing the wind farm is a challenge.
It's a significant operation to install one of these turbines. Fast flowing tides, the nature of the seabed is extremely variable. So even in one location, we could get a difference of up to 10 meters. The change is very, very extreme in a very, very small area. It's a challenge from start to finish.
So how is it possible to create a stable structure when your building site is underwater?
Left a bit, right a bit.
17th century English lighthouse engineers discovered that wooden structures were a flop.
Ew!
The Irish came up with the screw pile lighthouse. With long screws inserted into the seabed, this offered a solution, but only in the shallows. The Scots ventured further offshore, building one of the first masonry lighthouses at Bell Rock.
Hootsmon!
However, with the outcrop only above water for 2 hours a day, it took 4 years to complete.
About time!
Arromanches in northern France is the site of an historic marine construction breakthrough. Today, Dr. Rhys Morgan is joining a team of divers who are tracking down an engineering relic.
This coastline is the site of some of the most incredible Second World War engineering, and we're on the hunt for perhaps its most ingenious component.
Lurking in the depths since the 1940s lies a game-changing innovation that influenced countless future engineers, like the team at London Array.
Oh, does that look like it? Yep, there's a structure there, is that right?
Yep, I think you can definitely see it coming up on the edge of the screen. Ready, and go!
During 1944, the D-Day landings gave the Allies a toehold in Europe. But this was just the beginning. To free the Nazi-occupied continent, they faced the problem of landing enormous quantities of equipment on the Normandy coast.
To take on the mighty German army, hundreds of thousands of troops and their vehicles had to be landed on the beaches behind me.
British engineer Sir Bruce Gordon White had to carry out an astonishing plan. Construct 2 fully functioning harbours in a matter of 2 days. And it would have been impossible without a brilliantly simple piece of engineering called a spud leg.
There it is.
Ah, look.
There's the edge of it. It's definitely got an upright. 1 spud leg.
Fantastic! We've actually found one of the original spud legs on the seabed. It's incredible to think that these now discarded pieces of metal were once vital for ending a terrible war.
The spud legs were the vital component that made Sir Bruce Gordon White's famous Mulberry Harbours possible.
These big concrete blocks behind me were floating pontoons on which a steel roadway led out from the beach to the deeper water, so that the ships could unload their tanks and they could drive right onto the beach. Creating a floating pier is one thing, but anchoring it securely in tidal waters and making sure it's stable enough to carry a tank is a whole other ballgame.
The engineers building the London Array need a solid, stable platform to work from. Gordon White needed similar in order to safely land trucks and tanks.
This simple platform illustrates the problem. In normal conditions, it's fine, but if you've got rough seas, then actually it's very unstable. It will swing violently from side to side, potentially damaging the roadway. So it needs to be anchored. Now the problem is, if you have a fixed anchor, as the tide comes up, the platform itself starts to sink.
Surviving the seas required a special solution. And the answer was movable mechanical legs, which allow the pontoon to go up and down.
These 4 legs help the platform remain stable. They weren't driven into the ground, but rather the ends just sat on the surface of the seabed. Now, the weight of the platform connected by these chains is forcing the legs down, and that acts as an anchor. Not only did the legs prevent the platform moving from side to side, but the tension in the cable could also be adjusted to rise and lower with the height of the tide. Just a brilliant idea.
Thanks to inventive engineering, over 2 million men were landed alongside 500,000 vehicles and 4 million tons of goods. The remains of this remarkable invention may be hidden in these French waters, but it has inspired engineers around the world. The spuds were an ingenious solution for Normandy's shores. But how could movable legs be used to construct a wind farm in the middle of the North Sea? The answer lies in an extraordinary vessel.
This is MPI Discovery. 20,000 tons of hydraulic muscle. At the time of London Array, she was the fastest, had the highest lift, had the fastest turnover rate in the world. This ship is able to lift 6,000 tons, which is the equivalent of 86 Intercity 125 locomotives, 6,800 Fiat 500 cars. These ships were pretty much designed with the London Array project in mind.
Discovery can construct the seemingly impossible thanks to a mind-blowing metamorphosis. From ship to offshore building platform in a matter of hours. Experiencing this jack-up ship in action is a unique experience for Captain Nick Coven.
When you're slightly pitching and rolling as you do at sea, to the legs taking the seabed, everything stops and you become a platform. For a mariner, it's an extreme situation if you find you're putting your own vessel aground. However, this is our job.
Like a supersized version of Bruce Gordon White's solution for the Normandy invasion, MPI Discovery uses giant legs to act like a table sitting on the seabed.
Discovery itself has 6 legs. From the bottom of the keel to the top of the leg is about 75 metres. You can see here they're probably about 4 or 5 inches of steel. Also, you can see here by the barnacles that this part of the leg will be very much underwater, driven into the seabed.
The British Army's spud legs were winched, but Discovery's rely on hydraulics. Each leg is jacked up by 8 huge cylinders, with every vertical movement secured by a massive pinning system.
Each one of these cylinders is capable of lifting 500 tons. You have 2 cylinders here that go to a single yoke, and you have a pin that withdraws. The yoke comes down, the pin goes in, and then the leg is either raised or lowered, depending on whether we're recovering the legs or driving them into the seabed. The system here is capable of lifting 24,000 tons of ship, all the components for 8 turbines, completely clear of the water.
This ship can stand solid in depths of up to 40 meters. But in order to assemble the component parts of the wind turbines, it needs even more muscle.
So here we have a 1,000-ton crane, a unique piece of equipment. There was no other crane available that was so compact, that had such a lifting capacity.
This mega machine can assemble the superstructure of an entire turbine. First, a hydraulic hammer is used to drive a giant 5.7 meter diameter steel tube, which can weigh up to 650 tons to depths of up to 68 meters below the seabed. This holds in place a yellow transition piece, which can be up to 28 meters high. Next, the main tower is added, topped off by the nacelle and hub. 3 58-meter long blades complete each 480-ton structure. Amazingly, 8 turbines can be transported and built on a single voyage.
So the reason that we have such a vast deck space is basically because of the size of the wind turbine components. The nacelles are the size of 2 or 3 double-decker buses. We have 8 of them at the centre of the ship. The blades run across the vessel, going actually over the side by about 30 metres. My first day as captain, the London Array team told me that I must not roll the ship more than a certain amount, otherwise the blades would go in the water and get damaged. And I was thinking to myself, what have I let myself in for here, really?
The London Array relies on the North Sea winds, but nature has a habit of biting back.
We encounter all sorts of weather, from rough seas, high winds, to extreme hailstones and rain.
If these impossible wind turbines are to survive, engineers must find a way to protect them from the very elements they're trying to harness. Quietly revolving to produce immense power. 20 kilometres off the coast of Britain, 175 gentle giants make up a wind farm of epic proportions.
The circumference of a turbine with the blades on is about the same as the London Eye. It's an absolutely awesome project.
But the wind turbines themselves are just the start of this impossible engineering feat. Each turbine forms part of a 200-kilometre network, converging at one of the 2 gigantic offshore substations. These perform a vital role, boosting the voltage produced by the turbines before sending it to the mainland.
So there behind me you can see one of the 2 London Array substations. These structures are critical to the operation of the London Array. All of the energy that's produced passes through one of these 2 substations. They perform a critical function in increasing the voltage from 33,000 volts to 150,000 volts in order to minimise the losses as the energy transitions on its long journey back ashore.
4 huge cables, over 50 kilometres long, are needed to complete this final leg. Each weighing 4,500 tonnes, they're floated towards the Kent coastline and then sunk to the seabed as they finally converge at Cleve Hill onshore substation.
So this place is really interesting. This is where the 630 megawatts of energy produced by the London Array offshore wind farm out there comes ashore on the North Kent coast. The 4 large cables comes through this field and then joins the UK national grid. You can see the pylons extending off in both directions, and this is where we break into it and add our energy to the backbone of the UK electrical supply and distribution network.
Harnessing the elements to create colossal amounts of electricity is an engineering triumph. But there is such a thing as too much wind. The turbines must be able to stand up to a battering from the brutal storms that afflict this dangerous sea.
Our turbines are 12 miles out at sea. We encounter all sorts of weather, from rough seas, to high winds, to extreme hailstones and rain. The turbines can operate quite safely into wind speeds of up to 50 miles an hour. Beyond 50 miles an hour, the turbine needs to be able to protect itself. One of the challenges that the team who designed the turbines had to overcome was finding ways of being able to allow the turbine to protect itself in extreme weather conditions.
So when the extreme weather hits and wind speeds reach the 80-kilometre-an-hour mark, exposed to the elements, how can these vital mega machines survive? Deep in the Danish countryside is an extraordinary structure that Dr. Tuffe Coachman is scaling. And it might hold the key for the London Array.
It is super impressive. This is really exciting. So for the first time ever, I'm going to start up a turbine. So we released it. Right. Then we're going to turn this on. Look at this. It is still up and running. 40 years after. That's unbelievable. I'm 54 meters off the ground right now. And this 2 megawatt design machine has been operating at this very spot for the passing 40 years. That is by far the longest operational time for any wind turbines in the world. And it has a beautiful view.
In 1978, the giant Svindkraft dwarfed all wind turbines before it. To date, its 27-meter-long blades have completed over 120 million revolutions.
It has produced more than 21 million kilowatt hours. To put that into perspective, that kind of production could power up the entire New York City for more than 3 years.
Its scale is astounding, but how it came about is even more incredible. In the 1970s, the world was gripped by an oil crisis. Denmark was no exception. So a group of radical teachers set up a collective, promoting the country's strong winds as a viable energy alternative. On a farmland plot called Svind, they mobilized hundreds of volunteers, building the seemingly impossible with little financial backing.
What I really love about the Twin-Craft turbine is how many second-hand components you can find here in the nacelle. For example, this main drive shaft over here is from an oil tanker, and this gearbox right here is from a copper mine, and the generator is from a paper factory from Sweden.
But, as at the London Array, the sheer scale of the Svindkraft posed enormous challenges. No manufacturer could be found to construct the 27-meter blades, so the collective took matters into their own hands, breaking the mold of blade design.
They're not made of metal, which was popular at the time, but they're made of glass fibers, which give them a lot of flexibility.
Designed to withstand a hurricane, the massive blades can flex 1.5 meters in either direction. But this rotor has another ingenious way of dealing with wind.
Arguably, the most important innovation of Twin-Craft is actually being able to pitch the blades.
To maximize efficiency, pitching orientates Svindkraft's blades at various angles to the wind.
I have this little version of Twin-Craft with me here. We have the blades pitched to the ultimate efficiency position already. We will give it some steady wind and then get a reading out of that. So right now, my little twin is producing about 0.15 volts.
But if the angle of the blades is turned to a less efficient position,
we are actually adjusting them approximately half the way. We can already see that it's rotating a lot slower. And the reading I have is actually around 0.7.
But pitching can have an even more dramatic effect.
I'm changing their angle so that they will face the wind almost entirely, eliminating the lift that is created by the turbine blades. And when I take my hands off, no more rotation.
The Svindkraft collective had engineered a truly adaptable turbine that could safely survive a storm and maximize energy in a steady breeze. From these humble beginnings, it wouldn't be long before the commercial world took notice. In the 1980s, around 700 Danish-built turbines were ordered for a site in California that would eventually become the world-famous Tehachapi Pass wind farm and spell the start of the Californian wind rush. At 58 meters long, the blades of London Array's turbines are twice the size of Svindkraft's. But incredibly, they're able to maneuver in the same way. Engineer Ed Hall has special access to take a closer look.
The blades on these wind turbines can pitch. The advantage of pitching the blades is to allow a variable speed production. A greater amount of energy can be captured at lower wind speeds. And in terms of also providing a safety function for stopping as well, it's important that the pitch system can pitch the blades out quickly if the turbine needs to stop.
These intelligent blades are even able to angle to the optimum position automatically, thanks to a clever onboard computer which operates a system of hydraulics.
One of the special things we can do is change the pitch angle right now for working on different areas of the blade. So as you can see, the pitch angle moves relatively quickly. All the blades can move independently, continually changing the angle to optimize itself for the wind conditions present.
The blades themselves are molded from a single piece of fiberglass, making them lightweight but super strong. The circular base of each one is bolted onto one of 3 connection points on the nose of the turbine. A 3-meter-high fiberglass dome known as the hub.
So right now we're in the hub of the turbine. So this is right at the front of the machine, between the blades, 90 meters above sea level. Here we can see the 3 blades bolted on here, here, and here. The benefit of having a single piece design is so there's no jointed connections, which have historically in the industry been the weakest point of blades in their design. So to have it molded in a single piece is really key in the technology development. Inside the blade is actually hollow. You can get inside and move along it and walk inside it. It's that large. This is the evolution of a number of years, up to 30 years development of wind turbine blade design.
London Array is so efficient, its annual contribution to the reduction of CO2 emissions is the equivalent to taking around 290,000 cars off the road. But with the pressure on to produce even more power, how can engineers here take it to the max?
Wind is a free fuel, so it's all about getting the most out of it that you possibly can.
It's impossible engineering in the extreme. So can they rise to the challenge? In 2013, the vast London Array rose out of the North Sea, delivering more energy in a single month than any offshore farm before it.
Nothing on this scale had been done before, so it was a real step change in terms of the real size and capacity and the challenges faced.
Spread over 100 square kilometres, the 175 turbines are arranged in a giant grid to capture the North Sea's prevailing southwesterly winds. Each turbine is computer controlled, with all data sent back to the control room on the mainland.
This is the London Array Operations Control Room. This is the nerve centre for controlling all operations that happen on a daily basis. We're looking at the performance for the previous month. The table of information there in the centre of the screen is giving an indication that we would have hoped to produce about 192,000 megawatt hours. We actually produced 208,000, so we produced more than budget, which is again a very nice feeling, and is generally as a result of the wind blowing rather more than expected. The future is going to be much larger wind farms, much further offshore with much larger turbines. So the future is looking very rosy indeed for offshore wind.
But to stay at the cutting edge of this new technology, the challenge for this ambitious team is to maximise the array's potential.
It's all about coming up with new ways to really optimise the efficiency. So when the wind is blowing, we're able to capture all the energy that we possibly can.
But how is it possible to boost the power of the array? To unlock the secret, its engineers, in their quest for kilovolts, must turn to an unlikely source. Britain's Silverstone is home to a high-octane sport where performance is everything.
It's a beautiful day for racing.
But engineer Dr. Aisling O'Kane is finding out that despite the huge horsepower on display at this classic meet,
it's amazing to be close to this speed and this power.
a secret to slashing times is surprisingly small. and was invented over 40 years ago.
This is the Formula 5000 Gurney Eagle. This is a prime example of some really innovative engineering. The motor is incredibly impressive, but it's also the shape of the car that contribute to how fast this thing can fly around this circuit.
For racing cars, shape wasn't always a priority. By the 60s, sleeker bodies increased straight-line speed, and the invention of the airfoil improved cornering. This upside-down wing creating downforce and grip. But then, the Eagle landed and raced ahead of its rivals.
Take a look at this car. It's incredible to see how the aerodynamics allow this car to just fly around this track with ease. There it goes. 55,000 Gurney Eagle left us in its dust.
What sets the Gurney Eagle ahead of its field is a minute piece of engineering genius.
It's fun!
Created by American racing legend and engineer Dan Gurney. In 1971, his All-American team was struggling with performance, lacking the edge to be an Indy 500 contender, until Gurney bolted on an addition to its wing.
Here it is, the Gurney flap. Small piece of engineering, massive difference to downforce. Dan Gurney had happened upon, in his garage, a significant feat that even the aerospace engineers hadn't come across yet.
It might not look impressive, but this tiny detailing has a big effect on turbulent air known as vortices formed at the airfoil's trailing edge.
On a normal airfoil, there are two vortices that come out and meet in the middle. With the addition of the Gurney flap, that changes these vortices in a very significant way.
The flap's additional height changes the point at which the streams of air separated by the wing reconnect, increasing the vertical deflection of air, creating greater downforce. To see just how effective it is, Aisling is first putting a standard airfoil through its paces.
We're going to use this model airfoil, put it on the scales, and see how downforce is created. So you can see there it's 0 grams. We're going to take our trusty instrument to create the air force. The air coming through is creating low pressure underneath, high pressure above, and therefore creating downforce. The readings here hovering between 10 and 15 grams.
But when a flap is added, the difference is remarkable.
So look, you can see the grams are approximately twice what they were without the Gurney flap. It's doubled the downforce. The power of the Gurney flap has massive impact, even on this model.
Gurney's newly improved Eagle claimed 7 pole positions and won an impressive 4 IndyCar races.
At places like this, where there's such competition in race car driving, they're pushing vehicles to the limits and pushing the physics involved in it. The impact that it had to engineering is absolutely amazing.
But how can London Array's engineers adapt this minuscule concept to future-proof the largest offshore wind farm on the planet? Each of the 175 turbines are supersized, but Ed Hall and his team are making small adjustments to evolve its blade technology.
Increasing aerodynamic efficiency on these blades, we use a number of aerodynamic enhancements. It's about reducing drag and getting as much energy out of the wind as possible.
Inspired by the Gurney flap, a serrated strip is fitted along the edge near to the centre of the blade, helping to produce more lift, which makes them spin faster. Serrated tails are also fitted to the fastest moving part of the blade to reduce drag caused by turbulence.
The add-ons add a percent or two onto the energy that we can capture from the wind. Doesn't sound like a lot, but when you add it up over 175 turbines here, operating 24/7, then it does add up.
In this offshore world of mammoth engineering, it's the smallest details that can make the biggest difference.
Using different elements of engineering to really maximise the amount of energy that's captured from the wind is really exciting. Wind is a free fuel, so it's all about getting the most out of it that you possibly can.
These final modifications to the blades are the finishing touches to one of the world's most advanced maritime feats of engineering. Through design and engineering, London Array is changing the face of energy production.
Being part of the largest offshore wind farm in the world, it's a privilege. It's unbelievable. Great sense of achievement.
This groundbreaking wind farm is paving the way for the future.
Every time I come offshore and look at these amazing structures, I'm always impressed in the same way as I was the first time I saw them. The sheer scale and beauty of something that's generating so much power from an infinitely renewable resource.
By drawing from the pioneers of the past and pushing the boundaries of innovation, the engineers behind London Array are succeeding in making the impossible possible.
It is phenomenal. And thinking back as the maths and science kid at the back of the class, I would have given my right arm for this opportunity, I have to say.
Manhattan Island, New York. 26 square miles of some of the most valuable land in the world. Demand for space is high. But surrounded by water, spreading out is not an option. The only way is up, if you can find somewhere to build.
It's extremely difficult to get a large plot in Manhattan because everything's been spoken for over 100 years. So basically, when you do find a large plot, chances are it's because it's a railroad yard.
These vast expanses may be free of building, but they're strewn with tracks. Any construction seems impossible. But now, on the west side of Manhattan, ambitious engineers are taking that challenge on. Hudson Yards, America's largest real estate development, is being built directly on top of a working rail yard.
The engineering on this site is incredible. But it's not one individual piece, right? There's a whole series of these things added together. I mean, not just you're designing a building, but then you're designing a complete specialty underlying structure to be able to support that. And unless you look out at the Western rail yards and see the trains there, you have no idea what's underneath us.
Changing the skyline is not just one new skyscraper, but 6, with more towers to come. Jeff Butler is the senior project manager on site.
Each of these buildings is an amazing building. We have over 1 million square feet of retail space. We have almost 5 million square feet of residential space, 10 million square feet of commercial space. It has no comparison in scale. There have been some great developments in New York, but I'm very excited that this is the biggest and best.
Built almost entirely over a giant base platform above a working rail yard, Hudson Yards covers a 28-acre site on the west side of Manhattan. Multiple megastructures are being constructed simultaneously, including the 3rd tallest tower in New York, an arts venue that can appear from nowhere, and a brand new park constructed from scratch.
When Hudson Yards is complete, we'll have 125,000 people here working, living, and playing every day. It's an entire city within a city.
But this ambitious $25 billion project poses immense engineering challenges. How do you build New York's highest external observation deck?
We're about 1,050 feet up. So the combination of engineering and understanding the construction sequence was really complicated.
In a city blighted by power cuts, how do engineers keep Hudson Yards running 24/7?
The firms at Hudson Yards absolutely cannot live with the threat of power outages.
But it's the specific site that poses the biggest problem of all. Jay Cross has masterminded the project from the start.
The actual plot of land is highly valuable because there's just only so much of it. There's rivers all around us. But the West Side Yards was always like the hole in the donut because it was all train tracks.
Spanning 7 city blocks, the West Side Yard was used solely as railway sidings for Penn Station. The audacious plan to construct on top of the tracks, while the trains continue to run.
The engineering challenges were significant, not least of which we have to build over an operating rail yard. That logistically is a challenge unlike any other.
How is it possible to build directly over 30 active train tracks? Part of the answer is to be found 715 miles west of Manhattan. Architect Marty Sandberg is in Chicago, discovering how ambitious engineering helped a newspaper company overcome the confines of this cramped city.
In the 1920s, the Chicago Daily News was one of the best-selling papers in the city, and as a result, they had outgrown their current building and were on the search for a new home. Unfortunately, there was just simply no open land left at that time.
The problem was the same as that faced by the Hudson Yards team, the railways. At the beginning of the 20th century, Chicago was the busiest railroad hub in North America, with more lines radiating out than any other city.
The downside to being such a rail hub was, at the time, Chicago was literally choked off by rail yards on every side of the city. You had yards like this on the north side, the west side, the south side. There was really just physically nowhere else to grow, even as the city wanted to.
But the Daily News decided to attempt an extraordinary engineering feat.
So this is the Daily News building. I'm a sucker for a gorgeous old limestone building, and this is a great example of it.
In a city hemmed in by train lines, how did they manage to find the space to build this? It was down to a new law known as air rights. The Daily News had bought from the rail company the right to build in the air above their tracks.
Essentially, the trains were only so high and they weren't really getting any higher, so they recognized that they were wasting a whole lot of space up above, and they saw this as a pile of money just waiting to be had.
Pouncing on this opportunity were architects John A. Holabird and John Wellborn Root Jr. Incredibly, they built the 26-story tower block directly on top of active tracks.
So when we look at the building now, you can't tell there's still a mess of train lines running back and forth underneath. Everyone coming in there day to day would never have any idea that they're still sitting over an active rail line.
This is what the engineers at Hudson Yards need to achieve. So how was it done here?
This is our sandbox of Chicago right here. All we need are areas where we can sink a couple of key foundations in between the trains. So we start by seeking out a couple of areas where we can sink these deep foundations down, trying to aim for the bedrock if possible. From there, we go ahead, drill our foundations down nice and steady, and all of a sudden ground level is no longer down here. We're up here 20 feet above.
The building could then be constructed on top of this platform, with the weight being supported directly by the pillars.
And we've just turned a train yard into some of the most valuable and useful land in Chicago. The city's happy, the railroad is happy, the person walking down the street is no longer standing next to a train. It really turned into a great solution for everybody.
Holabird and Root's incredible achievement led to an explosion in air rights. Railroad plots once shunned by developers were now worth millions.
It's a complicated solution that really is a simple idea. You get a couple of genius minds figuring out how to actually make it happen, and now a good part of Chicago is built exactly this way.
In New York City, the Hudson Yard development is thought to be the biggest air rights deal ever. $1 billion paid for fresh air above Manhattan's Western Rail Yard. Tracks covering 28 acres must somehow be straddled to build multiple skyscrapers. A supersized steel sculpture, an assortment of public buildings, and 14 acres of open space. And throughout construction, the trains below have to keep running.
We work basically at the mercy of rail traffic. So think of it as they own the basement and you own everything above the basement. And so of the 30 tracks, we were only allowed to close 4 tracks at a time for the purposes of construction. What we had to then do is weave all of the foundations for the buildings between the tracks to go down to rock.
The foundations for this massive 28-acre site draw on techniques used in Chicago over 90 years ago. The first step is to drill 45-meter deep holes into the bedrock, which is up to 75 meters below the ground. Then insert the supersized steel and concrete support columns known as caissons. 300 caissons support the entire development. Carefully located between train tracks, they take the weight of the steel frames for the tower blocks, as well as the giant 40,000 square meter base platform that surrounds the buildings. This concrete and steel platform creates a new ground level above the tracks.
The platform doesn't support anything except the open space where we're standing right now. So where the platform is underneath the buildings go right down between the tracks. They go all the way to rock. So the trick is in the foundations. That's where all the load transfer goes. The platform just fills in the space in between.
But while boxing in the active rail yard creates acres of new usable space, the incoming trains below are now confined underground, creating a fresh challenge.
When the trains come and bring commuters in, they drop them off in Penn Station and they park here for the day. We've engines running and just all the train activity is creating heat below us. It can get up to 150 degrees Fahrenheit, which is very hot.
The team had to find a way to keep the rail yards cool, so they came up with an awesome solution.
Below you right now are about 5 jet engines. They're about 40 feet long, maybe 5 feet diameter. They're actually lined up right like this, and they exhaust through that shaft.
Twin ventilation shafts at the plaza connect to 15 giant fans, sandwiched within the thickest section of the platform. Principal engineer Eli Gottlieb has special access to the restricted area inside the platform itself.
It's pretty exciting to be in here and to be able to see this. This is something that nobody ever gets to see and to experience when we go down here, right? To actually see down into here and be within the structure and to see the fan systems that are operating on either side.
The fans are installed at the plaza directly above the trains.
Well, welcome to the central fan plant underneath the yards. This is one of 3 fan plants that are actually down here. These fans are really part of the lungs of the facility that actually allow it to breathe. The criteria in the rail yard is we weren't able to allow the temperature in the rail yard to rise more than 10 degrees above the ambient temperature. So if it's 70 degrees outside, it can't be more than 80 degrees inside the rail yard. So these fans allow us to exhaust any of the heat generated by the trains out and pull in new, fresh, cooler air to maintain a tenable climate for everybody who's down there. These fans can fully exhaust the entire facility in 7 minutes of all the air that's here and completely replenish it.
But for Hudson Yards engineers, more impossible problems could jeopardize the project.
You're just running out of space to actually be able to install anything.
And the challenges are set to rise to an even higher level.
They came up with this protrusion, so we weren't quite sure how to construct it.
For many, every buildable inch of Manhattan Island is spoken for. But the trailblazing Hudson Yards project is challenging this belief. America's largest private real estate development is attempting the impossible. Building directly on top of 30 train tracks to create a 28-acre New York neighborhood from scratch.
Most of the buildings are over an active rail yard, so there's some amazing engineering going on just to build our buildings. And when the development's done at Hudson Yards, it'll be very amazing.
To work on a project like this that has so many pieces to it, each one of which is incredibly challenging and amazing, and then to fit them all together, I mean, the project is just astounding.
Multiple skyscrapers will provide 18 million square feet of commercial and residential space, including a school, an over 200-room hotel, and a retractable art centre, all perched on 300 caissons squeezed between a network of train tracks. But in one critical section, this isn't possible, where the tracks converge in an area called the throat. Engineer Eli Gottlieb is one of the team charged with solving the problem.
As you look through this, you're actually looking east down into the 4-track narrows where the trains come into the Hudson Yards. From here, you can actually see that there's going through a lot of switching, and this switching allows them to fan out from the 4 tracks that they come in at to the 30 storage tracks. And you can imagine that if the tracks are spaced far apart, there's space in between them to be able to build a caisson and a column coming up. But as the tracks converge in together, you can just imagine that you're just running out of space in between the two of them to actually be able to install anything.
This area of the development is earmarked to have a tower block and a shopping mall built on top of it. If engineers can't span the 45-metre wide gap and support the buildings above, Hudson Yards will be left with a massive hole in its plans.
This is really a key problem on the site. All of that underneath us really narrows down the number of possibilities of what we can do to be able to support everything above.
Can the solution to this impossible challenge be found in the past? When it came to spanning, many of history's bridges appeared to have cracked the problem. Until you added a load. In 1297, Scotland's Stirling Bridge stood proud, until the battling English and Scots met in the middle. In 1444 in romantic Venice, the Rialto Bridge was the perfect spot to view a wedding, until a swelling crowd put a dampener on the big day. To span their gaps, bridge engineers needed something stronger.
Almost there now. Wow, it's a long way down.
Physicist Andrew Steele is getting a close-up look at the Worcester Railway Bridge.
Wow.
That's it?
What a beautiful view.
Can a game-changing innovation from the British railway boom be the missing piece of the puzzle for the team at Hudson Yards?
In the early 20th century, the UK railway system was undergoing a huge period of expansion. Not only were there more tracks, but there were also more trains, and these trains were much faster. And as they were getting faster, they were also getting heavier, and that meant that bridges on the railway network were being put under increasingly large strains.
Like the team in New York, engineers needed to find something strong and reliable to bridge the gap. James Warren was a merchant with no formal training in engineering. In 1848, he registered a patent that would revolutionize bridge design, the Warren Truss.
This is Warren's design. This repeating pattern entirely made of equilateral triangles, so triangles which is the same length along each side. Now, triangles like that have the advantage that they're incredibly strong. The railway track is above my head right now, and what that means is that as a train passes over the top of us, then its weight is distributed through all these different struts, and every single one of them can share that load. That means that all these individual beams are either in tension, so being pulled, or compression, so being squashed. There are trains rumbling over my head right now. This bridge is still very much in use.
Previously, many bridge engineers had used vertical struts. So how much stronger was the triangle?
So they can both take one brick.
2 model bridges are being tested to breaking point.
So in this simple design, all that load is mainly going through, well, honestly, just this vertical strut here. Whereas on the Warren Truss over here, all of that load with this triangular pattern of struts is being spread throughout the whole bridge. We're going to go for brick number 3. Right, brick number 4. A bit nervous about this one, to be honest. The question is, can it take a 5th? But a 6th, I think this is going to be it. Surely this time. Oh! Total structural failure there. You can see there's lollipop sticks everywhere. But the Warren Truss, it's still supporting that load pretty strongly because no individual lollipop stick is taking that much weight, and so incredibly, it can hold all of that mass. The Warren Truss really was an incredible engineering innovation. And of course, it's not just bridges. Wherever a weight needs to be borne and spread over a structure, you'll see these equilateral triangles holding them up. This incredibly time-tested design.
Engineers are supersizing this 170-year-old creation to support part of a 7-story shopping mall and skyscraper. Where piled foundations are impossible, sandwiched between the retail space above and the converging rail tracks below, lie a series of 4-meter-high Warren trusses.
So we're inside the platform underneath retail, over all the switching of Long Island Railroad. We're standing basically within a bridge structure, right, where we're standing on the bottom of the bridge and there's the top of the bridge above us, and these Warren trusses are those main elements of the bridge that are spanning across.
In total, 14 giant trusses are used to span the crucial 45-meter gap.
By being able to use this truss structure and build a nice stiff bridge deck, that's actually really efficient for being able to support the buildings above. It's a pretty incredible piece of engineering when you think about what these trusses need to do and how much they need to be able to carry.
The historic Warren Truss design plays a vital part in this huge modern development.
There's a lot of engineering that we stand on the shoulders of those who came before us. And so there's a lot of incredible engineering that comes out of, especially the 19th century, that has a thread that travels through what we're doing to today.
The tower supported by the truss is not only the highest on the project, but once it's complete, will be the second tallest office building in New York. Engineer Jay Cross has special access to its most incredible feature. On the 100th floor, a 10-minute ride away in the temporary lift.
The view changes so dramatically as you get higher and higher. It's amazing.
And it's the view from the top that inspired another phenomenal piece of engineering.
At first we designed the building without an observation deck, and we realized how high we're going to be. So we challenged the architects to say, come up with the idea of an observation deck. We, of course, thought they were going to come up with something that was inside the tower. Instead, they came up with this protrusion, which was pretty darn dramatic.
This is the highest man-made outdoor observation area in the Western Hemisphere. Almost a third of a kilometre up, it offers a brand new bird's eye view of the city below. But constructing a platform in the air calls for more impossible engineering.
At first, we weren't quite sure how to construct it. We thought maybe it would be like a bridge where you just kind of build piece and you inch your way out from the building. But the problem was we felt that we would have to have a lot of supporting scaffolding to do that. So our steel fabricator came up with the idea of making 14 pieces that would come up pre-assembled, and you would just bolt them on as you go out.
Built out from the building section by giant section, some weighing up to 45 tons. The result is a 700 square meter sky deck. But the final piece of the puzzle will be an immense triangle made of reinforced glass.
We felt that in addition to walking towards the peak, which I think will be exciting enough, we thought, why not make it a little bit more exciting and create a glass floor? Right now, there's nothing there. There's no glass. We're just looking down 1,000 feet. And it's pretty exciting, don't you think? It felt a lot more comfortable when the orange netting was across here. Now that it's down to like 2 or 3 wires, there's no need to get too close.
4 550-kilogram triangular sections of glass will complete the sky deck. 2 1/4 inches thick, it will allow visitors to take in the vertigo-inducing views from this mind-blowing vantage point.
I'll walk on it, I'm sure. I'll be goaded onto it, but I'll be nervous about it.
But this impossible project is attempting more audacious engineering, throwing up further challenges.
We're moving the equivalent of about 600 elephants stacked up on top of each other, wearing 8 roller skates.
Can their innovative construction be taken to another level?
It's very difficult to figure out that solution from an engineering standpoint.
New York's biggest ever impossible engineering challenge. Hudson Yards is a 1.6 million square meter real estate project constructed over a fully functioning rail yard. Perched on a specially constructed base platform above the tracks, this is a multi-tower mini-city. Multiple skyscrapers, a supersized mall, 14 acres of public land all coming to life simultaneously. But perhaps the most inventive engineering on site is a unique arts venue known as the Shed. Engineer Eli Gottlieb is overseeing its build.
The Shed is built up of 2 parts. One is what we've always thought of as the fixed building, which is the building that we're standing in right now. And then it has the sleeve that slides over the fixed building so that when it's not in use, it's actually retracted. But then when they have larger events and they need the space, they'll be able to roll the Shed out to enclose the plaza and turn it into this larger venue that we can see here in front of us. There's really no other places like this.
The team are using a special inflated plastic to keep the shell as lightweight as possible, so the power required to move it is kept to a minimum. The drive system on the roof generates just 180 horsepower.
So we're up on the roof of the fixed building of the Shed. You can see here are the main teeth from the drive mechanism that the actual Shed motors will then roll against and drive the assembly back and forth. We're moving the equivalent of about 600 elephants stacked up on top of each other, in this case wearing 8 roller skates.
The roller skates are in fact 8 pairs of 2-meter-high wheels running along heavy-duty rails. And in 2016, this retractable building was put through its paces for the first time.
To see the Shed move was actually fantastic, but it was also really surprising because it is so quiet that in fact a whole number of people actually kind of missed it because it happened and they sort of didn't hear it or realize that it was going on in that moment, and all of a sudden, hey, wait a second, it was back there, now it's here. How did that happen so smoothly, so effortlessly?
The vast 28-acre Hudson Yards is a series of separate construction projects. With many being built over an active rail yard, the challenges are undoubtedly huge. But although the corner is clear of the main tracks, it poses an equally taxing problem. A massive tower has to be perched directly on top of a $2.4 billion Manhattan transport hub.
55 Hudson Yards is an office building, and it's just outside of the platform area that's over the rail yards. It is, however, over a large subway station.
Just 3 years old, the 34th Street Hudson Yards station is one of the city's newest. With 1.5 million commuters coming into Manhattan every day, it's a key selling point for the development. But it presented the engineers with a weighty challenge.
We've limited opportunities to put weight on the subway station and limited footprint to put weight outside the subway station. And so we're looking for ways of putting as big a building as we can with the limited options we have at the foundation.
Lack of space for new foundations meant 40% of the tower block's weight had to be carried by the foundations of the subway station itself. Overloading was a real danger. The tower had to shed some weight without shrinking in size.
Our building is 51 stories of office space, and that's a lot of building to put on limited foundations. So the engineers needed to find solutions to lighten up the building as much as possible. It may sound easy to make a building light, but it's very difficult to figure out that solution from an engineering standpoint.
It seems impossible, but can engineers of the past shed any light on lightweight materials?
Beautiful.
Kipter Peak State Park in Virginia. Engineer Megan Hart is off to discover how a material used to solve a wartime problem could help the team in New York.
During World War I and World War II, there was a massive manufacturing effort, and that took a lot of raw materials. The main one was steel.
Steel production went into overdrive to supply the military. This led to a shortage, but the US Navy needed to build a fleet of supply ships. So how did they manage it?
These ships didn't need to be made out of steel. They would never see active combat. What they needed was another material.
These are the Inspired Solution, made out of an innovative version of a surprising material.
These are concrete boats, can you believe that? And they actually float. Not only do they float, but they carried supplies during the war efforts. You think concrete, you think massive and heavy and super dense, but density makes it very difficult to be buoyant. This concrete is different.
The man behind it is Stephen J. Haid. He was working in the Kansas City building trade in the early 1900s when he had a eureka moment. He noticed that shale stones left too close to the kiln during the firing process would bloat up when they overheated. The heat caused air bubbles to form in a honeycomb-like structure inside the stones, making them lightweight. So Haid added them to cement and water to create his revolutionary new concrete, an invention that could help out Hudson Yards engineers.
So Stephen J. Haid, instead of using traditional aggregate, which is heavy, it's just rock, he used an expanded shale. And that expanded shale is much less dense. This lightweight aggregate would not only float, but also weigh a whole lot less.
During World War II, 24 of these 100-meter-long concrete ships were made, the unexpected solution to the Navy's problem at sea.
Wow, that's amazing. You can see that the shell is still intact. Stephen J. Haid came up with a perfect material to build these boats.
In New York, engineers draw on Hade's discovery to solve a skyscraper's serious weight issue. 55 Hudson Yards is a whopping 240 meters high, and its sizable mass bears down on a major transport hub. To avoid overloading, the team had to save weight on the inside.
We're on the 47th floor of 55 Hudson Yards, and lightweight concrete helped us achieve a light building to go over the limited foundation we had around the subway station. So if we look above and below us, slab above, slab below, every floor on this building is made out of lightweight concrete. And we saved about 20 to 30% in weight overall. It made a huge difference. If we save 20% in weight, we can make the building 20% higher. So 20% more buildings, quite a bit.
The concrete floors are also lightweight because they're only 9 inches thick. But spanning the tower's vast open plan areas is problematic for such a thin floor. The team's solution is a pioneering technique known as post-tensioning.
Historically, post-tension technology in New York City specifically hasn't been used regularly, and this is the first building where it was used regularly in the slabs. So over our head we can see white painted areas that say PT zone. That's where we're using post-tension concrete. Simply put, it's a high-strength cable that's pulled through the concrete that helps limit deflection.
A network of steel cables are threaded through liquid concrete. Hydraulic jacks apply massive tension to pull them taut. Anchored in place, the compressive force of the concrete is increased from 7,000 to 8,500 psi, reducing deflection, allowing a thinner, lighter slab.
With our high-strength lightweight concrete and using the post-tension slabs, it makes for the most robust system we can for a thin slab. It was a perfect solution to lighten up the building and allow us to build as much as we could over the subway station.
But the engineers of this brand new neighborhood face another hurdle. They must defy New York's notoriously unpredictable weather.
When we lose power here in Manhattan, it's eerie. We're used to seeing the city alive.
Keeping Hudson Yards up and running calls for impossible engineering. The New York skyline is set to change forever. Thanks to the city's biggest ever development. Hudson Yards is built on a giant base platform over an active rail yard, but incredibly, all of this is just the first half of the $25 billion project.
What you're looking at here is the Western Yards. That's what we call phase 2. So we'll do another 5.7 million square feet of development over here.
With phase 1 almost complete, a second, even bigger steel and concrete platform will be built above the tracks, on the other side of the 11th Avenue Viaduct. 8 colossal buildings will be created. This city within a city will double in size.
We have 6 giant buildings around us, and we have a lot more coming in very short order. We're bringing more office space to New York City than there is in downtown San Diego.
To be a success, Manhattan's newest business quarter must stay online 365 days a year. But maintaining a steady power supply in New York is a huge challenge. Hurricane Sandy caused the latest and most devastating in a long history of power cuts affecting the city.
When we lose power here in Manhattan, it's eerie, right? It's a large city. We're used to seeing it lit up, and we're used to seeing the city alive 24 hours a day.
Frank Norcross is in charge of Hudson Yards' energy supply team. He needs to find a way to protect the new development from power cuts.
The customers that will call Hudson Yards home can absolutely not afford to lose power at any moment. They run 24 hours a day, 7 days a week, and they need reliable provision of electrical service. It's a huge problem when we lose power because vital systems, the things that we maintain to keep safety and security in a large city, are under threat when we lose power.
In the face of a hurricane, how do you keep the power supply running? The team need to turn to the past to stop history repeating itself. When it comes to creating power, factories have led the way. First, elbow grease drove machines, until the Industrial Revolution brought steam. Now, one enormous engine could power everything. But with their eggs in one basket, if anything went awry, everything ground to a halt. Physicist Andrew Steele is at the Anson Engine Museum in the north of England, in search of an historic innovation that would blow steam power away. It was Niklaus Otto, a German salesman with a passion for engineering, who came up with an invention that transformed the 19th century.
This is what Otto came up with. It's called an atmospheric gas engine, and it's got a number of advantages over the steam engines that existed at the time. Firstly, you don't need a huge supply of water to run this thing. Secondly, you don't need a team of people. You can do it with just one person. And thirdly, you can have a load of these small engines scattered around the factory to operate individual machines, rather than having one massive steam engine to drive all the equipment in the whole place.
More powerful for its size than its steam engine counterparts.
So, that's a bit of physical labour. It's not like starting your car.
This new breed was fueled by natural gas.
Oh wow, there we go. The way this atmospheric gas engine works is it's got a massive piston inside this cylinder. So then when that piston starts moving upwards, it draws in a mixture of gas and air. And when it gets to a certain point, somewhere around here, that pilot light, a little bit of that flame gets pulled into the cylinder. It causes an explosion, and that throws the piston up through the cylinder.
Essentially a power station in miniature, Otto's single-acting cylinder was hugely successful. But it was his newly improved gas-powered model that could provide the solution for Hudson Yards engineers.
This is the next iteration of Otto's design, and it's truly revolutionary. It uses something called the four-stroke cycle.
Unlike his previous engine, this makes 4 strokes of the piston for each ignition. First, the piston moves downwards, sucking air and gas into the chamber. Secondly, as the piston rises, the air and gas is compressed. Thirdly, it's ignited and the piston forced down. And on the 4th stroke, the exhaust gases are pushed out. The result is an incredibly efficient, reliable and quiet engine.
The principle behind this engine, the 4-stroke cycle, is also known as the Otto cycle, after the man who invented it. Engines like this were quickly deployed in factories, but they also rapidly found much more widespread use, particularly in the emerging automobile industry. This is a truly revolutionary principle of engineering. It's absolutely everywhere in the modern world.
Whereas Otto's innovation found its fame in light industry, engineers at Hudson Yards are using this game-changing design to provide an immense power backup system. In 2015, 4 of the biggest 4-stroke gas engines in the world arrived on site in Manhattan. 40-ton, 20-cylinder, 4,600 horsepower beasts.
What we're looking at here is very comparable to what you'd find in the front end of any souped-up hot rod. It's an internal combustion engine that operates on a 4-stroke cycle. It just happens to be about 30 feet long and 10 feet tall. This is really the beating heart of the energy infrastructure here at Hudson Yards.
If New York's electricity fails and the city is plunged into darkness, the natural gas supply will kick in and these monumental machines will take over the job of running the Hudson Yards power plant.
This plant protects Hudson Yards from power outages because it has the ability to operate in microgrid mode. What that means very simply is if there were an issue out on the utility grid, we could simply disconnect from the grid, then start restoring power that we source from our plant here. So the residents of Hudson Yards, the businesses that call Hudson Yards home, would be able to stay here and keep working come what may.
When called upon, these monster engines will produce over 13 megawatts of power.
It is exciting to hear one of these engines fire up. It is the same sort of teenage boy excitement that you would find, turning over any engine, multiplied several-fold because of the size of these engines. This engine has a heartbeat. This engine breathes. This engine creates energy, and you get a very visceral sense of that when the plant is running.
The Hudson Yards project represents impossible engineering on a staggering scale. A brand new 28-acre neighborhood built over a working rail yard.
Everybody knows the Manhattan skyline of New York, so when you change it, that's actually in some ways the most exciting thing. All of a sudden there's this monumental cathedral in the middle.
Every stage of this trailblazing enterprise poses extraordinary challenges.
The engineering on this site is such an example of incredible teamwork and incredible vision from so many people to be able to bring this to fruition.
But inspired by the work of the pioneers of the past, upscaling and breaking the mold themselves, the engineers are succeeding in making the impossible possible.
Coming onto the construction site, you get to appreciate it every day, but still every single day, it's a wow moment. I love this project.
The United States is renowned for its naval might. It has some of the fastest and most heavily armed ships on the planet. But patrolling the 360 million square kilometers of oceans requires more. Vital to the Navy's success is its air arm. And basing an air force at sea presents a unique engineering challenge. One that Chief Petty Officer Jeremy Stecklein is familiar with.
Those waters need to be patrolled, need to be protected for American interests. The forefront of military might has really become naval aviation, and it's very, very important to transfer that power anywhere in the world.
The US Navy requires a new breed of ship, capable of transporting more planes than ever before.
As we move into the 21st century, there becomes a new need for technology, a new way to combat the forces around the world and to help out with humanitarian efforts around the world. The United States Navy needs something brand new in technology to help those aids.
The solution? The Ford-class aircraft carrier.
Ford-class carrier is the largest warship ever built. It's about 1,100 feet long, weighs about 100,000 tons. It's about 24 stories tall.
Its scale is unheard of. Its 35-knot top speed makes it pound for pound the fastest carrier ever built. And it's on the brink of making history. The first of this colossal class, the Gerald R. Ford, has just been delivered to the US Navy and is undergoing vital sea trials to find out just what it's capable of.
This ship can carry aircraft and technologies that are out today, as well as that we haven't even dreamt of yet. This is the most impressive ship I've ever served aboard.
In dry dock in Newport News, Virginia, Jeff Hummel and a team of engineers are building the second of this 10-strong fleet of carriers. The John F. Kennedy.
We've been working on it for about 3 years. We got about another year and a half in the dry dock, and then after that we'll spend about 2 years of testing it before we deliver.
Mike Butler heads up construction of these trailblazing ships.
Well, an aircraft carrier has to satisfy two major roles. One is a humanitarian role, and one is a defensive or offensive military role. This ship does both and does it very well.
The largest warship ever built, the Ford-class carrier is almost as long as the Empire State Building is tall. 35 aircraft are stored in a giant hangar. 3 supersized elevators deliver the planes to a 337-meter-long flight deck, equipped with an electromagnetic catapult system, capable of launching planes quicker than ever before.
The amount of technology that's been infused into the ship is going to put the Navy in a position to fight the wars of the 21st century. It's going to be the most capable ship out there in the fleet.
But creating the world's largest mobile airbase poses many challenges. How do you power a 100,000-ton vessel with 4,500 crew?
What we do is live everyday lives, so washing laundry, serving 20,000 meals a day, so it's like powering essentially a small city.
How is it possible to get jets airborne in just a fraction of a normal runway?
The greatest challenge is to be able to get the aircraft to the speed that it needs in order to take off.
And how can you bring them home safely?
Landing on a carrier requires an external means of stopping the aircraft.
But the engineers face an even bigger problem. The Ford class holds more planes than any carrier before it. They must be able to launch and recover an astonishing 200 missions a day. So how do you achieve that on a ship? Engineer Marco Estrada is facing that challenge.
Typically, an aircraft carrier of the Ford class will hold approximately 78, 79 aircraft. The job of managing the flight deck is an organized chaos. You have launches, you got recoveries, you got fueling, you got weapons at the same time. So it's a very challenging operation.
To achieve their unprecedented mission rate, some aircraft must be able to land at the same time as others are taking off. It's an impossible problem that was faced by the innovators of the past. US Navy pilot Lieutenant Leslie Garcia is a fast jet specialist, well aware of the huge problems of launching and landing on an aircraft carrier.
It is not uncommon to have over 20 aircraft launch right before 20 aircraft are recovering during the same open deck time.
Pilots and engineers have faced these challenges for decades. In the wake of the Second World War, aircraft carriers got bigger to take on more aircraft. But as prop planes gave way to jets, the carriers' straight runways were hampering operations. Landing and launching these fast, heavy jets at the same time on a single runway was impossible. To simulate the straight deck's limitations, Lieutenant Garcia is handing over the flying to a model plane club.
So right now we're putting down the center line of the straight deck carrier. I didn't know I was going to get a workout while I was out here too.
The historic straight deck design is ready for takeoff, but how will it cope?
They're going to go airborne, execute their mission, and then look to come in and land.
As the mission gathers pace, landing simultaneously is impossible.
Now we've got the next cycle of pilots getting ready to take off, while the first cycle that we launched are still airborne and waiting for their opportunity to come land. So as you can see, they're basically fouling the whole flight deck. It's a very inefficient process.
But in the 1950s, aircraft carrier design was turned on its head. Now a floating museum in San Diego, the USS Midway was one of the first American carriers to be fitted with a game-changing solution: the angled deck. It was the brainchild of British Royal Navy Captain Dennis Campbell and engineer Lewis Boddington. They supplemented the traditional straight deck with a second runway. The plane's landing area was now separated at the ship's waist, whilst launch catapults were safely positioned at the front of the ship.
When this was a straight deck, you would basically just see one landing area straight up and down the ship, with taxiing and launching aircraft towards the bow of the ship, landing aircraft towards the back. Really, the game was changed when we went over to the angled flight deck. It became so much more efficient and, more importantly, so much safer.
The Midway's remarkable refit allowed her planes to take off and land at the same time.
The landing aircraft are going to be offset so that if they need to take back off, if they missed a wire, they will have the angled deck that is going to keep them away from the launching aircraft that are launching straight ahead.
So, will adding an angled deck bring some order to today's mission?
As you can see, we've got one taking off. He's going to come around and start executing touch and goes while we launch the other aircraft.
As on the Midway, Campbell and Boddington's addition transforms this airstrip into a well-oiled machine.
He's approaching on his landing. Let's go ahead and launch the second. And you can see that those two flight paths are naturally deconflicted because of the angle that landing aircraft is coming in on. We're basically getting two landing strips for the price of one.
The US Navy's ultra-modern Ford class is also equipped with an angled deck. But whereas the Midway launched just 89 sorties a day, the Ford class can complete over 200.
When you look at the flight deck as a whole, 4.5 acres seems large, but as you add 50 fighter aircraft and around 100 to 150 personnel at all times performing the various tasks, it gets very, very small very quickly. The ballet of us doing our job, they call controlled chaos, and that's really what it is.
400 yards!
The Campbell and Boddington-inspired angled deck enables the Ford class to complete 25% more sorties a day than the US Navy's previous carrier class.
The angled flight deck is a major feat in engineering in itself. With that angled flight deck, we have a living airport that is receiving aircraft at the same time it is launching aircraft simultaneously.
With the second in class, the John F. Kennedy, under construction, it's up to engineer Marco to deliver the Ford class's next awesome angled deck.
Currently, we are at the 01 level of the ship, so there's going to be a couple more levels going up where the flight deck is going to be. So currently, we're a little lower than the flight deck, but once the flight deck is installed, we should see the angled deck in this direction. The island structure should be in that direction.
The position of the island is radically different from all previous designs of US aircraft carriers. This is one of the keys to the class's extraordinary capacity to launch and recover aircraft at the same time.
On Ford class, the island structure was moved from this area to area closer to the stern of the ship. That allows more of the parking of the aircraft forward of the island structure, which allows the Navy operators to turn around the aircraft faster. Fuel, service, weapons loading, and in turn generates more sorties. At this point in time, this aircraft carrier design is the pinnacle of flight operations support for the US Navy.
The relocated island also has a smaller footprint than its predecessors, creating extra usable deck space. Beneath the runways, aircraft are stored in a cavernous hangar. and delivered to the flight deck by 25-meter-long electromechanical elevators. Positioned on the sides of the ship, any craft can be maneuvered without disrupting launch or recovery.
What you're looking at is what we call ACE 3, or aircraft elevator number 3, which is right here on the port side of the ship. And the elevator is up right now, as you can see, but as you look on these slots, this is what actually slides our aircraft elevators down to the hangar bay, and how we move our aircraft in and out for maintenance and operations, and then move it back up to the flight deck and taxi them off.
The Ford class is undoubtedly taking aircraft deployment to a whole new level. But the engineers face another almighty problem: powering this giant carrier.
The last two ships in naval service were under diesel power, but there are major drawbacks.
During lengthy missions, a traditional fuel-guzzling diesel engine could spell disaster for the Ford class.
You have to either dock at port, refuel, or be tied up across another ship, and that'll leave you vulnerable.
In Newport News, Virginia, the world's largest ever warship has been unveiled. The first of the state-of-the-art Ford-class carriers is now undergoing sea trials. Vital testing to ensure it will be capable of launching aircraft more quickly than ever before.
The aircraft carrier is a moving base. It is a moving city. So we have a mobile city, a mobile airstrip with all of the capabilities of any airfield, and it can be moved anywhere in the world.
Taller than London's Nelson's Column, longer than 60 New York cabs, and almost the width of an Airbus A380. It can hold up to 75 aircraft and accommodate 4,500 crew. In dry dock, the second of this brand new class, the John F. Kennedy, is currently being assembled. Construction director Jeff Hummel is supervising part of the mammoth build.
When we're done building her, we'll deliver a ship of a little over 80,000 tons of displacement. When the Navy actually loads it up with crew and planes and supplies, it'll be close to 100,000 tons going to sea.
It will take more than 1.8 million kilograms of welded metal to complete this ship. Construction on this scale creates huge logistical challenges. The solution is to build the Kennedy in a series of massive sections known as superlifts.
Right behind us is what we call the lower bow superlift. It's about 60 feet tall and a little over 100 feet long. It's made up of 7 units that were built in our steel shops, brought over here and joined into one giant superlift. And then if you look over here just aft of it, what you'll see is the beginnings of what we call the upper bow. You can actually see the leading edge of flight deck there with that rolled shape. That's actually going to be the very bow of the ship.
These megastructures are only possible because of a staggering piece of engineering. One of the largest cranes in the world.
Behind me here is what we call our 1050-ton crane. Other people affectionately know it as Big Blue. This crane is rated for 1,050 metric tons. It's a very capable crane. The crane has 2 rails running what we call east and west, towards and away from the river. It spans about 540 feet between the rails, and it's about 230 feet tall.
When you're maneuvering 1,000-ton steel sections, there's no room for error. Big Blue's 3 hoists allow pinpoint perfection.
With this crane, you're actually making one move with all 3 hoists being synchronized. It's got some pretty good precision as far as how accurately we can place the unit or move the unit to get it within an inch or less. And then we can actually use some jacks to position the unit exactly where we want it. It's just cool, man.
But once at sea, the Ford class's sheer scale poses another enormous problem. As their missions will last for months at a time, propelling a ship of this size with traditional thirsty combustion engines is out of the question.
There are major drawbacks to being a diesel-powered platform. Every 1 week or 2 weeks, you have to either dock at port and refuel or be tied up across another ship to refuel, and that'll leave you vulnerable.
Not only that, the power needs to satisfy the demands of over 4,500 crew.
We have all the galley and food services, stores, personnel accommodations. There's a tremendous amount of different systems underneath that flight deck, making the ship go and allowing it to perform its mission.
A new power source is needed. Can the innovators of the past shed any light on the problem? Cartagena in southeast Spain could harbour a solution for the Ford class. Former Spanish submariner Diego Cavado is visiting the historic naval base of a nation that once ruled the waves.
This was the very navy that carried famous explorers across the Atlantic to discover the New World.
By the 1800s, the might of the Spanish Navy may have faded away. But in 1888, a new breed of maritime engineering surfaced.
This is the Peral submarine.
The world's first fully functioning military submersible. The 22-meter-long Peral changed the face of warfare.
This was the first submarine that made navigation absolutely submerged, sailing at 10 meters deep. That's incredible.
But the Spanish engineers had the same problem as the one facing the Ford class: how to power the Peral on long missions through the world's oceans.
Propelling the submarine was very difficult. It was a big problem. The obvious choice was to use combustion engine.
However, a combustion engine's toxic fumes would be deadly in this airtight steel tube.
The air is necessary for sailors. Engineers need a solution to this problem.
The submarine's designer, naval engineer Isaac Peral, had an ingenious answer. To create sustainable power beneath the waves, he turned to electricity. And today, Diego has special access to the heart of the solution.
The submarine was 613 batteries, this side and this side. Each one is this side, okay?
The Peral was lined with 30 tons worth of rechargeable lead-acid batteries. Their first job, to propel its sleek structure through the depths.
Here, this side and this side, the two electric motors, and this one and this one, the two propellers. Of the 613 batteries, 400 of them was only for motors.
Virtually every system on board was also battery-powered, making this the world's first truly self-sufficient sub. The Peral paved the way for electric submarines throughout the world. And although nuclear eventually took over, Isaac Peral's contribution to marine power is beyond doubt.
Peral was not a normal engineer, an excellent engineer, on top of the engineers.
The Peral's batteries allowed it to cruise underwater for a few hours with a range of 132 nautical miles. But the Ford-class power source can keep it at sea for months at a time without refueling. Building on modern submarine technology, the solution is a pair of nuclear reactors.
One of the major advantages to having nuclear power is the engineering feat of actually getting 100,000 tons of displacement with the aircraft carrier through the water at about 35 plus knots. We are able to have 4.5 acres of sovereign American soil anywhere in the world for up to 25 years at a time under nuclear power.
The nuclear reactors split uranium, producing heat which converts water to steam, driving 4 turbines. These rotate 4 propeller shafts to propel the 337-meter-long carrier. But the reactor's output is so immense, they can also produce huge amounts of electricity. Unlike any carrier before it, virtually everything on the trailblazing Ford class is powered by electricity.
Essentially, what you're looking at is an electrical ship. It's like an electric car, only think of that about 100,000 times that size. USS Gerald R. Ford carries a load of 13.8 thousand kilovolts of amperage. So you're looking at 3 times the amount of electrical load that the aircraft carriers before us have ever had. And that allows us for some of the new technology that we have on board.
And over 3 million meters of electrical cabling also provide energy for 4,500 crew on board.
The USS Gerald R. Ford is a floating city, so we have every service that a civilian counterpart or an actual township that you might live in might have. We have a post office, we have gyms, we have a coffee shop, we have laundry service. We have that on board so that we can sustain ourselves out for long periods of time and really be effective.
This giant of the sea is built for the future. But today, the engineers face another seemingly impossible challenge.
You only have a fraction of the runway that an aircraft typically would need in order to take off.
If the aircraft didn't have enough power, it could be very catastrophic because the aircraft could end up going into the water and not taking off at all.
In Newport News, Virginia, an army of engineers are constructing the seemingly impossible. The Ford-class aircraft carrier, the largest warship ever built. This brand new class has 17 decks. Its colossal flight deck stretches to 5 acres. Supersized engineering designed to deploy more aircraft missions than ever before in any part of the world. The first of this game-changing fleet has just been commissioned into the US Navy.
USS Gerald R. Ford is setting the standard and setting the bar on the way that aircraft carriers around the world and the way naval operations are going to be dealt with and sustained.
10 record-breaking carriers will eventually make up the class. The second of which, the John F. Kennedy, is currently being assembled. When completed, it will be well over 300 meters long. But its runway will only be around 1/7 of a normal runway's length. Launching aircraft in this distance poses a huge problem for engineer Gabe Sava.
The runway on this carrier is going to be just under 350 feet. So the greatest challenge involved in launching an aircraft from a carrier is that you only have a fraction of the runway that an aircraft typically would need in order to take off. To get the aircraft to the adequate speed, we have to use a system of launching, which is a catapult system that propels and accelerates the aircraft so that it can take off.
To date, launch catapults have been steam-driven. But these systems lack acceleration control and would rip apart the Ford class's lighter aircraft, such as unmanned drones.
Steam-powered catapults, by their very nature, can put a lot of loads or stress on the aircraft. In addition, steam catapults require a lot of maintenance. There's a lot of corrosion within the troughs because there's a lot of moisture.
The Ford-class engineers proposed a new solution: catapult power generated by electromagnetics. Petty Officer Daniel Rivera is part of the launch team involved in the initial testing.
We had to perform what's called dead load testing. A dead load is essentially a big piece of metal on wheels that represents different aircraft weights. And pretty much we were all on the flight deck and we launched each dead load. The dead loads would go actually off the boat. They would take off and fly over into the James River.
Concealed below the catapult's shuttle and rails The electromagnetic aircraft launch system known as EMALS uses the ship's power to create an enormous electrical charge.
The system uses 13,800 kilovolts that's being generated from the ship in order to power the equipment. And with that energy, we're able to launch an aircraft 0 to about 150 miles per hour in just under 3 seconds.
With the plane on 100% throttle, this huge shot of electricity is released into a series of electromagnets positioned down 2 launch rails. A powerful magnetic wave propels the attached plane off the runway.
With EMALS, the power that we produce during each aircraft launch is a lot more controlled. So for that reason, we can be able to launch a wider range of aircraft using computer software. While the catapult is going down the track, it knows how much power is needed in order to get that aircraft off the deck.
But sometimes even the mighty EMALS catapult isn't enough to get the jets off the deck. Chief Petty Officer Jeremy Stecklein has experienced this potentially dangerous situation firsthand.
There are times that we're out in the middle of the ocean, depending on weather, depending on what the aircraft needs to be loaded down with. Sometimes that aircraft doesn't have enough power on 100% throttle to reach that minimum airspeed, and sometimes we need just a little bit extra.
For the engineers, this is a problem that could end in disaster.
If the aircraft didn't have enough power, it could be very catastrophic because the aircraft could end up going into the water and not taking off at all.
So how can these phenomenal jets produce more power? It's a challenge that's been faced in the past. Engineer Dan Dickrell is at the Patuxent River Naval Air Base in Maryland, the site of an extraordinary innovation that could provide a solution for the Ford class.
This is a T-38 Talon. It's a 2-seat trainer. It's powered by 2 General Electric J85 engines. Top speed's over 1,200 miles per hour, which is supersonic, faster than the speed of sound.
Today, the T-38 is entering the Hush House, a secretive test facility where engineers can see how jet engines perform up close.
All right, so the T-38's tied down. The test is about to begin. Let's do it.
With special clearance to be just meters from the engine, Dan is witnessing a test that will reveal one of the keys to a successful aircraft carrier launch.
Here we go. Test is beginning. Pretty exciting. You can hear it spooling up. When it goes on, we'll know. All right, here we go.
This incredible sight is created by what's known as an afterburner.
Man, I love the smell of jet fuel in the morning, you know what I mean? It's really good, it's really good stuff.
The afterburner is the secret to producing thrust, the explosive power required by the Ford class's jets. It was invented over 85 years ago by Sir Frank Whittle, one of the forefathers of the turbojet engine.
A Meteor jet plane is ready for an unofficial approach to the sound barrier.
During the 1940s, the race was on to break the sound barrier. Jet engines needed more power, but making them bigger was out of the question. So Whittle devised his radical solution: the afterburner.
See, it's right here in the back of the engine. It vastly increases the amount of thrust that's available to the engine without adding much weight or complexity to the engine itself.
A standard jet engine takes air in, adds fuel, and ignites the mixture, propelling the aircraft forward. Whittle realized much of the oxygen was unused, so he added more fuel at the rear of the engine to utilize it. This creates a massive amount of extra thrust.
When you're designing something, the simpler is usually the better. And Whittle's solution is amazingly simple, yet its performance increase is brilliant.
To fully appreciate the afterburn experience, Air Force veteran Bud Green is reacquainting himself with the F-100, the first US jet to fly supersonic.
Last time I looked into the back end of an F-100 was 52 years ago. I'm a little nervous. Not nervous, but a little antsy.
Equipped with Whittle's awesome afterburner system, 0 to 100 kilometers an hour takes just seconds. At top speed, it smashes through the sound barrier.
Man, it's been a long time. Holy.
Courtesy of a staggering piece of engineering.
Very nice. Thank you, sir. Wow. Oh, bang one. We were going about 320 or something like that when he lit it, and you could really feel the kick. Because all of a sudden, you got a whole bunch of additional thrust, and it just knocks you in the rear end. It was fun. It was really kick. Unbelievable.
The Ford-class jets are also equipped with afterburners. This Whittle-inspired innovation enables them to take on the broadest set of missions ever launched from a carrier.
The ability of the aircraft to have this afterburner option increases our flexibility. It allows us to go up in weight with that extra boost of energy that will allow us to reach that minimum airspeed. So we can carry more ordnance, more fuel, anything that we need to complete our mission.
To successfully launch, the jets must reach over 200 kilometers an hour in just 100 meters. It's up to the flight crew to decide whether the plane will need any additional thrust.
As an aircraft is coming to the catapult, we're going to predetermine whether or not that needs to have an afterburner shot, depending on headwind, depending on armament of the aircraft itself, depending on how much she weighs. So we'll signal the pilot and we'll signal the crew on deck, letting everybody know that this will be an afterburner shot so safety concerns are met, and then we'll safely launch that aircraft into the sky. The afterburner is another tool that we have in our Navy toolbox to be able to get these sorties and to get our aircraft off-site and on target faster and anywhere in the world.
Launching over 200 jets a day is an incredible feat of engineering, but it's only half the story. Bringing them home is even harder.
Landing an aircraft is definitely one of the most dangerous activities that you do on the flight deck.
The Ford-class aircraft carriers are the largest warships in the world. They dwarf all of their predecessors. At 337 meters long and weighing in at 100,000 tons, this class of ship is still capable of at least 30 knots, courtesy of 4 props driven by 2 nuclear reactors. The second in class, the John F. Kennedy, is just months from launch. Engineer Jeff Hummel supervises construction of this groundbreaking maritime marvel.
The Ford class has really taken about a 40-year leap in the development of aircraft carrier technology. So we expect this ship to last 50 years. We really don't know what they need to be capable of in the future. Right now, we know they need to be capable of launching and recovering airplanes and serving the different humanitarian missions that they'll do for the Navy.
Sea trials are currently underway for the class's first completed ship, the Gerald R. Ford. To satisfy its multi-mission remit, it's built to transport an assortment of aircraft.
We carry helicopters, we carry aircraft, we carry other ships on board the aircraft carrier, so we have an armament of ways that we can help out that's not just on a war effort.
But the pilots and crew face a mammoth problem every time their aircraft return from a mission.
Landing an aircraft is definitely one of the most dangerous activities that you do on the flight deck. This is because of the short runway and the precision that's required.
Somehow the jets have to stop in just 1/7 of a normal runway's length, or they'll end up in the drink. Can a bold pioneer from the past provide a solution to this seemingly impossible challenge? It may be hard to believe, but this beautiful biplane could hold the key to landing on the Ford-class carriers. Engineer Dan Dickrell is in Virginia discovering how.
So that marvelous airplane that just took off is the Ely Curtiss Pusher. Even though that's a replica, it was built in 1910 and it first flew in 1911. Oh, it's beautiful to watch in the air. Today, it looks like a very simple machine, but at the time, it was a cutting-edge flying machine.
The Curtiss Pusher was the first ever plane to take off from a warship. But American pilot Eugene Ely wasn't satisfied. He also wanted to land his plane on a ship. However, he only had 120 feet to work with. A problem demonstrated as today's flight draws to a close.
The biplane's landed. It first touched down right about here and has coasted to a stop. I'm gonna pace it off and see how far it took to come to a complete stop.
If this plane was landing on Ely's ship, anything over 120 feet would have ended in disaster.
All right, here. Hey, Boom. How's it going?
How you doing? Terrific. How much was it?
It was 275 feet.
It would have smacked probably right into the superstructure of the ship in that case, or over the side if it wasn't the superstructure.
But Ely had the help of engineer Hugh Robinson, who came up with an idea to bring his aircraft safely to a halt. It's a solution that could help the Ford class.
Robinson came up with arresting gear. This was a system that was designed to bring the plane to a stop. It was little more than rope and sandbags.
Robinson tied the rope between the sandbags across the ship's deck. The plan was to transfer the landing plane's momentum into the heavy bags.
Here we have a tricycle. This is going to mimic the frame of the biplane. Now, Robinson took a tail hook and attached it to the bottom of the biplane, something similar to this. The purpose of this hook was to catch with the ropes that would arrest the plane, taking its forward momentum, bringing it to a stop. Now, what I'm going to attempt to do is recreate how this tail hook works. So if I build up a little forward momentum, you can see what happens. I'm going to want to stop before I crash into this wall, drop the hook. Oh, yeah. So the forward momentum that my tricycle had was completely consumed by the sandbags. The tail hook dragged the sandbags along the ground. Friction was consuming all of that energy. It works really, really well. What a really brilliant concept it is.
And in 1911, this uncomplicated solution brought Ely's plane to a standstill in just 30 feet, on board a converted warship.
That particular innovation was the example that landing aircraft on ships was possible. It really paved the way for what we see today.
The Ford-class engineers are adapting Robinson's ingenious concept. But whereas Ely landed his biplane at 64 kilometers per hour, these jets are approaching at 4 times that speed. And they are 65 times heavier than the vintage aircraft. The solution is a cutting-edge system known as advanced arresting gear.
The current advanced arresting gear system on the Ford can arrest aircraft up to 50,000 pounds. In order to do this, it has to have precise controls so that you don't overstress the aircraft. As the aircraft approaches, it picks up the pendant off the deck. The cable tension then goes through a cable shock absorber. The shock absorber takes out the wave in the cable. It's kind of like car shocks. Then the braking power is provided by a water twister.
Situated below deck, the water twister is a paddle wheel submerged in fluid. Its rotation provides frictional resistance, absorbing around 2/3 of the landing's energy.
The remainder of the arrestment is controlled precisely by a motor generator that takes that kinetic energy and turns it into electrical energy that is then stored for later uses on AAG.
The advanced arresting gear is also incredibly adaptable. During a 2-second landing, computer controls continually adjust the gear according to the aircraft's weight.
In other words, I can arrest lighter aircraft than I would have been able to with my old system, or heavier aircraft, because I have the ability to actively control the arrestment. This system also actively compensates for the aircraft being potentially off-center or off-target, and it is able to control the payout of cable in order to reduce the amount of stress on the aircraft and land it safely.
Brilliant engineering is taking another of history's ingenious inventions into the 21st century. For those who serve on board, the Ford class is undoubtedly taking aircraft carrier design to new heights.
The fact that a 17-deck, 4.5-acre, 100,000-ton in-weight ship can be in service for 50 years is just an incredible thought.
Through the efforts of its engineers and crew, this ambitious class is changing the face of marine engineering.
For me, it's a tremendous honor to be part of the team coming together to put together this great Navy ship.
By building on the work of the pioneers of the past, upscaling, and making their own discoveries, the engineers are succeeding in making the impossible possible.
Where we go from here, really the sky is the limit, and I think USS Gerald R. Ford shows that impossible engineering is not so impossible.
Shanghai, city of the future. Vying for attention in this fast-growing, high-tech metropolis is some of the world's most cutting-edge architecture and ever more extraordinary feats of engineering.
There is a great competition for creating these landmark buildings. The clients have always asked me, build me a landmark.
Architect Martin Jochman has been set a seemingly impossible challenge: to design a radical new hotel that will stand out in this hotbed of innovation. But the unique site totally defies convention. It must be built 90 meters below ground level, in an abandoned, flooded quarry.
When I came here almost 12 years ago, it was just a hole in the ground. Now, over the years, against all the odds, this has changed.
Martin's master plan is one of the world's most inventive buildings. Resembling something from a James Bond movie is the intercontinental Shanghai Wonderland. This giant quarry hotel spans 100,000 square meters and is the first of its kind on the planet. Helping to realize this epic multi-million-dollar fantasy project is chief engineer Xiaoxiang Chen.
I'm very proud of being a part of the project. Everybody is excited because it is the only one in the world.
What, at ground level, first appears to be a two-story building is in fact only the tip of the 337-room hotel. It projects out from the precipice and descends to the base of the quarry 90 meters below. The glass wall in the center is designed to look like a waterfall cascading to the quarry floor. This will be flooded to create a lake, submerging the two lowest floors. It's an epic engineering challenge once thought impossible.
Such unusual location brings its problems to be solved. These can be summarized into the building shape, the seismic implications, and the fact that the building is partly underwater.
Not only must it be waterproof and earthquake-proof, but the engineers are also faced with a giant problem that looms all around them.
The biggest problem when we started designing this building was associated with the quarry itself, the composition of the rock. This rock has come out as part of volcanic eruption, and it has cooled rather quickly, which means some of it is quite solid, but some of it is crystallized and very, very crumbly. I can demonstrate how this crumbles easily in your hands. This problem had to be really solved before we could start on the main part of the construction, both for the safety of the guests, but also for the safety of the workers on site.
Failure to secure the unstable cliffs will mean disaster for the project. Building this groundbreaking hotel will need some impossible engineering from the past. The problem with rock walls is that they're prone to collapse. One reason why more discerning humans ventured out of caves and into homes made of other materials. The Nabateans took rock construction to the next level, carving Petra's fabulous sandstone temples and tombs. But over the centuries, many have crumbled. The presidents of Mount Rushmore are hewn from the toughest granite. But even they need a facelift from time to time. Any hairline cracks are filled as soon as they appear.
Hey, looking good, Abe.
But there's one device that's so effective at holding up rock walls that climbers like engineer Dan Dickrell are willing to trust it with their lives.
Oh, here it gets spicy. Woo! So right now I've climbed this rock face. I'm hanging in the air, and all of my weight is going through that rock bolt, which is anchoring me to the surface. So the rock bolt is a smart and simple idea developed over 100 years ago.
And this simple idea might hold the secret to solving the problems at the Shanghai Hotel. In 19th century America, lead mining was big business. The #1 producer was the St. Joseph Lead Company, and their mine in Bonne Terre, Missouri, was their biggest and most profitable.
This incredible piece of engineering ambition was, at the time, the world's largest man-made cave at over 375 feet high, and it was also the first deep earth lead mine in the world. It's really quite impressive.
This vast cathedral of a mine was operational for 97 years.
This place is epic.
When it closed in 1962, the water pumps that kept the tunnels dry were turned off, creating a 17-mile-long underground lake. And now, the only way to get around is by boat.
Mining this lead is no easy task. The miners are looking for the ore in thin veins, which are spread through the rock. They have to chip it out in large chunks of ore. Now, if we look over here, Some of the richest veins extend vertically, 375 feet from the bottom to the top.
So the question was, how to reach that precious metal buried in the walls, over 100 meters off the ground. St. Joe's was a forward-thinking company that prided itself on innovation. It recruited so-called experimental engineers, whose job it was to devise ways of extracting every ounce of ore. These early problem solvers faced the challenge of scaling the heights of these walls.
So this is what they came up with. The trapezes, a series of scaffolding suspended from the ceiling. The workers would work chipping away almost a skyscraper above the ground. The tools they used weighed 50, 60, 80 pounds. The men themselves were large, the rocks were heavy. Such a large amount of weight suspended above that cavernous drop.
And responsible for bearing all that weight, the newly invented rock bolts.
This is actually an original 100-year-old split rock bolt. You can see the split on the end. How would this be installed? Drill a hole in the ceiling and then pound a piece of oak in, which effectively would be a wedge that when you put the bolt into that hole and pound it in, the wedge would slowly split open the bolt, creating a very, very strong anchoring point.
Trapeze mining was a great advance, but it was these rock bolts that proved to be the real innovation.
It was noticed that after the scaffolding was removed, the rock bolts that still remained in the ceiling were holding up the loose rock that otherwise would cave in.
Securing a rock face is precisely what the team in China need to do. So how do the rock bolts achieve this?
I have a container that I'm going to fill with loose gravel. Now the thing about this container is it doesn't actually have a bottom. So now what we need to do is insert the bolts down into the temporary bottom. All right, let's put some gravel in here. I'm going to take the top washers and nuts and tighten them down. This will create a compressive force that binds all of the gravel together.
This will replicate the forces at work when bolts are inserted into a crumbling rock ceiling.
I'm optimistic. I'm optimistic this is going to work. I'm going to need a bit of help, so I'm going to have Adam from the Bon Terre mine come in and assist me with this. There we go. All right, Adam, slowly try and take the bottom off, temporary bottom. What do you know? It worked. You wouldn't think it's possible, but check it out. It's really, really solid. Management concluded that long bolts placed close together would safely knit the loose rock in the ceiling above us. Without knowing it, the miners here at Bon Terre had inadvertently invented real innovation, which is used all over the world today. What an accomplishment.
So, how can the engineers in Shanghai take this century-old discovery and put it to work?
Here are the rock bolts, which are a very important part of the stabilization of the cliffs. The rock bolts are in positions where they can be most effective in securing the cliff face on a certain grid.
First, the rock walls are blasted in several places to level them off. Then they insert 6,000 supersized rock bolts. The mega bolts, measuring up to 15 meters in length, are placed at regular intervals to make up a giant grid across 5,700 square meters of rock face. For added security, the whole area is covered with a layer of metal mesh, then sprayed with a thin layer of cement called shotcrete.
The mesh, together with the shotcrete, will prevent the crumbly face of the cliff falling down and endangering the guests and the visitors. This process is quite unique to this project. It has never been done on this scale before. It is in fact one of the great challenges that had to be overcome to be able to end up with this amazing building.
And Martin has the tech to make the most of seeing his design come to life from every angle.
Every time I come here, I'm amazed about the transformation of the site. To be able to actually get a picture from the same angle as you're rendering and then be satisfied that this is really as close as you can get to your concept vision, that is very satisfying, actually.
But this unique design has to be built to withstand the most destructive forces on the planet.
There's no precedent for this type of building in terms of seismic design.
Embedded deep underground, how could they make this impossible piece of engineering earthquake-proof?
Sometimes in the midnight, I wake up to think of the problem I should resolve.
In Shanghai, China, engineers are facing a subterranean challenge. This giant hole in the ground is the location for their city's newest state-of-the-art structure. A mega hotel built 90 meters below ground level.
Progress is going well. We almost finished it. But this project gives us many big engineering challenges.
Taller than the Statue of Liberty, the hotel is essentially an inverted L shape. The 10,000-ton steel mainframe is set into the base of the quarry, with the wider top section stretching out onto the cliff top above. But it has to be strong enough to withstand anything Mother Nature can throw at it, and this is earthquake territory. There is no greater destructive force on the planet than that generated by an earthquake. And China is one of the most active seismic regions of the world. The point of convergence of the Indian and Eurasian tectonic plates. The country is riven with fault lines. Engineers here are experienced in using methods to combat earthquakes in conventional buildings. But nothing like this has ever been attempted before.
There's no precedent for this type of building in terms of seismic design. So this creates a completely new problem to be solved, had to be done from the first principles with the latest engineering technology.
To help it withstand the forces of an earthquake, massive foundations are required.
As you can see, the foundations are immense, almost 50,000 cubic meters of concrete. It had to be so to give the steel structure the rigidity it needs, to embed the steel beams and columns into it quite deep, to satisfy the seismic regulations. But this throws a new problem: how to place such large quantity of concrete so deep.
In order to get such a vast amount of concrete to the quarry floor, the team need to come up with an innovation that defies gravity. The concrete for the foundations has to be mixed at the surface, then delivered to the base below. But sending it straight down a vertical drop means it's traveling too fast. The mix would start to separate, and by the time it reaches the bottom, it's unusable.
Normally on a building site, concrete is pumped upwards. This was placing it 90 meters down under gravity situation, so completely new method of pumping had to be devised for this.
It's up to Chief Engineer Xiaoxiang Chen and his team to come up with the solution.
During the construction, we have encountered numerous challenges, and sometimes in the midnight, I wake up to think the project, to think the problem I should resolve.
The team need to find a way to slow down the concrete's rapid descent to make sure they end up with a stable mix. So they insert additional mixing stations. The concrete drops down the first 15 meters, then enters the station. It gets remixed and sent on its way, passing through 2 further mixing stations. So once it reaches the base, it's the perfect consistency.
With lots of hard work, I'm very happy about the result.
But incredibly, 50,000 cubic meters of concrete on its own is not enough to protect it from an earthquake. Due to the hotel's unique design, the team need an extra engineering solution to prevent it from being pulled apart by opposing forces.
It is a tall building attached at both ends, and in the event of earthquake, both parts of the building move in different direction and different speed. So this creates completely new problems.
To prevent disaster, the engineers have to find a way to protect this unique structure. When the Earth moves, the only survivors are those that can somehow go with the flow. The Incas built Machu Picchu from precision-cut stones with no mortar. The stones are said to dance through the tremors, then fall back into place. China's Forbidden City has withstood over 200 earthquakes, thanks to an interlocking joint which spreads the impact of any tremors. What these techniques have in common is the flex factor. Italy has suffered centuries of devastating earthquakes, more than any other European country. So engineers here have been developing new ways of building which won't yield to the forces that regularly rock the landscape. These might hold the key for the team in China.
During the last 40 years, we learned to build the structures safe to withstand earthquakes.
Seismic protection engineer Samuele Infanti works for the company that designed Europe's first bridge engineered to be earthquake resistant. The Somplaggio Viaduct. Its twin decks run in parallel across Lake Cavazzo. And despite being 1.2 kilometers long, it remained standing when a powerful earthquake destroyed the nearby village.
So now we are entering the village of Somplago. As we can see, more or less all the houses were rebuilt after the earthquake. But it was only the bridge surviving that earthquake with no damages.
So how exactly did the bridge remain intact? Like the Wonderland Hotel, it's attached to high ground at the top and low ground at its base. The secret of its success can be found where the underside of the road deck meets the top of its vertical piers.
The idea it was to isolate the deck above the bearings from the ground. During an earthquake, this bridge will move back and forth along the longitudinal direction.
Using a principle known as seismic isolation, the key mechanisms are the mighty bearings which cap each individual pier. These are made up of sliding metal plates which allow the deck to move freely, protecting it from tremors at its base.
We want to simulate the effect of a seismic event, and this represents a conventional way of fixing the deck to the piers.
But on the second bridge, bubble wrap is added to simulate the bearings.
We can see that now the deck is kind of isolated. You see that we can move it back and forth in all directions. These elements provide a filter-like effect. So they are filtering the acceleration transmitted by the ground moving at the occurrence of the earthquake.
Dragging the bridges will replicate the vibrations of an earthquake.
You see that this model provided the typical collapse, whilst the other survived without damages. The bubble wrap in this case are simulating the behavior of the isolators. It means that the ground will move in a very quick manner, while the deck will move slowly, and immediately after the earthquake, the bridge can be ready to survive another event, an aftershock. And this way we can avoid the damage.
The principle of base isolation has been applied to structures around the world, saving countless lives. But can the engineers in China apply the same method to this unique construction project to avoid destruction?
The structural solution is totally unprecedented and comes with the fact that it's a building fixed at two ends. In order to satisfy the seismic requirements of the earthquake, it is important that this structure can move to a certain extent.
Here in the inner atrium, the rear of the hotel looks out onto the rugged exposed wall of the original quarry and the steel framework that supports the building. It's this that provides the ultimate defense against earthquakes.
The structure consists of horizontal trusses that sit on a concrete beam. These are then connected to the vertical trusses that are firmly embedded in the mass concrete at the base of the hotel. Together they form very rigid structure, but in case of earthquake, this can still move.
The horizontal trusses are not fixed to the platform at the top. Should the worst happen, the horizontal trusses can slide back and forth and ride out any seismic activity.
It's actually sitting loosely on a platform that will allow it to move freely. This will make it possible for the building to stand up during very strong earthquake. It is a unique solution to a unique construction problem.
With the structure now earthquake resistant, the engineers must face the next impossible engineering challenge: creating rooms underwater.
There is no light in this corridor because right now we are working on the underwater space.
But how can the submerged levels of this futuristic development withstand huge amounts of water pressure?
As an engineer, we need to find a solution for that.
Here in Shanghai, developers are pouring hundreds of millions of dollars into this giant hole in the ground to create a mega hotel. The first one ever to be built in a quarry. Its architect is Martin Jochman.
Such unusual location brings many challenges. One of those is the fact that part of the building is underwater. In fact, where we are standing will be submerged.
The quarry originally had a lake at its base, which was pumped out into the canal that runs above it. But the plan is to flood the quarry again before it opens. Walkways will cross the man-made lake to a central island, and a brand new waterfall will be built on the west face of the quarry. The bottom 2 stories will be submerged below water level, and an underwater restaurant and bedrooms will be surrounded by giant fish tanks.
One of the biggest problems to overcome when designing this building was the underwater rooms and public areas.
Architecture design manager Hao Tseng is overseeing this part of the project.
You can see there is no light in this corridor because right now we are working on the underwater space. Here is our very special and exclusive room. There is no traditional window. Instead of that, we have a big aquarium here.
To make this experimental concept a reality, the designers are setting themselves a seemingly impossible mission.
Our biggest challenge is how to deal with the water pressure and how to deal with waterproof. It's very important to keep the water away from the room.
The volume of water required exerts so much pressure that ordinary glass would break and flood the rooms. In order to realize their dream of underwater living, the engineers needed to look to the skies of the 1940s. At this airfield just outside Los Angeles, engineer Dan Dickrell is finding out what the team in China can learn from one of the most important planes in wartime history, the Boeing B-17.
As a child, I built models of this. One of the most iconic bombers of the Second World War. It's absolutely breathtaking.
Known as the Flying Fortress, this heavily armored warbird was designed to penetrate deep into enemy territory to carry out precision daytime bombing.
1, 2, 3, 4, 5, 7, 8, 9, 10, starting number 3 again.
This is one of the few airworthy models left in the world.
This is the aircraft that captured the world's imagination. It has a cruising altitude of 35,000 feet at a speed of 287 miles per hour. It weighs 29 tons. It's really a solid aircraft. At one point during the war, one of these B-17s returned, missing 2 out of the 4 engines, and had 180 flak holes in it like a piece of Swiss cheese. But it returned safely, which is a testament to how strong this particular airplane is. However, there was one part of this aircraft that was notoriously fragile and impractical, and that was the problem that needed to be solved.
The early versions of the B-17 had a weak spot.
The original nose of the B-17 was composed of a metal frame and large amounts of real glass. If you've ever broken a real glass, you realize glass shatters. This is obviously not great for the people behind the glass. Huge amounts of dangerous, sharp particles coming right at them.
To solve this fatal flaw, in later models this was replaced by a clear dome made of a brand new material, plexiglass. It was the invention of chemist Otto Röhm. Röhm's life's work had been the development of new plastics, but he discovered plexiglass by accident.
Röhm had MMA, which is a rudimentary acrylic in a petri dish. Sunlight hit the dish, heating up the MMA and polymerizing it, creating PMMA, which we call plexiglass.
He discovered that if it was heated, it could be molded.
So I'm going to keep mechanical strain on it while it hardens. As it cools, it will retain the shape. Yeah, it worked. It's a great material.
But crucial for aviation engineers was how it responded to stress.
Plexiglass doesn't shatter. And that particular property is what enables this aircraft to be such an effective daylight bomber.
This was a major development. The nose is one of the most tactically important spots on the plane, as it's where the bomb aimer sits. And plexiglass was not only safer, but greatly improved his visibility.
From this vantage point, you can see the view that the bomber would have. This bubble
This tough, transparent material could help the team in China achieve their vision. Within the giant concrete foundations sit massive water tanks.
We want the view of water tank as big as possible, but it has to be very clear. And due to the water pressure, the material has to be very thick. So we found acrylic glass. It's like 13 to 16 centimeters, and you can see it's very clean, and people can easily see through it.
But with added thickness comes added weight. This window alone weighs more than 2 tons.
You can see the acrylic glass is very, very heavy. We need 4 people at the same time lift the chains.
The largest windows on site weigh 4 tons, used in the hotel's underwater restaurant.
So now we are standing in the biggest space underwater. This is the dining room of our specialty restaurant. You can see there are 5 pieces of acrylic glass. The big acrylic glass is more than 5 meters wide and 3.5 meters height. It's very, very big and heavy. But behind them, it's a big water tank. It's like 30 meters wide. We really want the client to feel like they're staying in the ocean.
From the watery depths of this extraordinary construction to its heady heights, the engineers still face a high-level challenge at the summit of the cliff face.
To build something at the top of the cliff is a really big challenge for us.
In their quest to create more impossible engineering. Shanghai is famed for innovative structures punctuating the horizon. A new landmark is underway, but it won't be changing the skyline. Instead, it's pushing engineering boundaries deep underground. Racing to transform an abandoned quarry into a high-spec, high-end hotel resort
那个是核心任务啊
is a 5,000-strong construction team led by Chief Engineer Xiao Chen.
就上面这一层啊，上面但是因为下面它都是泡沫。It is the only hotel in the world built in the pit. We face many new challenges.
Building in a quarry is a mammoth operation. But the setting has provided inspiration for its biggest and most complex design feature, dreamed up by Martin Jochman.
The glass waterfall is symbolic of the connection of the rock face, the cliffs, with the water, and the shape is itself suggesting the falling water shape, and this is the most difficult part of the whole structure. It's curved, it's irregular, it's covered with glass, so it's a great challenge to actually put it together.
A complex steel framework is being covered with over 5,000 square meters of flat and curved frameless glass panels to create the illusion of a glass waterfall.
Now we are actually inside the glass waterfall. It is a vertical circulation containing observation lifts which will take guests and visitors from this floor down to the base and to their guest rooms. When I see what's been produced, I'm very happy that my original idea that I have sketched a long time ago is there. All credit to the team, the people involved in the design, the structural design and the construction.
The next phase is to start filling the quarry pit to create the man-made lake. It will need 200 million litres of water. With such a huge volume, it's a slow process.
Filling water of the pit. I'm very excited for it. It will take 4 months to fill it. but I'm very patient.
For architecture design manager Hudson and her team, there's one more challenge. An audacious final addition to make the most of this unique location from every angle.
That's a really magic and amazing view here. It is great to stand at the bottom and look up. We want to build something at the top of the cliff so people can stand at the top and look down.
The team want to somehow create a walkway right at the top of the 90-meter-high cliff face. It's an ambitious plan.
To build something at the top of the cliff is a really big challenge for us. We want to build something sticking out of the cliff wall, and it should be strong and safe enough. It's really tough for us.
The solution could lie in an engineering innovation embraced by a famous trailblazer of the past. In the wilds of Pennsylvania, tumbling rivers cut through the forests of the Appalachian Mountains. It's here that a landowner threw down the gauntlet to an up-and-coming architect to design him a home. Civil engineer Scott Hamilton is here to see how it might help the team in China.
Falling Water, a truly amazing architectural building. It challenges the very landscape it sits upon, and many have described it as America's most famous house.
The Falling Water House is the brainchild of innovative architect Frank Lloyd Wright.
Falling Water was commissioned by wealthy Pittsburgh businessman Edgar J. Kaufman. Kaufman wanted a home where he could hide away in nature, yet it had to be a big enough space where he could entertain lots of people.
Like the hotel in China, the location of the site proved the biggest challenge. Surrounded by rock faces and a river, the plot of land wasn't big enough for the house Kaufman craved, so he left it to Wright to find a solution.
What Wright came up with is this: a series of rooms and gigantic balconies with seemingly no support beneath, essentially creating spaces in thin air.
Wright pulled off this balancing trick by anchoring these platforms so deeply into the central chimney they didn't need any other support, providing he made them strong enough.
This will be my Falling Water house, just like Wright's design. So we take our ground level balcony. As you see, if we put it out, we need something to counterbalance. Wright used this chimney stack and the main structure to do that. So I'll use a brick. And then we have our next level. And again, we need something to counterbalance that. And then we have our top level. And we'll counterbalance that. So here's my Falling Water house model. So let's have a look with what can happen when things go wrong. As we take our load and we put it on our balcony, we see it starting to bend down. As we increase the load, we see it bending more and more. We get closer to our limits and we have a failure.
So Wright's ingenious solution was to reinforce these cantilevered floors with lengths of steel.
So there we have our reinforced cantilever. So let's give it a go and see what happens. We put our load on and we see it holds, just like we want it to. This design relied on a careful balance of both geometry and tension and compressive forces. If one part of this was off, the whole structure would fail. It was so radical for its day. Falling Water is a national treasure and a truly great engineering feat.
innovative design relies on impossible engineering. Wright's cantilevered platforms started from 10 meters above the water below. In China, they're 8 times that height. This is the Skywalk.
You are 80 meters high above the bottom of the quarry.
To create this impossible structure, the team turned to Wright's cantilevers.
We use cantilever series to support this skywalk. We cut holes into the rocks and insert many reinforced bars to build such a horizontal concrete base.
Using the cliff itself as the anchor point, 42 holes were drilled up to 2 meters deep. Steel beams were then inserted to carry the 74-meter-long stretch of reinforced glass.
It's a wonderful engineering feat. We are using ideas that are 100 years old, mixed with modern technology. I love it up here. That gives you the best possible view of the amazing engineering that went into building this hotel.
"12 years in the making, from the first concept to 5-star reality. The intercontinental Shanghai Wonderland is almost ready to open its doors to the world. Creating this unique subterranean structure has been an epic undertaking.
When I first saw the site, what I saw is really, really incredible. Working on this project is like a dream come true.
The engineering challenges in turning this abandoned quarry into a luxury resort have tested those involved to the limit.
The whole idea seemed too fantastic to be realizable. I'm happy to say that the results are quite amazing.
By drawing on the great pioneers who've gone before.
It's absolutely breathtaking.
Adapting, supersizing, and creating innovations of their own. The engineering and architectural teams of this veritable wonderland have succeeded in making the impossible possible.
This is the most important project in my life. When the first guest arrive, I will want to cry. I love every part of the hotel.
Yuma County, Arizona. 3,000 square kilometers of the harshest terrain in the American Southwest make up the US Army's biggest testing ground. Which means this uninhabited desert is anything but peaceful. This is the Army's biggest land combat vehicle, the mighty Abrams tank, known as the Beast.
Beast is an absolutely amazing machine. Abrams is the best tank in the world, hands down.
Deployed in every US conflict since its introduction in 1980, these amazing machines have stood the test of time.
There's no tank out there that is more lethal, more maneuverable, more ability to provide shock effect on the battlefield. This is the ultimate ground combat system.
The Abrams M1 tank. Weighing as much as a herd of 20 elephants, this 70-ton combat vehicle is turbo-powered to reach speeds of 45 miles per hour. It carries 4 crew, the commander, gunner and loader in the turret, with the driver below in the hull. The Abrams is put together in Lima, Ohio.
I absolutely love this tank. There's no doubt about it. The first year that I was married, I spent more nights here on my tank than I did in my home, and my wife can verify that.
Former tank commander Bill Goyne is the project manager.
If we were going to kind of walk around the tank, this is what we call the front glacis of the tank. So you can see the driver's hole is right in there. So the driver's down inside the hole. The driver sits kind of a kickback position. He's laid back. He's got kind of motorcycle type controls. Where that sight is up there, you can see those two windows. That's the gunner's sight. So the gunner is the one that we, is primarily engaging with this. It's a 120 millimeter smoothbore cannon. Then you've got up on top here, you'll see there's a remote weapon station. Put a 50 caliber machine gun on there. Then you've got this kind of almost looks like R2-D2 kind of thing sticking up right here. That's the commander's independent thermal viewer. Over in this hatch here, that's the loader's hatch. That's where you're going to be reloading from because it's kind of the largest diameter hatch on the tank. And then back here, this is where the turbine exhaust comes out of. So it's great on a cold day. You can be back here getting warmed up. Soldiers live on these tanks, and so you can kind of hang things off of here. You can wrap up a burrito and hang it and set it there for a little bit. It'll get warmed up real quick for you. Great on a winter day.
Cooking burritos aside, the Abrams tank needs to be able to perform a variety of vital tasks. Maneuvering across the battlefield and providing accurate firepower while keeping its crew safe. But making all that possible requires solving a long list of huge engineering challenges. How do you power a 70-ton monster up to speeds in excess of 45 miles per hour? How do you protect its occupants against all the threats of a modern battlefield? And how do you create a vehicle capable of taming whatever kind of terrain is thrown at it? The Romans used interlocking shields to create a protective shell all around their foot soldiers. But if one man tripped, the strategy literally fell apart. In the Middle Ages, siege towers were all the rage. But they were slow and cumbersome and, being wooden, highly flammable. But in 1487, Leonardo da Vinci had a light bulb moment when he saw a turtle. But if anyone had ever built his wheeled wood and metal cone, they'd have soon realized its shortcomings. Over 400 years later, an engineering innovation emerged that changed the face of the world's battlefields forever. The tank.
So this is a Mark IV tank, and it's the first mass-produced tank of the First World War.
Former British Army Captain Patrick Bury is at the Tank Museum in Dorset, England, to find out how these machines came into existence.
Now, there's three basic things in tank design which this actually encapsulates. Protection, mobility, and you got firepower. And all those design elements are still seen today in the design of modern tanks.
As this is a drivable replica, Patrick's able to experience firsthand what it would have been like to ride this mega machine.
This is incredible! The amount of noise inside here and the vibrations off the tracks, it's just unreal.
It was the brainchild of William Tritton, Walter Wilson, and draftsman William Rigby, who came up with this entirely new type of war machine. World War I saw deadlock on the Western Front. With both sides dug into their trenches, crossing no man's land in between was seemingly impossible on foot. So the British government asked this engineering trio to devise machines that would allow troops to advance across this torn-up terrain, and crucially, get them over the enemy trenches. And this was their solution, the British tank, a tracked and armoured fighting machine.
The tracks are really an amazing design for the time because they spread the weight and they also are able to deal with the mud.
It travelled at 4 miles per hour, and the infantry walked behind it, using it as cover until they reached the enemy lines.
You just get a sense of terror. If you were in the trench, if you'd never seen a tank before, one of these was unleashed against you. Just slowly trundling towards you, firing its weapons. There's nothing you can do about it.
It took an 8-man crew to operate the Mark IV, all squeezed into its cramped interior.
This would have been the driver's position when this hatch is up. You actually got a really good field of view. And then when you went into action, you'd close down this hatch like that. And you'll be using this periscope, which is just a tiny little slit. And obviously your sort of situational awareness is much more limited when you're in battle. Next to me, you would have had the commander of the tank. He basically is responsible for the direction and also the target indication. In the din, you know, he can tap the driver and tell him which way to go, but crucially, for the tank to move, he needs to communicate with the gearsman at the back. So often they would bang a spanner for the gearsman to stop. The driver would engage the clutch, the gearsman would change the gear. The tank track would either change direction, one would go, one would stop, and that would rotate the tank.
Many of these early machines broke down, and the crew were either poisoned by the fumes from the engine beside them or captured by the enemy. Despite this, engineers continued to develop this original design, and a tracked vehicle soon became a vital part of the military arsenal.
Although it's simple and basic inside and indeed out, it was really effective when it was unleashed against the enemy in the First World War.
In Lima, Ohio, former tank commander Bill Goyne and his team are standing on the shoulders of those early pioneers to build the most advanced tank ever made.
Really, it's drawing on pretty much every decade of tank innovation. If you go all the way back to World War I, it's a tracked vehicle, just like you see with the Mark IV. That concept hasn't changed. That no man's land that you just couldn't get across, well, that type of terrain still exists today. And this tracked vehicle solution is the best, most maneuverable in all of those types of difficult terrain. That's why we prefer this track solution still, even after 100 years of tank development.
The 20-meter-long tracks are made up of linked steel plates with reinforced rubber treads. Each track weighs a staggering 2.5 tons. Product manager David Moore oversees the process.
We hold the track up and over the road wheels. We're now joining the track with the last coupler, so we use that hydraulic actuator to pull the track together. And then once we adjust the final tension, it'll be done with the track tensioner on that last road wheel.
With the tracks on, the hull section is now complete.
At this point, it does look like a tank. That's a convertible. We call these convertibles at this stage because you can drive around a test track just like that.
Once fully assembled, those tracks mean that nothing can get in the beast's way.
Just because of the sheer weight of the vehicle, everything bends to its will going cross country. So because of that, you have this kind of smooth ride that you can really focus on using the weapon system. You can really focus on maneuvering. It's a very confidence-inspiring feeling that you have when you're inside the tank.
But for this mighty machine to be effective on the battlefield,
when the bullets start to fly, you're just trying to stay in the fight.
Its crew has to be able to defend itself.
It's a life and death situation out there, and you want to be able to engage that target before it has a chance to fire back at you.
The US Army's biggest land combat vehicle is the Abrams tank. The platoons in the field rely on the engineers back home to keep its capabilities up to date. It's a huge responsibility for project manager Bill Goyne and his team.
There's no second place when it comes to the battlefield, right? You either are the winner or you're in trouble. So in the back of our mind, there's always the tank crew. It isn't going to make them more effective because the cost of getting it wrong is too high. You can't put a cost on getting it wrong. We have to have the best tank that's out there.
Since its inception, the weaponry on the Abrams has been continuously improved and updated. Its first major modification in 1985 was replacing a 105mm cannon with a 120mm model. Its secondary weapon is a 7.62mm M240 machine gun. And fixed to the highest point of the tank, there's a 50 caliber M2 machine gun. As a former tank commander, Bill knows it's vital to find ways to control all this firepower in a simple, intuitive way.
There's a tremendous amount that's coming at you as a tank commander. You're on the radio, plus you're looking for targets, plus you're trying to maneuver. The bullets start to fly, and your pupils dilate, and you can't read anything, and your breath is going out of control, and you're just trying to manage, kind of yourself physically and still stay in the fight. So the engineering has got to develop a system that's usable under duress and allows the crew to work as a team. If it doesn't do that or detracts from that, then you've actually made it less capable.
In live combat, locating the enemy is crucial. Threats can come from any direction, at any time, day or night, in any climate or terrain. It's essential to be able to respond to danger quickly.
Every second counts when they're in combat situation.
Abrams Test Chief Greg Dudar knows the importance of rapid target acquisition.
It's a life and death situation out there, and you absolutely want to be able to detect, recognize, identify the target, and engage that target before it has a chance to fire back at you. A key component is to have situational awareness of anything that's around you on the battlefield, and that could come from any direction around you. It is tough, and that's one of the big things we're looking to enhance is awareness that the crew has when they're in the vehicle.
Coming up with ways to locate and defend against surrounding threats from inside a tank is a huge challenge for the current Abrams team, and one faced by engineers of the past. Engineer Dan Dickrell is taking this 100-year-old French tank out for some target practice to discover how it radically changed tank design.
I cannot describe to you the noise, the vibration. It's like being inside a belly of a steel monster. It's very visceral.
Known as the FT, at under 5 meters long and weighing under 7 tons, compared to the Abrams, it's relatively small and lightweight. The brainchild of automotive engineer Adolphe Ernst Metzmeyer and renowned French car maker Louis Renault. The FT was designed to be used in large numbers, with many sent at a time in a swarm to overwhelm the enemy. But what made this tank so effective was its ability to target the enemy.
You ready to go? All right, 3, 2, 1, go!
All the tanks built during World War I had a fundamental flaw. In order to get the gun pointing in the right direction, they had to reposition the whole tank.
Main gun slowly coming on target.
On the battlefield, this was highly ineffective.
And we're gonna call it right there. So about 48 seconds. 48 seconds to take the tank, spin it around effectively 180 degrees. If that was trying to kill us, almost a minute to turn this thing around. That's not very fast.
But the Renault FT solved the problem. It was the first production tank to have a turret that could rotate 360 degrees. To demonstrate the difference it makes, the tank will have to find the same target from the same starting position. But this time, it can give it some spin.
To rotate it, there's no motor. It's me, it's my power. And I have this strap, I'm strapped to it, I hang onto the handles, and I press with my legs as hard as I can to make this huge metal turret rotate around. It took the tank about 48 seconds to rotate the entirety of it 180 degrees to put the gun on target. I'm gonna give it a go. I got my stopwatch. Let's see how fast it takes me. 3, 2, 1, go. It's rotating. Whew, it's a little bit of effort. That took about 4.5 seconds. In situations where every second counts, that's a huge deal on the battlefield.
The rotating turret was truly revolutionary.
The ability for the turret to rotate a full 360 degrees was a huge leap in battlefield effectiveness. To be able to see all around and then position this tank gun on whatever target I could see all over the battlefield, it laid the basis for the modern tanks we see today.
The 30-ton turret of the Abrams tank weighs almost as much as 5 Renault FTs. But incredibly, it can also rotate 360 degrees in under 10 seconds.
The turret can slew 700 mils per second. So that's one of the many things that make the tank amazing, is the ability to move as much mass as it has just so quickly.
Like the FT, it can fire in any direction. But the big difference is that the Abrams locates its targets using state-of-the-art optics.
We can see the vehicle's sighting systems. We have the gunner's primary sight on the left beneath the commander's weapon station. And then on the right is the CITV, the commander's independent thermal viewer. The sighting systems allow us to see at night. And then there's levels of focus and zoom that can be brought in to scan the battlefield for targets. The tank is not just hardware, heavy metal. There's also a lot of software, electronics, and high-tech equipment. There's 1.4 million lines of code on this tank.
All this high-tech feeds into the turret's interior compartment. This is the nerve center of the tank.
20 years ago when I was a tank commander, you felt like you were getting into a suit of armor, you and your 3 closest buddies, your tank crew. Now it's a little bit more like getting into an Iron Man suit, right? You're getting in there and there's so much tech.
Known as the basket, this space, just 3 meters wide, is shared by a 3-man crew. The loader's position is next to an armored ammunition compartment. The commander has controls for rotating the turret and firing the cannon or machine gun. The gunner down below has their own sets of sights and weapons controls. So, what is it like to be at the controls of this powerful machine? Former US Army tank commander Joseph Murrieta has first-hand experience of its capabilities.
We have ourselves in the tank commander seat. The tank commander has an extension of what the gunner sees so that he can verify. We also have usage of our 360-degree viewer. Gone are the days of having your head out and getting your own situational awareness, which was really hard for a tank commander to break because it's really comforting to be able to see outside your tank and see the battlefield. So now that generation is pretty much gone, and you have a new generation that's trained to be undercover, to use his situational awareness and to rely on his thermals.
This new generation are also operating the machine gun by remote control and controlling the cannon with a joystick.
Like any full-size video game in an old school arcade, you will just give the input left, right, down, and up. And then you have the trigger, just like everything else. So you have a gun here that weighs more than 15 tons. You can see how effortlessly it elevates and depresses. So when the tank is on uneven terrain and traversing, the gun will stay stationary to its target. So while the tank is traveling, the gun is basically looking like this inside. And the reason it's doing that is it's actually staying on target.
The cannon can lock onto targets up to 4 kilometers away, even when it's traveling at speed.
The vehicle can be moving up to 40 miles an hour over very rough terrain, and the weapon is stabilized. So From the gunner's standpoint, he's sitting still. And what that results in is accuracy on the move. That means he's going to hit what he's shooting at.
But hitting those top speeds requires serious motoring muscle.
So you've got a 70-ton vehicle, you want it to go over 45 miles an hour, and what does it take to do that? It's all about the speed of the battle. It's being able to outmaneuver. That's really the hardest part of the engineering.
Red, this is Red 1. Engage tanks. Fire when ready.
The iconic Abrams M1 is the US Army's main battle tank. Keeping it ahead of the field over 4 decades of service is a great achievement for former tank commander Bill Goyne and the team involved in building this unique vehicle.
From an engineering perspective, it's right at the edge of what's capable. Even though from the outside it doesn't look like it's very different than what we fielded, 40 years ago, on the inside, it's completely different. The most updated electronics you're going to find on the battlefield are stuffed inside of this. But frankly, we're not allowed to even talk about what some of these technologies are that are packed into the inside of this tank.
A tank is effectively 2 separate machines in one. The turret controls sights and weaponry. The hull is its set of wheels. Almost 10 meters long, the rear is elevated to house the engine with the driver's compartment at the front. The turret and the hull are worked on separately on 2 giant assembly lines, overseen by David Moore.
When the turret finishes at the end of the line, the turret then gets its final gun shield, the turret basket guards on. At that point, we'll load it onto the finished hull.
Joining the 2 together calls for millimeter-perfect precision engineering.
We call it marrying a turret. You'd probably guess what we call it when we have to pull the turret off the vehicle. We call it a divorce.
Once the 2 halves are united, the combined weight is an incredible 70 tons.
This one looks like it's about ready to go for a ride.
So how is it possible to get this mighty machine moving at high speed?
One of the key tenets of armored warfare is shock effect. So you want to shock the enemy by moving at them so fast that they have very little time to react. It's all about the speed of the battle. It's being able to outmaneuver.
This presents a critical conundrum. The tank needs enough power to go all out, but if the engine itself adds too much weight, it becomes less maneuverable.
You've got a 70-ton vehicle, you want it to go over 45 miles an hour, and what does it take to do that? That's really the hardest part of the engineering, is getting that balance right. You need to have something that's giving you all the power that you need, but as light as you need it to be.
Designing an engine that's heavy-duty but lightweight seems an impossible mission. Solving it requires imaginative engineering from the past.
Starter light showing engage. Little booster pump shoving some fuel in. It's running on its own.
And there we go. Wow.
Aerospace engineer Ben Evans is taking to the skies in a pioneering aircraft that may hold the key for the team working on the Abrams tank.
That is an incredible feeling. Yeah, you really sense that this is a powerful machine, don't you?
It's lovely.
Mike Kurtell owns this iconic 1963 Alouette 2 helicopter.
The Alouette 2 helicopter really became one of the most influential helicopters in the middle of the 20th century. It set the trend for modern-day helicopters.
The first helicopters were powered by piston-driven engines like those used in cars. And as the aircraft grew in size, so did their engines. But ambitious helicopter designers struggled with this weight problem.
They wanted to make helicopters bigger and more powerful, which meant bigger engines. But increasingly they were finding that as helicopters got bigger, more and more of the power from those piston engines was actually being used to lift the weight of the piston engine and not the thing the helicopter wanted to lift, which was the cargo, the passengers.
They faced the same problem as the team behind the Abrams tank. They needed an engine that was powerful but lightweight. In 1950s France, one man came up with the perfect solution. Józef Skidowski was a Polish-born engine designer who pioneered the use of the turboshaft gas turbine engine in helicopters. The Alouette 2 was the first mass-produced helicopter to use the new engine.
So basically what we've got here is a jet engine, but instead of generating thrust, we're generating mechanical power down a shaft. This is one of the air intakes, and there's another one on the other side of the engine. It's sucking air in at the front of the engine here, and that air passes into a compressor. That compressor is squeezing the air, increasing its pressure and its temperature before it passes into the combustion chamber. So in this region here, fuel gets added and ignited, and then you end up with lots of hot, high-pressure exhaust gases which need to escape somewhere. And they come out of the back of the engine through the exhaust. But unlike a jet engine, where those exhaust gases are accelerated into a jet to push the aircraft forward, what we have inside here is a turbine. And that turbine is connected to a shaft running down the center of the engine. You can actually see the shaft coming out the front of the engine here into this gearbox system here, converting that power and sending it vertically upwards into the propeller system.
The key elements of the turboshaft engine are the compressor, which provides the pressurized air for added turbo power, and the turbine, which turns the shaft that spins the rotors. Although the engine weighs just 143 kilograms, it generates 530 horsepower.
So this engine system is revolutionary because you can generate more power for less weight than the conventional piston engines that were being used before the Alouette 2. This makes it perfect for something like a helicopter where you need a lot of power, but you really need to keep the weight of the aircraft down as low as possible.
Delivering maximum punch for minimal weight, the turboshaft engine took helicopter design to new heights.
The turboshaft really was a game changer, and what this allowed designers to do was to build bigger and more powerful helicopters.
So how can the team building the Abrams battle tank make use of a helicopter engine? By supersizing it. This gargantuan gas guzzler is a 1,500 horsepower version of Skidowski's gas turbine turboshaft. In tank terms, it's known as the Power Pack.
What we've got here is what we call a full-up power pack. It has the AGT 1500 gas turbine engine, basically the same kind of turbine that you'd find in a helicopter. So this will kick out the 1,500 horsepower that we need to move the 70-ton beast.
At 1.25 tons, it's a whopper, but it's the optimal power-to-weight ratio. A diesel engine with the same output would weigh twice as much.
So the turbine is actually about here. It's very small. So you have the air that's coming in through where this kind of red bag is, goes in through a compression stage just like you'd find in any other jet engine. We've got our turbine. The turbine is spinning. There's a shaft that goes right through here and interfaces here into the transmission. And this transmission here, all that power gets translated out these final drives that attach to the sprocket, drive the track of the tank.
The engine may be super powerful, but it doesn't make a lot of noise. This gives it a key strategic advantage.
So what you're hearing right now is the turbine sound of the engine. Most tanks are going to be diesel, and so you're going to hear them. They're going to be very loud, very smoky. But as you can see with this turbine here, there's almost no visual signature. Although it sounds loud to us on the battlefield, this is actually very quiet. You can be within a few hundred meters of this in the forest, and you won't even hear it at all when it's running. makes it more survivable, because if you can't be seen, you can't be hit. And so that's what's great about the turbine engine. Oh, it's the greatest sound in the world. It has such a unique quality to it, and it just sounds like high performance, right? It sounds like it's ready to go. It's just chomping at the bit. That's the real advantage that we get from an engineering perspective over a diesel engine is you effectively have immediate torque, meaning when you turn the throttle in this one, the tank's gonna move. It's gonna move immediately.
I think we're ready.
Yeah, we're good.
There's only one way to put the engine through its paces.
Engine firing up.
By taking it for a test drive at the proving ground in Yuma, Arizona.
All right, we're about to go out on course.
Today, Test Chief Greg Dudar is taking the Abrams off-road.
When we do testing out here, we test on all the road surfaces. We're ready to roll.
The Abrams can go from 0 to 20 in 7.2 seconds.
20 miles an hour, no problem. Open her up a little bit.
And has a top speed of 45 miles per hour.
It's quite amazing when it can be propelled this fast. It's actually a pretty smooth ride. We sure are riding in an Abrams.
The engine can run off most types of fuel. And although it does less than a mile to the gallon, it gives the tank the turbo force it needs.
It's always a good day to be out here and experience the power of the Abrams.
But before it's sent into combat, the #1 priority for the engineers is working out how to keep the tank crews safe.
How can we make this vehicle more survivable? And that's a real challenge for us from an engineering perspective.
This giant facility in Ohio is the ultimate tank factory. Birthplace of 10,000 Abrams tanks, each one an epic build incorporating the latest in military and mechanical engineering.
This one looks like a zero defect tank to me.
David Moore supervises this supersized assembly.
As the product manager, I oversee them all the way through the process to when they're delivered. All these tanks I consider my babies. Right now we have a completed tank. Gave them a final coat of paint and then put it onto a rail cart. And once they get a train load, we ship them. It's quite a sight when you see these tanks line up. They'll line up till you get a row of 24 of them or more. It's pretty impressive.
Before they're sent into the field, each one has to undergo a series of vital tests at the military proving ground in Yuma.
Let me know when you're ready for a round of the load.
Today, Test Chief Greg Dudar and his team are test firing the cannon on this newly built tank.
The test crew are unloading ammo, and they're going to bring it into the safe compartment in the tank as we prepare for firing. We're going to be in a safe location behind a blast shield. We expect to see a big bang and a large fireball. And you'll feel it. You can actually feel the sound waves in your body. So never a dull day when you're out at the test site testing tanks.
Roger, guys. Clear to load?
What they're doing right now, the weapon's been loaded. They're going through all their weapon checks, and they're going to go ahead and fire the weapon.
Roger. Clear to fire.
They get the on-the-way command. There you go. Hard to beat. That was amazing as always. It never gets old. I love the smell too. Serious shock waves, serious power. Lots of energy being released.
The tanks must deliver force, but they also have to withstand it. The biggest challenge facing designers like Bill Goyne is keeping its defenses up to date.
Just like any other business, ultimately there's competitors that are out there. that are constantly putting out new products with new capabilities, whether that's a new munition that we have to be worried about or some new threat that we have to be worried about. Because of that, we're constantly looking at what new technologies can we put in? How can we make this vehicle more survivable? And that's a real challenge for us from an engineering perspective.
Using the best possible armor has preoccupied tank engineers since the beginning. Originally, tanks were all made from steel plating. But post-World War II, as weaponry became more powerful, new armor had to be developed. And when a new type of anti-tank weapon appeared, for tank engineers, once again, the pressure was on.
Firing! 3, 2, 1! Wow, that was a big bang.
Physicist Andrew Steele is at a secret location in the British countryside to find out what they were up against.
This steel represents the armour plating on our tank. We've got 4 2.5 centimetre thick steel plates. There's 10 centimetres of armour in all. And as you can see, there's a pretty big hole in that. And if we go through, number 2, there's a hole. Number 3, there's a hole on both sides. And finally, number 4, there's a pretty big hole in that one too. It's gone straight through. So what sort of weapon could blow a hole in 10 centimetres of steel? Well, I've got a little model of one here. It's called an RPG, or rocket-propelled grenade. In here, you've got your high explosive crammed in the back, and when that explodes, it crushes this inverted copper cone. It turns it into an incredibly hot, thin stream of copper metal, and it just cuts through it like a hot knife through butter.
Engineers had to find a way to defend against these new weapons. In the 1960s, German ballistics scientist Manfred Held discovered the solution by accident. He was experimenting, firing different projectiles at disused tanks. Some of the shells hit the area of the turret containing leftover ammunition, making it explode outwards, often deflecting the missile, preventing it from penetrating. This discovery would prompt Held to create a revolutionary piece of military hardware.
What we've got here is a modern version of Held's invention. It's called an explosive reactive tile. The top layer is just this very thin piece of steel. Inside, we've got a couple of bits of foam, which are representing the high explosive, and then on the back, we've got a much thicker steel plate. Now imagine an RPG impacting on this tile. What happens is that thin, hot jet of copper pierces this outer layer very, very easily. And that then detonates this high explosive inside. And what that does is sends this front piece of steel flying, which is why it's known as the flyer plate. That means this piece of steel can deflect the RPG, deflect that explosive energy away from the thicker plate behind, and keep the tank and its occupants safe. So what you want to do then is place loads and loads of these plates all over different parts of the tank. Might seem like a counterintuitive idea that covering the exterior of your tank in explosives can make it safer, but this simple invention is very effective.
To see it in action, the team's creating a reactive tile to try to protect a new set of steel plates from another blast.
We've got 10 centimetres of steel plate back here, but this time in front of it we've got 2 mil of steel, and then just in there we've got a couple of little sheets of SX2 high explosive, which is representing that tile of explosive reactive armour. Let's go and set this thing off. Arm the explosives. Firing! 3, 2, 1! Whoa! Wow, this is a scene of total destruction. If we come down here, have a look through the rubble, you can see this is a piece of that flyer plate, the thin bit of steel that was on the front, and as you can see, it's been pretty heavily deformed. Now, our 4 steel plates are, well, nowhere to be seen. They've probably been thrown back somewhere into that pile of rocks. If there was the weight of a tank behind them, they'd still be in place probably, but because they've just been completely free to move, they've been scattered by that huge, huge explosion.
Once all 4 plates have been found,
that's warm as well. Wow.
It's possible to see whether they've been protected from the blast.
You can see here we've got piece of armour number 1. You can tell that because it's got a really big hole in it and because it's got this indentation here where the high explosive was just pressed directly against it. Then we go through to plate 2, still quite a big hole, a little bit of a dent. Plate number 3, you can see that jet has been split into 2, disrupted by that explosive reactive armour. And finally, plate number 4, you can see still 2 jets, but they've not quite made it through to the other side. So we've saved our tank and we've saved its occupants.
The success of the exploding reactive tile turned armour design towards a totally new concept: fighting fire with fire.
Held's invention was a real game changer. Just by adding a thin layer of explosive and a thin layer of steel on top of existing armour, you could massively improve the safety of the crew inside.
The team working on the Abrams adopted this technology and developed their own exploding tiles that can be added to its outer shell.
The reactive armor on the Abrams mounts to the skirts, so that the skirts are replaced with a very similar but different version, and then the tiles, they're called, are slid all the way down the hull. That provides protection for the hull, for the tank itself, and also the driver.
The Abrams reactive armour tiles, known as ARATs, are fitted to each side of the tank. Flat box tiles are attached to the hull and turret. Then an additional layer of curved tiles are hung over the top of the hull, just like Held's original invention. If they're hit by an incoming shell, they'll detonate.
It is an incredible technology. We do ballistic testing on the performance of the tiles themselves, and what it does is it creates just a tremendous explosion and very loud noise, not unlike the weapon firing. I'd say the ARAT is critical for certain threat environments. When you're operating the vehicle, having that protection increases the chance that the tank is going to survive any time it gets engaged.
If I was to go into combat again, this is exactly where I'd want to be. There is no safer place to be on the battlefield than inside of this vehicle. And the things that can be updated have been updated, and the things that worked really well, no reason to break them. That's why we're sticking with this tried and true design.
The Abrams tank is a victory for impossible engineering. After 40 years of service, this powerful piece of machinery remains the Army's top gun.
The original designers of the tank are really truly amazing to me that they built so much margin into this tank. And it's a testament to the longevity of this tank that we can still make upgrades to it and it can still maintain its performance over such a long period of time.
It's a constant battle to produce the best machine.
Engineers are curious and like to work problems, and there's a lot of things for us to do in order to deliver something this complex, but it's almost impossible to keep up with the latest technologies that are out there.
But driven to do their utmost for the tank crews, they're building on pioneering innovations of the past and creating new capabilities for the future to make the impossible possible.
We believe this is the best tank built in the world. Everybody's in awe. It's bigger than they imagine. It's faster than they imagine. We take great pride in what we do, and it brings the soldiers home.
Hampshire, England, the birthplace of flight in the UK. Home to one of the greatest aeronautical events on the planet, Farnborough International Air Show, where the biggest aerospace players unveil the world's most cutting-edge technologies.
This is gate B.
Can we be a bit gentle, Dan? I don't want the engines to fall out.
I'm not used to driving this.
But this year, an ambitious team of engineers are showcasing something so unique, it could steal the show.
So we're heading onto the runway.
capable of making an impossible dream a reality.
Mankind has always had this passion for flight, always looked up at the sky and thought, gosh, I wish I could do, frankly, what the birds do.
An innovation that will allow man to fly free.
We've had a great history of putting human beings inside flight vehicles, helicopters and aeroplanes. I think there's something deeply inspiring about the process of slimming that down to that raw, kind of impossible point where you as an unencumbered human being could just float around and move about wherever you like.
The awe-inspiring solution: the personal jet suit.
The suit consists of 5 gas turbines. They're the same jet engines that you see on a jet aircraft. Together, they produce enough thrust that you could equate it to around 1,050 horsepower, about 1.3 times a Formula One car. In terms of straight line speed, we set the record at about 32 miles an hour. It's a Guinness World Record.
This infeasible engineering is the extraordinary vision of inventor and test pilot Richard Browning.
We have opened the doorway onto a whole new realm of human mobility that was previously just the domain of superheroes in the science fiction world.
Trailblazing design also shaped by aeronautical engineer Angelo Gruberzic.
With this simple, small amount of equipment, you can essentially gain that full three-dimensional control of human flight that people have been aiming for the last 100 years. And I think that's something that's very special.
Weighing just 45 kilos, the jet suit is made from aluminium alloy, nylon polymer, and steel. Twin tanks holding 40 litres of jet fuel feed 4 microjet engines mounted on the arms, and one on the back. All controlled by a fingertip throttle trigger, and packed into just 2 flight cases. Minimal kit to turn man into flying machine. Richard and the team are using revolutionary technology. But now their jet suit is about to be put to the test in front of the movers and shakers of the aeronautical world.
Can you check I'm not twisted underneath there?
In a show where $170 billion of deals are struck each year.
So we're going to drive out to the edge at what, like 2 minutes to 1 or 3 minutes?
We're going to get going as soon as you're ready.
Oh, okay.
The team are keen to put on an impressive display.
This is something that people have not seen before, and many of the public are unaware that this is even possible.
Good heads up working.
But with human flight, nothing is guaranteed.
I'll kick the back when I'm about to take off.
There's a potential of having an incident. You know, if one of these engines suddenly fails, you know, things can fail.
When you're building the impossible, the challenges are huge.
Okay, I'm good.
For a start, getting airborne at all means defying the laws of physics.
The human body is not designed to fly. We don't have any flight surfaces, we have no means of propulsion, we don't have wings, we don't have anything that actually lifts us.
So how do you launch a man into the skies?
You require a lot of power to produce enough thrust to get yourself off the ground.
And once airborne, how can you maneuver safely?
We honestly didn't have an idea of how we were going to do this, and it was a potential reason why this might be infeasible.
Today's flight is the culmination of 15 months' development. But to achieve the impossible and fly like a bird, the team have had to turn to the pioneers of the past. For centuries, eccentric aviators have dreamt of taking to the skies, building hair-raising contraptions. In the 1950s, there was a new wave of construction. Inspired by science fiction, the goal was to pare down the kit and fly like a superhero. But before all of this, the first successful personal flight took its inspiration from nature.
Yes! Woohoo!
5-times world champion hang glider Karina Schweigershausen is soaring high above the Bavarian Alps.
You see the beauty of these cliffs. It's amazing.
She's only able to fly like this because of one inspiring 19th century visionary. Engineer Otto Lilienthal was the very first birdman. In the 1870s, he began designing a range of winged machines based on his studies of the mechanics of bird flight. 2 decades later, he had constructed the first known hang glider.
Look at this. This is Otto Lilienthal with his glider. You see, it's a very simple construction, just made from some fabric and some steel wire and willow wood.
But engineered with an understanding of wing aerodynamics, in 1891, Lilienthal's glider changed aeronautical history, successfully taking to the air.
He could launch it just by running off a hill and then get airborne by playing with the wing and the angle of attack of his design, and it worked. Up to today, not only our hang gliders, but even the big passenger planes use just the very concept that he started with his wing, and it's a miracle, isn't it? The holy grail of aviation history.
Like jet suit inventor Richard Browning, Lilienthal was convinced that testing his ideas was key. Throughout the 1890s, the ambitious aviator completed over 2,000 test flights on a series of gliders.
He didn't just talk about it, he didn't just draw designs, he built them and he tried them and he proved that it's possible.
Over 5 years, Lilienthal increased his flight distance from 25 to 250 meters. He became known as the Flying Man.
In my thoughts, I often take Otto Lilienthal up to our flying adventure. I'm sure he would love it. He would love to soar with the birds, just like we do. We all owe him and adore him because he made our free flying possible. He planted the seed for the whole history of aviation.
Hidden in a secret location in the British countryside, an unconventional team of engineers are bringing Otto Lilienthal's passion for personal flight into the 21st century. Richard Browning's pioneering flight suit may not have wings, but like Lilienthal's gliders, this engineering step into the unknown relies on vast amounts of trial and error.
So our development approach is one of actually having a portfolio of different attributes to the flight equipment that we try and progress all at the same time. Some of them end up unearthing interesting opportunity, interesting revelations that we never imagined. Other ones that we thought would be easy just hit a brick wall and we'll pause.
Richard first strapped a jet engine to his arm in 2016. Then tried to take flight with one on each arm. Then two, before attaching three.
So after really learning from safe failure, so in other words, learning from trying things and often falling over and realizing those things didn't work, that methodology allowed us to learn really quite quickly.
Months of modifications with state-of-the-art equipment eventually pay off.
Can you get Dave on the fire extinguisher, please?
Small, tantalizing flights show early signs that Richard Browning's fantastical dream could become reality.
It started to dawn on us that actually this is only the beginning. I think we can take this an awful lot further.
But to push on the jet suit's development and reach higher altitudes, he would need someone with his head in the clouds. Aeronautical engineer and world-class wingsuit base jumper Angelo Grubasic knows a thing or two about pushing the limits of human flight.
I've always been fascinated with skydiving, eventually getting into wingsuit flight, you know, essentially trying to experience exactly what birds achieve on a daily basis.
He's tasked with refining Richard's efforts. But going from wingsuits to jet suits poses many problematic questions.
Where do we mount the jet engines? Do we mount them on the arms? Do we mount them on the back? Do we mount them on the upper arm? Do we mount them on the lower leg? Do we go on the thigh? There's been no textbook about how to approach this particular aspect of human flight.
Angelo and Richard's combined engineering expertise allows finessing and testing to step up.
Okay, Angelo, let's roll.
Hundreds of man-hours increases their altitude. Now they can fly as high as they dare. Despite some bone-crunching finales, the team have made an engineering breakthrough.
What we've done is settled on the best solution. 2 engines on each forearm and 1 larger engine on the rear. There have been several leaps forward. One of those was the angle at which we position each of the engines relative to the forearm. So actually splaying them out slightly gave a lot more stability. Moving the engines to the rear rather than the lower legs also was a huge leap forward as well. To be integrated into one of these machines is absolutely phenomenal. I like to participate in a lot of extreme sports, and this is the most extreme sport there is.
In a matter of months, the team have come a long way. But for today's Showcase Farnborough display to be a success, they must overcome a huge problem.
How do you produce enough thrust to get a human being off the ground?
Constantly defying gravity brings many challenges.
Coming up with something that was safe and controllable and in a small package, that was a major challenge.
To fly like a superhero is an impossible dream. But now, groundbreaking engineers are making science fiction reality.
For me, the freedom of flight is about not being in an aircraft, it's being the aircraft.
I mean, it sounds ludicrous, but nearly every major breakthrough in human technology has always sounded ludicrous.
At Farnborough Air Show in England, one of the most prestigious events on the international aeronautical calendar, Richard Browning and his team have been handpicked to demonstrate their visionary innovation.
I never imagined I'd be here at Farnborough in front of huge crowds flying a 1,000 horsepower jet engine suit. It's quite a privilege.
As the world of aviation watches,
Alex, this one sounds a little funny. It's a new one.
inventor Richard Browning gears up for one of the biggest flights of his life. The jet suit's nerve center is a heads-up display providing in-flight fuel and engine status. Its range is 1,400 meters, equivalent to the length of 28 Olympic swimming pools. A 50 km/h top speed makes it the world's fastest body-controlled jet suit. But propelling a combined weight of 120 kilograms this fast requires an immense amount of force. At a secure location in southern England, lead aeronautical engineer and test pilot Angelo Grubasic is charged with solving the propulsion problem.
You essentially need to produce a lot of thrust. There are 2 major problems to solve. One is, how do you produce enough thrust to get a human being off the ground? And then, how do you do that in a fuel-efficient way?
For inspiration, the team looked to the engineers of the past. Gliding allowed man to soar into the skies, but relied heavily on nature. So engineers created their own propulsion.
Ooh.
In 1955, man stood above an almighty propeller on a rotor craft. But the blades proved unpredictable. A safer alternative was just round the corner. Mechanical engineer Dan Dickrell is in Niagara, upstate New York.
This facility is the Bell Aerospace Company airplane factory. It's a really impressive piece of history in terms of airplane manufacturing.
He's gained exclusive access to the site of the greatest advancement in personal flight.
It's a cool experience to be here right now.
In the 1950s, Bell Aerospace were attempting to develop a flight suit for the US military, an innovation for the soldiers of the future.
Bell challenged its engineers. How do you make a person fly?
Aeronautical engineer Wendell Moore believed rocket propulsion was the solution. In the late 50s, he developed an incredible piece of military kit. The first controllable rocket pack.
So this is it. It's the Bell rocket belt. It's pretty cool to be up close and personal to this very basic yet historic thing. This is not a model, this actually flew. Check this thing out. It's got a polystyrene and fiberglass harness. That's where the pilot goes. We see these controls. There's throttle, there's directional thrusters, the aluminum foil sort of hoses that come down. This is actually the rocket nozzles themselves. We swing around the back, we can see there's these 3 storage tanks. There's nitrogen in there and hydrogen peroxide in the 2 outer tanks.
Compressed nitrogen gas in the central chamber pushes hydrogen peroxide out of 2 surrounding tanks, bringing it into contact with a silver catalyst. This causes the hydrogen peroxide to instantly decompose into water and oxygen, sparking a huge reaction.
That hydrogen peroxide reaction is really energetic, creates a lot of heat. So that water gets turned into steam, expands to 5,000 times its volume, and exits these nozzles at over 1,000 meters per second.
This almighty force was powerful enough to lift man from Earth. Extraordinary energy created by chemistry.
So what I have here is effectively a small car that will be rocket propelled. All right, so let's draw in some hydrogen peroxide. I'm gonna add this to these silver spheres. This makes a lot of heat. We can see the reaction is happening. Oh wow, that's not a lot of hydrogen peroxide and not a lot of silver. And it is propelling the car down the table. You can see the hot gases coming out, and even though it's going slowly, it's the same premise that's used in Wendell Moore's rocket belt. We can harness the power of a chemical reaction and make all sorts of mechanical motion happen. Science.
Just like the jet suit's team of engineers, Wendell Moore used the most astonishing science of his day to launch man into the air.
Okay, I've got to get in this thing. How often am I going to be able to try on a Bell rocket belt? So squeezing into this, it's kind of a tight fit. Being in this thing, it's hard to imagine. It's hard to imagine how someone would actually fly.
But in 1961, the Bell rocket belt did just that. Propelling its pilot around 10 meters high, it reached a controlled 55 kilometers per hour. But despite impressive aerial displays, Wendell Moore's space-age invention had one major limitation.
Bell rocket belt was not successful in the end because its thrust to weight ratio was just not good enough. You only had about 20 seconds of flight time in this version, and that was not practical on the battlefield. But Wendell Moore had proven that personal flight was possible. It's just that the propulsion system is what needed some tweaking.
Inventor Richard Browning and his team of engineers owe a huge debt to the early rocket men, who unknowingly ruled out the inefficient chemical power of hydrogen peroxide as a propulsion solution. Another option was the traditional rocket, burning 100% solid rocket fuel in an explosive reaction. This generates enormous thrust, but is fuel inefficient and dangerous when it comes to personal flight.
If you look at solid rocket motors, you're talking about a very difficult to control technology. Once you light that solid rocket booster, it's going and you're not stopping it.
Rocket propulsion wasn't the answer, but another technology powered by kerosene stood out. The microjet engine.
It didn't take us very long to really settle on jet engines as a very likely good solution. It's a very small, lightweight form of thrust relative to how much it produces. The power involved is enough to take that mass supersonic. And the fuel in kerosene is actually extremely energy dense and yet at the same time not very volatile and not really that prone to explosion. It's actually pretty safe as fuels go.
What's expelled from the back of a jet engine is mainly air. In this case, ejected at 2,700 kilometers per hour. The superpowered process starts at the engine's front. Air flows in through an inlet. It's compressed, combined with kerosene fuel, and ignited, which produces a hot airflow or gas. Forced through a nozzle, it rotates a turbine, which helps ingest more air, generating immense thrust. The team have spent months developing customized jet engines or gas turbines at their secret test facility.
So this is a solution. This represents the ultimate in gas turbine technology. It spins at about 117,000 RPM, so we're looking at nearly 2,000 revolutions every second. The gas is coming out the back at over 1,700 miles per hour, at about 700 degrees Celsius. This is, in terms of brute power, the highest power density that you can get out of any particular kind of engine. To put the power of these engines into perspective, when we've got all of our engines integrated on the suit, we're producing nearly 1,000 horsepower. And if you can imagine, it's like having two Ferraris at full power acting on the human body. That's the amount of power we've got going through us. And that's all being produced by these very lightweight gas turbines, each weighing no more than 1.85 kilos.
Okay, right. Looking good?
Design engineer Sam Rogers is conducting an idle test on these small, yet remarkably powerful engineering marvels.
It's going to spool to about 30,000 RPM, and then it's going to sit at that throttle. So already you can feel some of the thrust produced just below idle. But it's a very small amount compared to the amount of thrust you get on full throttle. You can really sense the amount of power that this unit has.
This ingenious, compact, lightweight solution radically increases flying time.
The microturbine allows us to have a high level of thrust for a much longer period of time. We're now into the minutes rather than seconds. It means we can have reasonable flight time whilst having a reasonable fuel efficiency at the same time.
In little more than a year, the team have gone from barely getting off the ground to 4-minute-long flights. Once airborne, they face another seemingly impossible problem: steering.
You're not using wings, elevators, rudder. We've got none of that. We honestly didn't have an idea of how we were going to do this.
And landing is even harder.
You don't want to drop out of the sky because you ran out of fuel.
Hampshire in southern England, at arguably the most prestigious aeronautical event in the world. 80,000 spectators and top aircraft specialists flock to Farnborough Air Show to witness the latest innovations. As part of the exclusive lineup, an audacious team of engineers are showcasing their awesome invention. The fastest body-controlled jet suit in the world is powered off the ground by 144 kilograms of thrust, produced by 5 innovative microjets, with the potential to one day fly 1,000 meters in the sky.
So we're going to come down here, we're going to stop about here.
Today, pioneering pilot Richard Browning prepares to take flight.
You're going to take off and go that way.
Yep, and you're going to go...
I'm going to go that way, probably turn around...
By the white lines.
I want to pass you in front of the stand, ideally.
Yeah.
There's enormous pressure to get today's complex flight right. Engineer Angelo Grubasic knows the challenges that lie ahead.
When you choreograph performance, there's going to be quite a large number of sharp turns that you're going to have to execute. And that demands a certain amount of control and maneuverability.
But just how do you control and steer over 1,000 horsepower strapped to your body?
You're not using wings, elevators, rudder. We've got none of that. We honestly didn't have an idea of how we were going to do this.
A solution to their seemingly impossible problem lies with the innovators of the past. But the group of engineers would have to reach for the stars. The Space Rocket Center in Huntsville, Alabama. The home of America's first space program.
Sorry, I keep drifting away from you.
Where aspiring astronauts get a taste of what it's like to maneuver at zero gravity.
I'm gonna slow down here for a minute.
But one man knows how it feels for real.
When you're outside and the only thing between you and the rest of the universe is a little bitty thin sheet of Lexan that's comprising your helmet, the colors that come through, the detail that comes through, it just boggles your mind.
Veteran astronaut General Bob Stewart is one of a privileged few. He's spent almost 300 hours in space. Stewart was the first active-duty Army pilot to ever make a spaceflight.
When you're there, it's a complete sense of freedom. You can have lunch on the ceiling, you can lift huge weights, you can get on the sidewall and jump through the middle of the cabin and try to grab peanut M&Ms as you go.
However, working in space can also be a dangerous business.
This is Mission Control Houston. The hatch is now open.
Astronauts often had to conduct repairs outside the safe confines of the shuttle.
Mark, we got about 60 to go, 60 centimeters.
And were tethered to prevent them from floating away, at the cost of maneuverability.
The primary problem with being tethered in space is that restriction. I want to go out here to fix something, and my tether is 3 feet too short, and I'm sitting here so close and yet so far.
Your safety tether is going to pass your left knee. I'm trying to get on the other side. We'll go with it. We'll just keep an eye on it.
You get to thinking, what if I could figure some way to do without that tether? So that I'm no longer constrained.
Yeah, that's it. And you can head toward the airlock.
In 1984, NASA engineer Charles E. Whitsett came up with a solution that would free up the astronauts and allow them to make untethered flights outside the craft. An invention that could help out the jet suit team. Known as the Manned Maneuvering Unit, or MMU.
With this machine, we could fly freely, and it is just the most delightful flying machine that I've ever encountered. It is the easiest thing I've ever operated. I told the people on the ground that I could thread a needle with this thing.
It allowed Bob Stewart and his fellow astronauts to make the first ever untethered spacewalks.
Good boy. Thank you for bringing me home.
The MMU gave astronauts complete control in this most unforgiving of environments.
If I want to roll the vehicle, I roll it with this axis right here, just with those fingertip type motions. If I want to pitch it, it's a rotation like this. So by combinations of these movements, I can make the machine do anything I want to as far as the attitude that I'm in. If I want to go somewhere, I do that with my left hand, the translational hand controller. And it is a push in the direction you want to go type of control. This would back me up, this go forward, this slide me to the right, slide me to the left, and push me up or down.
This mind-blowing maneuverability was down to precision thrust control. 3 thrusters located on each of the suit's 8 corners were orientated at different angles, producing intricate and effortless steering. 12 kilos of nitrogen provided propulsion for a 6-hour flight.
I felt very relaxed in this thing because I had been working my butt off in the payload bay. And when I got time to fly this, I just slid back in here, and it was like sitting in an easy chair. I'm gonna go out 100 yards from the shuttle now, so there we go.
After 3 space shuttle missions, NASA retired the MMU.
It makes me sad to see that NASA made the decision to discontinue it. And about 6 of us guys went to the bar and had a beer and cried about it, because it's a lovely flying machine.
Though successful, ultimately untethered flights in space were deemed too risky. But the MMU will forever remain an icon of spaceflight.
When you reach far and you try to grasp things so far beyond your capability and you make it work, that is a great, great feeling.
Back on planet Earth, Richard Browning and his team are also directing thrust to maneuver their jet suit. But unlike the historic MMU, it's the pilot who moves or vectors the engine's nozzles to give precise control.
To our surprise, what started to bear fruit was not the idea of individually controlling the throttles of each engine. It was not vectoring them with adjustable nozzles, it was actually vectoring them using your arms. The geometry of those arm mounts is very, very specific, and suddenly it unlocked a huge amount of stability and control. It feels entirely planted.
The solution is to have 3 main points of thrust to form a stable tripod of air. All 5 engine nozzles are fixed. Those on the arms can be adjusted by simple movements, creating a stable 3-point vector control system unique to the jet suit.
So this is the solution that we've found works best, creating that 3 thrust vector control. So 1, 2, and then 3 on the rear. And between those 3, you balance all of those thrust vectors. For example, to lose altitude, you flare out the engines, which are operating at 100% all the time, and they will reduce your vertical thrust vector and you will descend. As you bring the arms in, you're increasing your vertical thrust vector and you'll start to gain altitude. And then very small changes in those thrust vectors are enough to actually initiate roll or sliding side to side. And it's all to do with weight shifting and thrust vector control.
Maneuvering these cutting-edge jets is finessed for hours above the safety of water. Shadowing a nimble jet ski proves the perfect way to fine-tune this skillful control. But with any flight, the stakes are high. It's critical pilot Richard knows that all 5 engines are operating smoothly. Engineer Alex Wilson is facing this communication challenge.
Richard doesn't have a cockpit to sit in, he doesn't have his panels of screens in front of him, so he needs a way to be able to monitor this in real time as he's flying. When you're flying along at 30 miles an hour, 10 feet above the ground, it's quite important that you're able to monitor the amount of fuel that's left in your tank. It's quite a critical thing. You don't want to drop out of the sky because you run out of fuel.
Alex and the team's solution wouldn't look out of place in a sci-fi movie. The jet suit employs the latest engine control unit engineering. State-of-the-art electrical systems monitor and control each engine to optimize efficiency. An ultra-lightweight carbon helmet and visor with built-in display is wirelessly linked to the suit, constantly updating the pilot with engine and fuel data.
So each one of the engines that we have on the jet suit requires its own little control system to read the engine data and then report that back to a central hub. The control board is the brains of the whole system. That monitors all of the 5 engines' data so that you can package this into the most important vital systems information to send up to the heads-up display so Richard can monitor his temperature, his RPM, most importantly his fuel systems, so he knows how much fuel he's got left.
So, head-up display.
Oh, so this is a new one where we've taken...
Alex is continuously developing the electrical systems.
Do you want to try it on?
Yeah, let's do it.
He's currently trialling improvements to the heads-up display.
So how does it feel now?
Oh, it feels perfectly normal. It's really nice, yeah.
Mind-blowing technology first used by fighter pilots. All vital information is projected in front of the pilot's eyes.
This solution is brilliant because it's focused right at infinity, so I can stare right ahead, I can look wherever I'm flying, and then still be able to see all of my engine systems in real time without having to focus, and it just overlays it over my normal vision. Without this heads-up display, this whole venture will be so much more dangerous. It's like flying a plane without a cockpit.
But to stay at the cutting edge of new technology, the whole suit must also be developed to the max.
When working on something as advanced and futuristic as a jet suit, we need a manufacturing process that can live up to that.
And will the team's showcase flight rise to its impossible challenge?
It's happening. He's about to take off.
Farnborough in southern England. Where innovative engineers
Okay, I'm good.
are showcasing their phenomenal jet suit at one of the world's greatest air shows.
It's pretty special every time I fly this anywhere, really, even in testing, but to do it in Farnborough, the home of British aviation, and in front of a big crowd, and on a runway where so many other amazing aircraft are flying, it's exciting and exhilarating and certainly focuses the mind.
It has taken hundreds of hours of testing to get to this stage. Throughout this 15-month process, evolving the suit has been vital. Countless design alterations have created massive challenges for design engineer Sam Rogers.
Bringing the flight suit to life really wouldn't be possible without a very reactive manufacture process. Some of the main challenges are to be able to test and iterate very, very quickly, and keeping ahead of anyone else who may be developing a similar technology is very beneficial.
In this fast-moving market, global competition is fierce. A futuristic jet board, high-speed formation-flying jet wings, and a rotary-powered jetpack are all vying to be a major player in personal flight. If the jet suits team are to keep ahead of the game, they need a super-fast build technique.
When working on something as advanced and futuristic as a jet suit, we need a manufacturing process that can live up to that.
Fortunately, one of history's engineers can provide the solution. In 1983, American Chuck Hull came up with stereolithography, an extraordinary layering process which focused a beam of ultraviolet light onto liquid to form solid structures.
The value to that is that you can see your design errors, you can get feedback, you can change it quickly and have another one.
Hull's innovation would evolve into what is known as 3D printing, a game-changing invention that is now allowing the jet suit's engineers to build the impossible. The starting point is selective laser sintering, or SLS, an efficient process used to prototype new parts in plastic.
We use the nylon SLS process to test fit some of the arm mount, and then if we're happy with the fit, then we'll move over and build this in metal, because the metal process is significantly more expensive than building something in polymer.
Printing in metal involves trailblazing engineering. A computer-generated design is brought to life by layering powdered titanium in the metal sintering machine.
So in here we have the receptacle where the powder is stored. At the bottom of this there's a plunger type mechanism that will rise, and this will cause the powder level to rise at the top here. This mechanism, called the recoater arm, will then drag a layer of powder over the build plate. This very thin layer will then be scanned with the laser.
Today, the lab is prototyping some new intricate designs. The laser operates at 1,668 degrees Celsius, instantly melting each minute layer of titanium.
The layer thickness depends on the material. This can range from 20 microns to 40 microns. 20 microns is 20 thousandths of a millimeter thick.
Once melted, another fine layer of titanium powder is dragged across to repeat the process. This precision layering builds a complex design in one single structure. Detailing on this micro-turbine housing would simply not be possible with conventional manufacturing.
And that's how it would look like once it's completed. This would comprise of about 5,000 layers and probably take about 2 days to build this part.
3D printing's speed and seemingly impossible detailing are making the unlikely dream of the gravity-defying jet suit a reality.
It really makes a huge difference on top of what we would be able to do with standard manufacture methods. It really removes the limits of what we can create and design for the flight suit.
At Farnborough Air Show, Richard Browning makes final preparations for a flight that must impress the aeronautical community. If getting off the ground safely wasn't tough enough, today's routine is choreographed with the team truck.
Of course, when you've got a truck coming towards you at quite a speed, you've got to have good control and make sure that at no time do you ever even consider moving in front of that truck.
It's happening. He's about to take off.
Finally, the jet suit is launched. Propelled by 5 miniature jet engines.
Come on, Richard. Come on, Richard.
Encased in cutting-edge materials. Richard's seemingly impossible flight rockets to 30 miles per hour. It's a daredevil climax. Completed with pinpoint accuracy.
It's great. I mean, it's an amazing venue to be flying around in. Everything ran very well, felt smooth. Yeah, it's really good actually. Very pleased indeed.
The personal jet suit's successful Farnborough debut will ensure they land firmly on the world stage.
As an aerospace engineer, it's phenomenal. It's the ultimate project. To be building these systems, wearing them and flying them, it's just a dream come true.
For this ambitious aeronautical team, the sky's the limit when it comes to impossible engineering.
Being able to actually touch and hold this machinery is something that I've always really wanted to do from when I was very young, and to be able to actually get up close to it, feel it, see how it works is a real privilege.
This system is unlike any of the human flight systems we've seen before. Controlling all of the thrust, having it directly onto your arms is just so much more exciting and so much more inspiring.
By building on the work of the pioneers of the past, overcoming huge challenges, and pushing technology to even greater heights, the engineers are succeeding in making the impossible possible.
Some of the technology could well create an entirely new direction for human mobility. I think the suit opens up a doorway to an entirely new world, and I'd like to think our journey has been all about that.
The Black Rock Desert. A barren wilderness in Nevada. The setting for one of the most awesome challenges known to mankind. The land speed record. Engineering at its most extreme. Which in 1997 took the British thrust SSC to a mind-blowing 763 miles per hour. A record that has remained untouched for over 2 decades. But now in Perth, Australia, an ambitious team are building a car that they believe will one day rewrite history. The Aussie Invader.
Well, here she is, soon to be the world's fastest car, Aussie Invader 5R. 55 feet in length, 6.5 tonne in weight. Very, very powerful, 200,000 horsepower, 62,000 pound of thrust.
This extraordinary machine is the culmination of a life's work for inventor and driver Roscoe McGlashan.
I believe this car is the most innovative land speed car ever conceived. This baby here is a solution to go very, very fast. This car, it's perfect. It's got everything in the right place. It's a revelation.
To create a car as fast as a speeding bullet requires NASA-like technology. Keith and Jenny Lovett are part of the team striving to create this engineering first.
This is absolutely one of the most exciting high-speed car projects in the world.
The dynamics of the car do share with the aerospace, the rocket engine, the wheel speeds. Even the paint finish on the car has to be able to cope with super high speeds.
Aussie Invader's futuristic bodywork has just been completed. The team is now working on its propulsion system. But this will not only have to break the land speed record. Incredibly, Roscoe has another audacious goal in his sights.
The next big thing that we want to achieve in the land speed record is what we say is the holy grail of auto racing, 1,000 mile an hour. To achieve 1,000 mile an hour in a car or 1.4 Mach is impossible. And that's why we're doing it. We love it.
This is a one-off, absolute unique car. Aussie Invader 5R is the ultimate of cars.
Aussie Invader is constructed around a unique steel tube. 2 huge fuel tanks feed a liquid propellant rocket engine. Powerful enough to break the sound barrier in 15 seconds. Before state-of-the-art air brakes and a parachute system bring this horizontal rocket to a halt at the end of its 24-kilometre run.
That's good. Yep.
12 volt.
But as this pioneering team look to enter the unknown, the challenges are immense. How is it possible to create fighter jet performance on 4 wheels?
To make a car go as fast as we want to go, which is 1.4 Mach, you need a heap of power.
How do you ensure Aussie Invader won't break up?
It has to be made to withstand some extreme forces. 1,000 miles an hour with wheels turning at 10,000 RPM, strange things happen.
And how can it safely slow down from supersonic speeds?
It has been a challenge to develop a braking system for the car because there is no book that tells us what we need to do.
The fact that few have even attempted to travel this fast on land poses perhaps the biggest problem.
I think that 3 times as many people have gone to the moon that have
gone 600 mile an hour in a car. So it's a pretty amazing thing to achieve.
So how do you even know what shape to build?
A lot of people say to me, how do you make a car go 1,000 mile an hour? What's the difference between a 1,000 mile an hour car and my road car? Obviously the aerodynamics, making the car stay on the ground. It's just got to have the right load on the ground at all times. The aerodynamics are possibly the major thing to get right.
Can the pioneers of the past shed any light on what it takes to construct the fastest car on the planet? The land speed record was initially the reserve of the French aristocracy. In 1898, Count Gaston de Chazelou-Lobar set the first record, reaching 39 miles an hour in a production car. But Belgian car manufacturer Camille Janatzi soon stole his crown, propelling his car to 41 miles an hour. In an ego-fueled rivalry of one-upmanship, the Count finally broke the 50 miles an hour barrier, and it seemed the battle was won. But Janatzi was determined not to be beaten. Like Aussie Invaders' team, he had to come up with something completely different. Andrew Steele has come to the Cité de l'Automobile in Mulhouse, France, to get up to speed with Janatzi's inspired solution. A totally new breed of car.
This is a full-size replica of that incredible vehicle. It's called La Jamais Content, which means the never satisfied. And it was a revolution in automotive engineering.
This was the first ever car specifically designed to break the land speed record. Few people have had the chance to drive it, but today, the museum are making an exception.
Wow, bit tight in here. This is like a 25-point turn.
Its aerodynamic body is made from a lightweight material called partinium.
Right, let's take this thing for a spin.
Never before used in car manufacturing.
Here we go.
In April 1899, Janatzi used the car to set a new land speed record of just under 66 miles an hour.
It's not doing 0 to 60 very fast.
Making him the first person ever to drive a car over 100 kilometers per hour.
Just coming out of the corner, and I'm going to stick pedal to the metal now. This just isn't like any car I've ever driven before. I mean, you can hear it sounds like, what, a dinosaur? It hasn't got a steering wheel, it's got this incredible sort of tiller system. It's also the days before the internal combustion engine became popular. And that means that it's driven by two 25 kilowatt electric motors, giving me a whopping 68 horsepower under my right foot.
Built purely for straight-line speed, the Jamais Content's bullet-like design broke the mold of automobile aerodynamics. The kind of forward thinking that Aussie Invader will have to adopt.
Just leaning into the corner now, I feel so unsteady going around this not even particularly tight turn. This is absolutely terrifying. It's incredible to think this was once the fastest car in the world.
Janatzi's record would stand for almost 3 years, proving that by specially engineering a car, it was possible to go faster than ever before.
What a machine.
In Perth, a team of engineers are constructing a one-of-a-kind car that they hope could reach an earth-shattering 1,000 miles an hour. Like Camille Janatzi, inventor and driver Roscoe McGlashan's life is focused on one thing.
The land speed record has been something that I've wanted to achieve all my life. Quit school at 12 years of age to set the record, and here I am many, many years later still chasing that elusive goal.
Roscoe's quest for speed began with homemade go-karts. As an adult, he upped the ante.
Race things like rocket-powered motorcycles, jet dragsters, a lot of stuff.
In the 1990s, Roscoe would earn himself legendary status as he targeted the Australian land speed record.
Initially, what we wanted to do is I want to claim the title of fastest Aussie on earth, and it took us some time to do that.
Yeah, how you doing, mate? Good, mate. That looked really spectacular, looked really beautiful. It is good, mate.
It wasn't until '94 that we actually went set the record at 500 mile an hour.
The average speed for the 2 runs was 801.3 kilometres per hour.
We can bring the champagne. So we've got it, guys! We've got it!
One of our earlier passes, we ran 638 mile an hour on a one-way pass. So that was actually faster than the world record at the time.
But an official land speed record requires 2 timed runs. Unfortunately for Roscoe, a freak storm made this impossible.
Within an hour, exactly an hour, we got to be coming back the opposite direction. We couldn't back it up, and but we went pretty good. We did pretty good.
Now, 2 decades later, he believes his new groundbreaking design has the potential to become the fastest car on the planet. As with Gennazi's bullet-like innovation, the starting point for Roscoe is creating the right shape.
We thought if you want to go to the moon, you start off with a cylindrical object, have a point at the top of it, rocket motor in the bum, pressure vessels all the way through, and you sit under the point at the top. Well, obviously, in a car, we want to be sitting on the centre of gravity. So the centre of gravity is about here, and we're sitting right behind it, so we know what the car's doing. So obviously, if the front of the car's moving, if the back's moving, we want to know about it.
Aussie Invader's nose is angled down to avoid lift. To house the rocket's huge fuel tanks, a unique 12-metre-long steel tube forms the car's colossal front cylinder.
What we call the mainframe is a pipe, if you like. It's been dimpled to get the right boundary layer airflow over it. And if you measure this car from the front axle to the back axle, it's possibly 2 mil difference. So it's stiff, it's strong. Yeah, I think it's a perfect solution.
To reach 1,000 miles an hour, Aussie Invader's cylindrical body would have to cope with some extreme forces. Approaching the sound barrier, or supersonic travel, would disrupt the airflow, causing a potentially devastating problem underneath the car.
Just before it's approaching supersonic, there's a shockwave that forms on the car. The problem with the car is it cannot dissipate that shockwave downwards because it hits the ground. And if you've got a flat belly underneath the car, it goes bang, 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 all the way down.
These trapped shockwaves could throw Aussie Invader dangerously off course. So the team came up with an ingenious solution.
We made a V underbelly on the car. The further back it goes, the sharper it gets. So as that shockwave moves backwards, the shockwave can dissipate off the side of the car and go outwards instead of hitting the ground and bouncing back on the car.
But if this engineering marvel is to ever travel nearly 250 miles an hour faster than any car before it, the team will need to overcome another seemingly impossible problem.
We believe we need 62,000 pound of thrust to get us where we want to go.
So how do you create more power than any land-based vehicle has ever produced?
3, 2, 1.
The steering wheel still removes, pull the steering wheel off to climb in and access the car through here.
In Perth, Australia, a trailblazing team are developing one of the world's most ambitious engineering projects. Aussie Invader, a supercar they believe will one day achieve the impossible. To drive at 1,000 miles an hour.
Aussie Invader 5 is the pinnacle of all land speed cars. I just don't think there will be another car built with this capable power that this one has got.
Aussie Invader is aiming to travel 5 times faster than a crossbow bolt, 4 times quicker than an Indy 500 racing car, and double the cruising speed of an Airbus A330. But to achieve this, it will have to generate more thrust than any other car, creating a massive problem for inventor and driver Roscoe McGlashan.
I'm in the speed business, so we want to go really, really fast. We believe we need 62,000 pounds of thrust to get us where we want to go, to the 1,000 mile an hour, and there's not many ways to get that.
Land speed records have been set with a wide range of power sources. In the 60s, the American Goldenrod was fitted with 4 combustion engines. But its piston-powered record was 600 miles an hour short of Aussie Invader's 1,000 mile an hour target. Engineering greats like Spirit of America were fitted with turbojets. But these are not the ideal solution for Roscoe.
The things that scare us with jets is where the engines will suck in, like a big vacuum cleaner, a stone or a rock or a wrench, into the engine, kill the engine, you lose the record. So we're done with jets.
So what could propel Aussie Invader to its impossible dream? Can the pioneers of the past help out? In Dudenhofen, Bavaria, a test track is playing host to an engineering masterpiece that could help Aussie Invader. Behind the wheel is vintage car specialist Uwe Mertin.
This car was originally driven in 1928, and to drive it here now, 90 years later, it's just amazing to have this chance to be here and to drive this car.
This is a replica of the legendary Opel Rack 2. Its extraordinary wings give a clue that this was no ordinary car.
The original car had a kind of a different, you can't really say engine, it was just powered in a different way.
With the sole goal of out-and-out speed, the carmaker's director of testing, Fritz von Opel, replaced the combustion engine with something quite incredible.
What you see here are 24 rockets. And imagine there was no engine inside, no transmission, just the rockets. And the driver had the steering wheel, that was it. And then bringing up this car to a speed of 238 kilometers per hour, it's just amazing.
Von Opel used solid fuel rockets. Once lit, their powered propellant burnt outwards, releasing high-speed gases, propelling the car with 6 tons of thrust.
Whenever they were ignited, it was like a firework. The driver ignited with a pedal, always 4 rockets at a time. So 24 rockets, he had to do it 6 times, and then the car went faster and faster and faster up to the end speed.
To appreciate the rocket's phenomenal performance, Uwe has a scaled-down demonstration.
I'm going to do a fun little challenge with a remote-controlled car. I'm driving up the straight here, maybe 4 seconds to get there. So maybe could we take some inspiration of Fritz from Opel, so to make it faster? So in my hands I have 3 solid fuel rockets. Put the rockets on here. Let's see.
And when 3 fuses are slotted into place, today's pocket rocket is ready for launch.
So I'm gonna light the fuse now. Oh! My God! Similar to what Fritz did with the rocket car.
In 1928, at a Berlin racing circuit, these awesome rockets would launch the Rack 2 into the record books, with its 148 mph top speed.
There were tons of smoke. There was a big, like a firewall coming towards you. It was really the first time that people had seen something like this. Fritz von Opel is for sure a pioneer and a German hero.
Aussie Invader is following in the footsteps of the remarkable RAK-2. But its single rocket is being built to drive it almost 7 times faster than its land speed predecessor.
So this is a solution to all our power problems. It's a bipropellant rocket motor and it's designed to produce around 200,000 horsepower. That's more power than the entire grid of a Formula One race.
This bipropellant rocket is engineered around 2 liquids: an oxidizer, white fuming nitric acid, and turpentine, which acts as its fuel. Nitrogen gas stored in 3 giant tanks pressurizes the 2 liquids at 600 psi. When the throttle's opened, the liquids are released into the combustion chamber.
As soon as they see each other, it's instant oomph. There's a massive controlled explosion inside there. They get squeezed through here, which puts a massive amount of pressure through the throat and then out through the nozzle. The same scenario as when you're watering the garden, you put your finger over there, you restrict the flow at the end of the hose, and obviously the pressure goes up massively.
Testing of the rocket's cutting-edge fuel is currently underway at a facility in America's Mojave Desert. When white fuming nitric acid and turpentine are injected together, the result is spectacular.
5, 4, 3, 2, 1.
On land, it's hoped this extraordinary thrust will allow Aussie Invader to cover 440 meters in just 1 second.
When I hit the gas pedal on this car, the 2 mixers go into this into the combustion chamber. The 2 mixers puts out a plume 300 foot out behind it, makes full power in 3 milliseconds, and the temperature inside there gets close to 2,000 degrees Fahrenheit within seconds. That's space technology. Rocket's the only way to go.
Rocket engineering could one day fire Aussie Invader into the land speed history books. But its fuel-guzzling performance creates a major problem.
With the propellant usage on the car's getting 2.5 tonne lighter in 21 seconds.
This could make the Aussie Invader dangerously unstable.
What can actually happen is the car can just lose its directional control and spin like a top either way sideways.
Australian inventor and racing legend Roscoe McGlashan is on a mission impossible. To create the world's fastest ever car.
I'm no rocket scientist, but I've got rocket scientists that help me. I've got engineers, I've got welders, I've got fabricators, I've got the best you can possibly get. There's a steering cone that mounts off a rack on the inside here, which gives us 5 degrees. Yeah, just give her a turn, Trust Pete, would you mate? So it puts it actually through a 5-degree plane either way, and that's basically all the steering we have.
To date, Aussie Invader has been 15 years in the making. Its designers hope it will one day reach a mind-blowing 1,000 miles an hour in just 20 seconds, making it an engineering first.
There's not a lot of people that can tell you how to do this or work it. There's no land speed book, there's no rocket car building project kit. You have to start from scratch and work forward.
The 9.5-ton Aussie Invader will be rocket-propelled, capable of creating more power than 2 Hornet fighter aircraft. Its engine is 1,300 times more powerful than a family car. engineered to travel 1 mile in an astonishing 4 seconds.
I think the greatest thing about what I'm doing is no one else is doing it. It's too hard. It's the most impossible thing you could attempt to do.
Aussie Invader's projected speeds are staggering. But driving this fast would create an immense problem for a crucial part of the car.
So at 1,000 mile an hour, our wheels have got to turn at 10,000 RPM, so we cannot run tyres, it'll just explode. So one of the biggest obstacles we've had to overcome is having wheels that would turn at that RPM.
The space-age solution is a set of super strong aluminium wheels. Engineer Mal Austin is overseeing their development.
Essentially, it's one of a kind, so you're not going into production with these type of wheels. You've got 900 diameter piece of solid aluminium turning at 10,000 plus RPM. The forces at play are astronomical, hence being the toughest grade of aluminium you could possibly find. Any slight stone or anything it may hit upon the track, it puts an immense lot of force onto the wheel. It's got to be able to withstand a lot of load.
These unique wheels are built to withstand an unbelievable 50,000 G.
Being machined out of one solid piece is the only way to go. It provides with the right tensile strengths. This weighs approximately 140 kilos. There's no ring to that, so it's pretty solid.
But if Aussie Invader is ever to achieve a safe supersonic run, it will have to overcome another huge challenge. A problem that nearly killed the pioneering record holder Donald Campbell in the legendary Bluebird.
Donald Campbell, back in about 1960, ran his Bluebird racer and he found that the back of the car came around past the front, so the car couldn't run like an arrow.
It's thought that instability at high speed caused the catastrophic crash. Unwanted lift had nearly cost Campbell his life. Now Roscoe McGlashan faces the same danger. To keep Aussie Invader safely on the ground, its centre of gravity must be perfectly positioned. Achieving this with a rocket-powered car is far from easy.
With the propellant usage on the car is getting 2.5 tonne lighter in 21 seconds. What happens, the centre of gravity on the car is moving rearwards, and what can actually happen is the car can just lose its directional control and spin like a top either way sideways.
Can an innovation from the past offer a solution to avoid disaster? Formula One pit engineer Michelle Creighton is used to life in the fast lane. Today, she's at the British Motor Museum, discovering a racing icon that could provide an answer for Aussie Invader.
Wow, this is the beautiful, stunning Jaguar D-Type. This is the car that raced at Le Mans in 1954. It's engineering at its finest. It's so smooth, it's made out of one piece of lightweight aluminium. It's all handcrafted and it's absolutely beautifully finished. Absolutely stunning.
Despite its slick lines. To beat the world's best at the grueling 24-hour Le Mans, the Jaguar team needed all-round super-fast performance. But high-speed sections like the 6-kilometre Mulsanne Straight were posing a problem. When travelling over 170 miles an hour, the D-Type's lightweight body was becoming unstable.
Jaguar knew to compete, their engineers have to come up with something game-changing and iconic to stand a chance.
Aerodynamicist Malcolm Sayer had a simple solution to help the D-Type reach the checkered flag. An invention that could also assist Aussie Invader.
Designed specifically for high speed. Going down the Mulsanne Straight, you're doing 170 miles an hour. Don't want any crosswinds to knock this car. The tail fin is just like a fin on a plane. It's trying to help the stability of the car. Wow, the feeling of this car is unbelievable. The sheer speed of the carpet is just phenomenal.
This brilliant innovation made the D-Type rock solid on the high-speed straights. Its impact is down to the relationship between the car's centre of gravity and centre of pressure, the point where lift acts. With no wing, the two are roughly centred, creating instability. By increasing the car's surface area with a fin, the centre of pressure moves further back, controlling lift and creating stability. Science that can also be seen through a speeding arrow.
This area here where we've got the feathers is just like the tail fin on the D-Type. As the D-Type's going down the Mulsanne Strait at 170 miles an hour, it doesn't want to be doing this. Same as the Archer's arrow, the tail fins just help it fly in a nice straight line.
So will world-class archer Kathleen McCarthy's shot from 25 metres prove fruitful?
When you're ready, Kathleen. Oh, nailed it! That's a wicked shot.
But when the crucial surface area of the feathers is removed...
Wow!
It's a different story.
Without the feathers or the fletchings on the back, the arrow has completely gone off course. Just proves how vital those feathers are and the fin on the back of the D-Type.
In the 50s, the Jaguar's game-changing fin helped to increase the D-Type's top speed from 172 to 192 miles an hour on the straight, powering it to an historic hat-trick of Le Mans wins.
This kind of success back in its day and age was unheard of. It's absolutely dominated Le Mans. The fin is a great achievement.
Aussie Invaders' team are building on the D-Type's ingenious concept. After months of prototype testing,
So that man there is responsible for that. Look at that. Woohoo!
the final result is a state-of-the-art tail fin that they hope will one day keep Aussie Invader stable at 5 times the speed of the historic Jaguar.
So here she is. Here's our vertical stabiliser mounted on top. Without this component on their car, this car could not run straight. As soon as it like the rocket, the back end would want to pass the front and turn around themselves.
As with the Jaguar, the tail fin's surface area keeps the crucial centre of pressure to the supercar's rear. At around 400 miles an hour, aerodynamic loads will want to spin Aussie Invader round, but the tail fin's intricate profile creates an opposing force to this immense sideways pressure. Whilst the new innovation on the top of the tail fin will counteract lift.
The horizontal stabiliser works basically opposite to an aeroplane wing. When it's going through the air, it's creating a downforce of pushing it back down. And the beauty of this one is that if we have too much downforce on the back of the car, we can actually change the pitch on that horizontal stabiliser to the desired loading on the back axle.
But at super high speeds, Aussie Invader's front end will also face a major aerodynamic challenge. With 2.5 tons of propellant burnt in just over 20 seconds, the front's balance will continually change, making it potentially unstable.
So to compensate for that, with the front getting lighter, what we've got is the canards on the front that are computer controlled.
The canards are small pitchable wings, positioned behind the wheels.
As the weight comes off the front wheels, we get more wing put into it, the wing cranks down and pulls the nose down a bit harder. The canards at the front help us with that. It's a fine balancing act to get the car to run perfectly straight, and all I can say about that is this is the slickest land speed car that's ever been built.
Cutting-edge aerodynamics and a 200,000 horsepower rocket may in the future bring the land speed record into Aussie Invaders' reach. But then the team will face their final impossible problem.
With the development of the car, the slowing of the car has to be a critical area of it.
With phenomenal forces at play, if this massive car isn't slowed down precisely, the run could end in disaster.
Everything's got to happen in the right sequence, going down from 1,000 mile an hour back to zero. It's a major job.
Aussie Invader is being built to rewrite history. The 763 miles an hour world land speed record is in its sights. And not only that, this team of engineers, headed up by creator and driver Roscoe McClashen, believe it will one day raise the bar to an unimaginable level as they target 1,000 miles an hour.
Roscoe is probably a pioneer in the idea that a car can go 1,000 miles an hour. He's dedicated to the point where he's willing to put his life on the line for it.
If I can be the fastest man on earth, and it might only be for a day, I think I'd be a happy camper, and I might be prepared to hang the helmet up and go fishing. Come on, mate. Come on.
Over a decade of development has gone into Aussie Invader. When construction is complete, Roscoe will be more than ready for his attempt at the impossible.
Lucky I'm slim. I should take that steering wheel off. It makes it a bit tight, put that on. Yep. Once I've climbed in the seating position here, the canopy's down, I'm secure, I've got my air breathing mask on, I've got my comms, I'm ready to go. Both throttle pedals go down and instant ignition, and I'm away.
62,000 pounds of thrust could launch this supercar to the magical 1,000 miles an hour mark in just over 20 seconds. But then the engineers will face their final problem.
With the development of the car, the slowing of the car has to be a critical area of it. From 1,000 mile an hour, to keep it in a straight line once the engine power goes off will be a challenge.
The distance is critical. He needs to allow himself plenty of distance or time to stop.
If they break this 9.5-ton machine too suddenly, Roscoe will experience up to minus 16 G and could simply black out.
The difference between stopping a fast, light car as opposed to a fast, heavy car is a world of difference.
Conventional brakes are out of the question.
Everything's got to happen in the right sequence, going down from 1,000 mile an hour back to zero. It's a major job.
Surprisingly, it's an aeronautical innovation from the past that could provide a solution.
One last check of the controls. And we had full throttle.
In Idaho, former US Navy flight surgeon Dr. Rich Sugden is taking control of the FJ-4B Fury.
Here's coming up.
A 1950s trailblazer that holds a key to solving Aussie Invaders' problem. Astonishingly, this 60-year-old jet can virtually reach Mach 1. But for the engineers who built it, slowing it from these speeds was perhaps their biggest challenge.
Jet aircraft need to be slowed down for two reasons. First, to land, and then secondly, they have to be slowed down in certain phases of maneuvering. The FJ-4B was designed to be a nuclear bomber, and part of that design required that it make a very steep dive from fairly high altitude.
Okay, we'll be taking it all the way to the end.
This high-speed maneuver hurtled the jet towards the ground at around 460 miles an hour. Controlling this dive posed a major problem.
You need some way to slow down quickly in an airplane that's going fast and is very slick, has very little drag. And you have to have something that can withstand high stresses.
This seemingly impossible problem taxed the greatest aeronautical minds. But Edgar Schmud and his team of design engineers at North American Aviation equipped the FJ-4B with a brilliant solution. They are known as air or speed brakes.
So these are the outboard speed brakes that come out when the gear is down. And in addition, there are ventral speed brakes that come out on both sides that stick down. They put the speed brakes on the fuselage versus being on the wings because they wanted pure drag. They didn't want anything that was going to affect the airfoil of the wing.
When diving on a target, all 4 air brakes were engaged, greatly increasing drag resistance. This allowed the plane to slow from around 500 to 200 miles an hour in a matter of seconds.
So the speed brakes are electrically controlled, which means it's just a switch that opens a valve, and then 3,000 pounds of hydraulic pressure is used to force these speed brakes out against the air. And doing 600 miles an hour through the air, there's a lot of force against these things, so there'd be no way to do this whole thing mechanically.
These robust engineering marvels help transform high-speed jet performance and still play a crucial role in the world of aviation. Aussie Invaders team have been inspired by this solution from the skies to develop their own trailblazing technology that they believe will one day bring the fastest car in the world safely to a halt.
So at 1,000 mile an hour, I pull both throttles back and the car will go from 1,000 mile an hour back to around 850 mile an hour.
At this critical point, Roscoe will gradually engage his unique air brake system. The first phase of slowing Aussie Invader down.
Then I start inching the air brake, so I hit the button. 1, 2, 3, 4, 5, 6, 7, 8, and then fully open. It's a little bit like putting your hand out the side window on a car and feeling your hand get blown back. It's the same sort of drag, except 10,000 times that.
Electrical engineer Barry Fitzsimmons was involved in constructing these engineering marvels.
The air brakes are extremely important. They allow us to get away with about a 27-kilometre long track. Without them, yes, it would slow down, but it would take an awful lot longer.
A series of small holes stop air easily sliding over the air brake by firing the airflow in different directions, increasing braking efficiency by 30%.
The air doors themselves are extremely robust because they're going to be deployed into an airstream at very high speed. If one of these air brakes opened without the other, it would slew the front around dramatically. So they have to both open in sequence, and that's achieved by having a single hydraulic ram connected to the 2 hinges. They either both work or they both don't work, which is great. So that took about a year to design. Getting these made was a beautiful piece of engineering.
Keith and Jenny Lovett are responsible for Aussie Invader's second phase of braking, the parachutes.
So we would initially expect to drop the main high-speed chute out at around 800 mile an hour. It'll probably work all the way down to 600 mile an hour. You'll see that the top is vented, where it's allowing the air to go through. This is very similar to what you see in a space shuttle landing or a space capsule coming down.
The chute not only acts as a brake, its length also helps maintain a straight course.
If the car started at high speed to get sideways, pull the chute out, and this will suddenly give it greater stability because it effectively makes the car from its 40-odd feet now to over 120 feet because the parachute will be well back there. It's like a sea anchor. It'll help pull things into line.
3, 2, 1, fire.
Drogue guns have been developed to launch the chutes. Deployment takes just a quarter of a second. Following the high-speed chute, a second low-speed parachute is triggered at around 400 miles an hour, further decelerating Aussie Invader. With the end of its 24-kilometre run in sight, the final system, a set of rear-mounted disc brakes, can then be engaged.
If you can get the car down to 250 mile an hour before he uses the wheel brakes, that would be best, simply because it's wear and tear on the car. We expect to run it a number of times to get up to a speed record.
Through ambitious design and innovative engineering, Aussie Invader may one day change land speed history.
The whole car makes me very, very proud because it is like a 10 years accumulation of seeing it all come together. You stand back and think, God, did we really do that?
Overcoming extreme challenges to take on the seemingly impossible.
It's been my lifetime putting it all together, and I can't wait to sit my bum in that car and light the wick.
By building on the work of the pioneers of the past, adapting and breaking the mould themselves.
This car's come of age. I believe it's going to set the world on fire. It's going to be the first car in the world history to go 1,000 mile an hour.
The engineers are succeeding in making the impossible possible. Sailing is the passion of millions around the globe. But when it comes to harnessing the wind, there's often a choice to be made. Size versus speed. The two seldom go hand in hand. But now, a brand new boat is rewriting the rule book. Black Pearl, the world's largest sailing yacht.
Welcome to the Black Pearl, 106 metres, 7.2 metres of draft, 14.5 metres of beam, sails at 22 knots. We expect it to do 30 knots. Without a doubt, that is unique.
Never before has a yacht of this scale been built to sail so fast.
Good morning, welcome on board the Sailing Yacht Black Pearl.
Today, this $200 million feat of engineering is setting out on crucial sea trials in Tarragona, Spain. Captain Chris Gartner heads up its crew.
The Black Pearl is completely different from almost every other sailing ship ever built. She's just designed to sail.
Drop the ground lines.
It is really a modern day miracle.
The world's largest sailing yacht, Black Pearl is the length of 10 London buses. Its tri-deck design is equipped with a helideck, state-of-the-art tender garage, and can accommodate 38 guests and crew. All powered through the sea by an innovative 3-masted rig, equipped with nearly 3,000 square metres of sail.
It is a sailing machine. It is so on the cutting edge. Yeah, it's exciting.
However, creating such a vast vessel poses many impossible engineering challenges.
Looking good.
How do you ensure the largest hull of its kind will glide through the water?
Moving close.
221.
And stand up to the unpredictable ocean?
Every time we leave the dock, it feels great.
But perhaps the biggest problem is making this 100-metre-long, near 3,000-ton super yacht a world-class racer.
And we're only 10 degrees starboard, and it turns that quick. We want to sail fast. Sure, there's a lot of boats out there that are real flyers, but they're a quarter of the size.
To get up to speed, this marine giant requires a staggering 2,900 square metres of sail area. But how do you rig and control such a vast amount of canvas? Could a marvel from the past help with this seemingly impossible problem?
Well, this is not how I usually start my days.
Naval architect Nick Bradbeer is in Greenwich, London, scaling a supersized 150-year-old speed machine.
I am climbing up a tall ship's rigging, and I've never done this before. I'm a little bit nervous, as well as excited.
That, incredibly, could provide an answer for Black Pearl's design challenge. Equipped with 47-metre-high masts, this 85-metre-long maritime masterpiece was once one of the fastest ships on the planet.
This is the Cutty Sark, one of the last surviving clipper ships. And back in 1869, when she was built, she was an astonishing piece of engineering.
This amazing vessel was the result of a nation's quest for a decent cup of tea. A thirst that started 200 years before it was built.
Tea was imported from China, from India, and it was all imported by the East India Company. They were the only people allowed to bring tea into England.
With no competition, their ships, known as East Indiamen, weren't built for speed. 1,200 tons of tea was crammed on board.
Please.
A typical round trip to the Far East took a leisurely 2 years. But in 1834, the East India Company's tea monopoly was ended. Other ships would now be vying for the tea market's rich pickings. Their slow, bulky boats now had a major problem.
Wealthy Londoners were willing to pay a premium for that first batch of tea back from every harvest. So an enterprising group of merchants and sailors realised that they could make a lot of money, and that meant they would need a new kind of ship, something that was much faster than anything that had gone before.
Scottish shipping entrepreneur John Jock Willis and engineer Hercules Linton came up with a trailblazing solution. The Cutty Sark was a legendary British tea clipper, so named because of her ability to clip off the miles at breakneck speed.
The Cutty Sark was a very fast ship. She did speeds up to 17 knots, which is about twice as fast as the ships that came before her, and actually is about the same speed as a lot of merchant ships do today.
Her secret? A towering square-rigged three-mast design. A sailing powerhouse that could inspire the Black Pearl's team.
One of the things that really sets a clipper apart, because she has to go fast, is the sheer quantity of sail that she's designed to carry. Looking up, we've got 11 miles of rigging, 32 sails, nearly 3,000 square metres of canvas, which is just an unbelievable amount. I can't even quite fit them all in my field of vision. She's just a machine for carrying as much canvas as possible, because it's all about speed. The more sail she carries, the faster she can go.
The Cutty Sark and this new class of ship slashed 20 weeks off a round trip to China. Its awesome rig making the most of whatever wind was available.
If you're in light winds, you want to cram on as much sail as you can. If you're in a heavy wind, then there's only so much sail you dare pack on. But the clipper captains were driven by speed, so even in high winds, they keep packing it on to keep that speed up.
The Cutty Sark spent the 1870s speeding tea across the world's oceans. By the 1880s, she was working the Australian wool trade routes, holding her own against a new breed of ship.
Even in the age of steam, she was still far outstripping the speed of those steamships over that long run. She's a piece of history, and she's an incredible piece of engineering.
Like the Cutty Sark, the Black Pearl is built for speed. In 2016, its super sleek hull is delivered. But this engineering marvel only comes to life when its epic rig is installed.
Keep going, 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 keep going. That's it, we're down. Get the box in.
Inspired by the historic Clipper, a trio of masts resemble the Cutty Sark's iconic design, but their 66-metre height would tower above it. Engineering on this scale produces something special. The world's largest sailing yacht. Chris Gartner captains this extraordinary vessel that's shaped by the past.
Based on all the principles of the Clipper ship, we've incorporated everything that worked for them using modern day technology and materials, and now we've built a flyer.
Black Pearl's standout engineering is its game-changing square-rigged mast system.
This is the dyno rig of the Black Pearl. It's a carbon fiber structure that stands about 66 meters from the water up to the masthead. There's so much engineering in this whole structure, it's mind-blowing.
Each of the 3 masts is flanked by a series of rib-like structures known as yard arms. These subdivide the rig into 15 low-loaded sections, allowing the engineers to unfurl 2,900 square meters of sail. Today, a sail test is about to get underway. First, a manual inspection must be carried out on one of Black Pearl's massive masts.
Going up there, I leave that for the young guys. In case they fall, we're not really losing as much as if I were to fall off the rig.
The vertigo-inducing job falls to rigmaster Declan Clamp.
It's basically getting hoisted up by a winch.
And stop.
He's on truss number 6, and he will begin his inspection from up there.
View's great. Always a good view from 60 meters up.
We take a lot of safeguards in order to prevent any mishaps.
Everything's okay up here. Cool. And you get a real scale for the boat up here. You realise how big it all is.
Now the checks are complete, Chris can automatically bring this engineering marvel to life.
And I'm going to set the sail. Right now, the 4 outhaul winches are pulling on the 4 corners of the sail and dragging the sail out. It's fast to set. Days of old, the poor sailors on those boats would be working their you-know-whats off, climbing up the rigs, pulling them up towards themselves while they're balanced on little tiny foot ropes, and to do all of their sails probably take them hours.
Today, Black Pearl's sails can be set in less than 7 minutes. But even that's not the most impressive quality of this rig. It can also revolve.
We simply rotate the rigs, the entire mast rotates, and that in turn trims or eases for tuning the sails. It just facilitates something that's much easier to do, much safer to do on a big ship.
The innovative engineering that makes this possible is concealed below deck.
Yeah, Declan, can you please rotate the foremast 180?
Now.
Yacht manager Derek Munro is putting it through its paces.
So we're now in the foremast technical space, and in here we have the foremast tube that comes down. There are 4 of these mast rotation units which turn the mast around as and when we need it. And in the middle, as the mast rotates, we need to manage the cables so that they don't get tangled up. And that's what all this is up here, the cable management system.
This phenomenal technology rotates 32 tons of carbon fibre mast. Its immense capacity for canvas propels this 3,000-ton super yacht to a jaw-dropping 20 knots.
It's revolutionary as far as ease, safety, and efficiency. When we have a full set of sails up, you can actually see the masts moving. It's like a living animal. You can have a maximum of about 3 to 4 meters flex at the masthead from 0. These rigs are living and breathing. They're just moving all over the place. The Dyna rig is one of the most incredible advances in sailing.
But to engineer a purebred racing yacht, the team face more problems. Lurking below the surface lies a huge challenge.
We want to ensure that everything underneath the hull is as streamlined as possible, because it's all about winning the race.
For Black Pearl, only perfection will do.
If you've got any forms of resistance underneath there, then that will slow you down.
Black Pearl is the largest sailing yacht in the world. A brand new engineering colossus, currently taking marine engineering into uncharted territory. At 106 meters long and weighing in at almost 3,000 tons, this mammoth ship is equipped with 2 diesel engines. But its crowning glory is a trio of 60-meter-high rotating rigs, capable of propelling Black Pearl to over 20 knots. It's captained by Chris Gardner.
The horn on the Black Pearl, as impressive as the rest of the boat. It's mind-boggling, you know, to be a part of such a big boat, so advanced. It is mind-boggling for sure.
Black Pearl's unique supersized design is built to race and break records.
We're planning on being at your pilot station at about 4 or 5.
Today, the team are preparing for its latest sea trial to see if she has what it takes.
Understood.
Chief Engineer Richard Tatlow must ensure her hull is in perfect shape.
When we're racing, we're under sail, and we want to ensure that everything underneath the hull is as streamlined as possible to maximise our speed, because it's all about winning the race. Hi, Alberto. How's it going? Good. So currently the guys are kitting up with their dive equipment, where they're going to go down underneath the hull and they're going to clean our propellers. They're also going to inspect the rest of the hull to make sure we haven't got any growth that can cause us drag.
On a boat of such enormous proportions, this fingertip search takes the best part of a day.
Ooh. This looks like a band, is it? A band?
It's a band.
Yeah. Can you see any gone inside? Basically what we're seeing around the starboard propeller, it looked like a rope. And what we're also looking at is the starboard propeller is heavily fouled, so that needs to be cleaned. It's a good call to get this done.
The clean-up's not an issue. But the propellers themselves create a major problem. Used in light winds and to manoeuvre around harbours, they permanently protrude beneath the hull, compromising Black Pearl's underwater streamlining when under sail.
The propellers are always underneath there. We can't retract the propellers. We can only retract our thrusters and our anchor.
The drag through the water caused by this pair of 1.2 metre wide propellers could thwart Black Pearl's racing ambitions. Could an innovation from the past offer a solution to this unfathomable problem? The surprising answer for Black Pearl can be found at a British airfield. Engineer Dan Dickrell is discovering an historic masterpiece, currently being brought back to its former glory.
Look at this. This is the C-47, one of the most iconic and legendary aircraft of the Second World War. A plane famous for dropping paratroopers over occupied France in D-Day. It's a really beautiful airplane. It's easy to imagine what it would have been like going across the channel over enemy territory with flak going off. In the event that this airplane would lose an engine, the only way to get back safely is to maximize the ability of the remaining engine to get you to the ground safely.
But in an emergency, the disabled engine's propellers could create a major problem. Sitting in the airflow, they caused drag, which burned precious fuel. The solution was down to American engineer Frank Caldwell. He devised the Hydromatic, a propeller which utilized hydraulics to change the pitch of its blades. Known as feathering, it's a process that could help out Black Pearl.
In the event of losing an engine, the pilot reaches up, pulls the feathering button, which feathers the blades of the propeller. The 3 propeller blades will rotate, taking the fat part of the blade out of the airstream, giving it the knife edge. This reduces drag greatly and effectively helps this plane get home safely.
Today, Dan is putting his faith in Caldwell's brilliant invention, with a daredevil experiment on board a modern twin-engined plane.
So currently we're about 3,500 feet and going about 115 knots, and we're going to simulate an engine failure. When I give Captain Rob the signal, he's going to reach down and cut the power to that engine right there, and we're going to see what happens. I can't believe we're going to do this. All right, let's cut it. So there's some control instability. There's some alarms going off right now. Even though the prop is turning, that engine is actually not generating any power. It's called windmilling, and the broad side of that prop is facing the oncoming air. It's creating a lot of drag. So to maintain this altitude, eventually this airplane will stall and fall out of the sky. This is not a great situation at all to be in. Now, yeah, so we got a stall warning.
Luckily, this plane is equipped with a Caldwell-inspired variable pitch propeller.
All right, the solution to this problem is we're gonna feather the engine, so go ahead and feather, please. All right, so instantly there was an effect on the plane, and while it looks scary, the prop's not turning anymore, we feathered the blades. Now the knife edge is into the wind. The airspeed is slowly increasing, so the good engine doesn't have to do as much work. We're no longer in danger of literally falling out of the sky.
Since its launch, the Hydromatic has transformed air safety. An engineering breakthrough that has helped shape the history of flight. The team at Black Pearl have been inspired by this aeronautical game changer. But their pitched propellers cut through the waves.
Copy that. All lines off. All lines off.
Captain Chris Gartner is using the props to maneuver the 106-metre super yacht into open water for today's all-important sailing trial.
Copy that. Thank you. Actually, we got a little bit of wind today. Might be good sailing.
Below deck, Chief Engineer Richard Tatlow can monitor Black Pearl's cutting-edge propeller system from its nerve centre, engine control.
As you can see under the water here, our propeller is obviously rotating, providing propulsion for the vessel. Currently we have a pitch of around about 70%. So we have, there's the shaft line and there's the blades, and we have about that much pitch on. And things are looking pretty good.
But as the Black Pearl goes through her extraordinary metamorphosis,
We would like to set sails in 10 minutes. Is everything away?
Yeah, we're all set, Chris. No problems. Just living the dream.
We are beginning to have fun. We are setting sails.
the 1.2-metre wide controlled pitch propellers go through a change of their own to complete this streamlined sailing machine. From a 70% pitched motoring position, the blades are electronically feathered to what's known as zero pitch.
I'll go stop on starboard engine.
Okay. Now you're going to see our propellers start to slow down.
Stop on port engine.
Okay, stop.
Yeah, very impressive. Thank you very much, Steve.
So now you can see the props are no longer turning. The blades are in a feathered position in their least resistant position. So now we're sailing and we're dragging them through the water and they are not slowing us down any.
The water flows so efficiently over the blades, Black Pearl's sailing speed is increased by 2 knots. However, the propeller's ingenious engineering doesn't end there. On this giant boat, which consumes the same electricity as 25 family homes, the propeller's pitch can be altered to generate power when under sail.
We can turn them into a form of a turbine. Because we can control the pitch, we can allow them to rotate, and as they rotate, they're coupled together on the main shaft line into an electric motor. We can then generate electricity. So here we go. As we can see, that was the shaft brake releasing, and then the blades are beginning to come out of this feathering position, starting to open up and act as a turbine. Very shortly, we'll be generating enough electricity to run the ship's load.
But to survive the seas, Black Pearl's engineers must overcome another huge problem, created by its enormous size.
With the hull, all the forces exerted onto the boat itself by the rigs, the sea, there is a lot of twisting and a lot of movement.
If the hull isn't phenomenally strong, there's a danger it could fail.
Not only could it be catastrophic for the boat, but it could be tragic for someone's life.
Tarragona, a Spanish port harboring a brand new feat of engineering. Black Pearl, the largest sailing yacht on the planet. 106 meters long and 15 meters wide, Black Pearl can accommodate 38 guests and crew and an assortment of advanced equipment, all propelled by 3,000 square meters of sail. Its unique square rig, electronically controlled from 3 different sailing stations. The main hub is the ship's bridge, where Captain Chris Gartner has mind-blowing technology at his disposal.
I think the sailing station is really what makes this boat special. Nothing in the world has this. In order to sail the boat, it requires one person. We can control all masts and turn the rigs all at once, or just an individual one. This page here is how we control which sails we would like to set at that particular moment. So you just simply select it, and we'll be able to deploy all the sail area in less than 7 minutes.
This automated rig is one of a kind, but its mammoth proportions create a big problem for its engineers. The huge masts and Black Pearl's sheer scale place the body of the ship under immense pressure.
As far as the Black Pearl with the hull, with its length overall, all the forces exerted onto the boat itself by the rigs, the sea, there is a lot of twisting and a lot of movement.
The engineers need a lightweight material to competitively race. But for a boat this size, if it's not exceptionally strong, the entire hull could fail.
If it does go wrong, not only could it be catastrophic for the boat, but it could be tragic for someone's life.
Can the pioneers of the past help out with this seemingly impossible problem? The solution for the Black Pearl lies in Philadelphia. Local historian Max Kaiserman is discovering a maritime game-changer born from necessity in the aftermath of the American Civil War.
The Civil War had destroyed most of what was left of the old sailing Navy, and they really hadn't rebuilt yet. The ships that were still left in the U.S. Navy in early 1880s were wooden ships. Some of them were ironclads or iron ships, very low to the water, just for use in rivers and protecting the coast.
But the dilapidated US Navy had a major problem. It now faced a new threat in the oceans, from seafaring nations such as Britain and France.
So by the middle of the 1880s, the US Navy really needed to step up to a more modern material.
It was Secretary of the Navy William Chandler who came up with the solution: a new breed of ship constructed with a revolutionary material.
So what we're standing next to is the USS Olympia. She's the oldest steel warship left in the world. The shift from wood to iron to steel was monumental. Iron was brittle, wood was incredibly costly and weak compared to steel.
Made by chemically modifying iron, steel is incredibly strong and light. Much of Olympia's hull is under an inch thick. The perfect lightweight solution for her high-speed seaborne operations.
The Olympia represents actually an entirely new type of Navy, and a hull that was able to withstand hurricanes, high seas, and armor-piercing shells from other ships.
In the depths of the hull, the malleable quality of steel comes into its own.
Oh wow, you can actually, it's cold because on the other side is the water. We're about 15 feet below the waterline here. This is steel. It's a mild nickel steel, about 3/4 inch thick. The steel here is curved into place. It can be welded. You can see where the plates are riveted together. None of that's possible with wood. It's almost impossible with iron.
Her sleek lines and super lightweight steel hull enabled Olympia to steam at 10 knots for 24,000 kilometers without refueling. And in the heat of battle, this new material offered unprecedented protection.
Where we are now is actually one of the few places that's armored. Around the 5-inch guns is about 5 inches thick. This steel armor could protect beyond anything wood or iron could do. If I were a sailor on a ship in the 1890s, I'd much prefer to be on a ship behind 5 inches or 8 inches of steel armor rather than a foot of wood that could splinter and kill me, just the wood.
By 1898, the trailblazing steel ships had transformed the US Navy from obscurity into a global military power.
We float still today because of those engineers over 120 years ago decided to use steel on new warships. I think Olympia is a marvel of engineering.
Steel has enabled Black Pearl's engineers to build the largest sailing yacht in the world. With 21st century technology at their disposal, this cutting-edge giant is longer than the USS Olympia, but at 3,000 tons, it's virtually half the historic ship's weight. Despite this, it's still remarkably strong.
As far as the material used in the Black Pearl, steel is definitely the best choice. You know, there's the safety factors, the strength factors, and it certainly resists so much, you know, from corrosion. It's not so affected by the elements of the salt water. And if you hit something in the sea, which is always a consideration, to dealing with the twisting, the bending, and the forces that will exert on the boat from the masts in big seas.
The 720-ton hull carries over 1,300 tons of outfitting weight and 300 tons of ballast. Its unique shape took 14 months to construct in a Rotterdam shipyard in the Netherlands. The flexible quality of steel, as thin as 8 millimeters, allowed engineers to form a streamlined hull built for speed. A lightweight aluminium superstructure saves vital weight, delivering the impossible. A 106-meter-long super yacht designed to break records. But perhaps the standout engineering is Black Pearl's one-of-a-kind bow.
The special thing about this is, as you can see, it doesn't look like any other bow you'll see on any other motorboat or sailing boat. The shape of the bow at the lower end makes her very efficient through the waves. Instead of riding through them, she tends to ride over them, but it's fine enough at the same time that she'll slice through whatever you get. But it just means she's much faster. And it's very effective too, because when we get 1 2 metre seas, we have a very dry foredeck, and it's because it's hitting this bow and dispersing off the boat instead of coming right up on top and making it wet. I think when everyone sees how efficient this bow is, they'd be a bit silly if someone didn't copy it.
Black Pearl's design is so advanced, its team are targeting the 30-knot barrier, a first for a sailing yacht of this size.
It excites me a lot to be a part of this, to try to break these records. It's just an amazing, amazing, amazing sailboat.
But a new, ambitious transatlantic goal throws up more challenges for the world's largest sailing yacht.
To cross the Atlantic with zero fossil fuels means that we need to manage the power on the boat very carefully.
For a boat which consumes 8,000 kilowatts of electricity a month, a totally self-sufficient voyage from Europe to America sounds impossible.
Christopher Columbus did it, but as far as I'm aware, he had no fridge freezer, no laundry, no air conditioning.
Can Black Pearl follow in the footsteps of one of history's greats? Black Pearl is changing the face of marine design. Currently undergoing racing trials, the world's largest sailing yacht is built for speed and has the 30-knot barrier in its sights.
Yeah, it's freshening nicely, huh? Very good. Great day of sailing so far. I feel like it's getting proven. It's already great, but we're proving the systems that were put onto the boat, so it's getting better and better.
But to make its mark, this audacious yacht must also have staying power at sea. Millions of dollars have been pumped into innovative technology developed to make Black Pearl self-sufficient.
So as you can imagine, on Black Pearl, water consumption can be quite high. So what we do is we try and minimize that as much as possible. So this is actually raw sewage that's being compressed through a membrane system, then a series of fine filters through a treatment plant. That water is just used for basically washing down the boat, but apparently I have been told by the manufacturers that you can drink it. And no, I haven't been brave enough to try.
Black Pearl's sustainable systems and regenerating propellers are cutting edge. But even these aren't enough to cope with the owner's latest audacious goal: a fossil fuel-free transatlantic crossing.
To cross the Atlantic with zero fossil fuels means that we need to manage the power on the boat very carefully. Christopher Columbus did it, but as far as I'm aware, he had no fridge freezer, no laundry, no air conditioning. The jacuzzi didn't work on his boat as well. Whereas on here, we have all the comforts of home, and we want to try and keep them going.
On a mega yacht with the same energy demands as a small residential street, completing a 12-day zero-carbon crossing seems an impossible challenge. But an out-of-this-world historic innovation could offer a sustainable solution for the world's biggest sailing yacht. Physicist Susie Shee is visiting Brittany in France, discovering how the answer for Black Pearl originated in the stars.
At the moment, there's about 2,000 satellites orbiting the Earth, and they're doing everything from TV to data communications. But of course, they weren't always up there. This radome is at the Plumeau-Bordeaux Telecom Centre, and this has an incredible history in the development of satellite telecommunications. It's absolutely incredible, and it's enormous.
During the 1950s, a new era of space exploration unfolded. And with it came the potential to transform global communications. Early satellite experiments successfully relayed signals to and from space. It wasn't long before the global stage was beckoning.
Engineers in the US came up with an ambitious new project. They wanted to send live TV images from the US to Europe and beyond. So this is what they came up with. This is Telstar, which is a global communications satellite. It can take live images from the US up into space and back down to Europe, transmitting them across the Earth.
But achieving this meant overcoming a massive problem. Like Black Pearl sailing across the vast oceans, to be viable, Telstar had to be totally self-sufficient in the isolated vacuum of space.
Early satellites were powered by batteries, and in orbit they'd only last a week or sometimes days before the battery would go flat. So to keep the satellites up there for longer, scientists had to come up with a new solution.
In 1954, Bell Lab engineers Calvin Fuller, Gerald Pearson and Darrell Chapin were developing silicon transistors when they made an unexpected discovery. One of their transistors began producing electricity when exposed to light. Silicon had the potential to produce the first practical form of solar power. A special quality only seen at an atomic level.
Now, what I've got set up here is two different layers of silicon, like in a solar cell. And the important thing is that each layer has a slightly different atomic structure. So these are my atoms, and around the atoms are electrons. On this side, there's actually slightly more electrons. So this side is overall more negative, so we call it N-type silicon. And the other side, there's actually a slight lack of electrons, so I'm going to take some away. So this one is overall positive and P-type silicon.
A section between the silicon layers acts as a junction, allowing electrons to migrate, creating an electric field, a process stimulated by light.
The sun shines down on the top of the solar cell, and all that light energy can liberate electrons from their atoms in the center here. So now these free electrons are moved upwards by the electric field, and if we connect with a terminal on the top and the bottom, that creates a path for these electrons to travel round and fill the holes on the other side. And it's the flow of those electrons that provides an electric current which allows us to do work, such as powering a calculator. And you can see there's actually a couple of little solar cells just on the top of the calculator here.
The infinite power of the silicon solar cell was the perfect solution for space. In 1962, the Telstar satellite was launched, equipped with this game-changing innovation.
They actually coated Telstar with 3,600 solar cells mounted on platinum and coated with sapphire to protect them from the high levels of radiation in space. And that allowed it to produce about 14 watts of power, enough for it to relay about 600 telephone calls and a live TV feed.
To complete an historic live transatlantic satellite broadcast, Telstar received signals from the United States, magnified them by 10 billion before beaming them here to France's mammoth telecom centre.
This antenna is the first place that received the signal from Telstar. They actually transmitted a TV broadcast featuring President Kennedy.
I understand that part of today's press conference is being relayed by the Telstar communications satellite, viewers across the Atlantic, and this is another indication of the extraordinary world in which we live.
The success of Telstar helped demonstrate how good solar technology was, not just up in space, but also down here on Earth.
From the vacuum of space to the vast seas, Black Pearl's engineers have been inspired to develop their own solar technology. Their ambitious goal: to sail the world's largest yacht across the Atlantic without burning any fossil fuel.
One of the solutions we've been looking at for the last few years is to put solar cells on the sails. Firstly, we need to consider the weight, we need to consider the flexibility, and we need to consider the cable connections. So that takes us to technology which is called SIGs, which is about the thickness of a piece of paper.
At just 0.5 millimetre thick, the engineers plan to bond this super lightweight cutting-edge system to Black Pearl's Dacron sails without compromising their performance.
The solar cells, that's very, very flexible. We can easily get the rotation on the sail. We'll probably end up, if we're lucky, at 50% of that with solar cells.
That's about 1,400 square metres of solar technology, mounted on Black Pearl's 15 sails. Set to deliver around 22% efficiency through a network of cabling to the ship's 384 batteries.
We should get enough power to run the vessel with all the crew on board and all systems running, which means we should get around about 160 to 170 kilowatt hours. It's enough to provide us with enough power to run the boat without the requirement for fossil fuels. When it happens, it will be an amazing piece of engineering, and it'll be phenomenal to see it, and it's just one more step that we're taking in the future to making the boat a little bit greener.
By pushing the engineering envelope, this team are opening up the world's oceans to the remarkable Black Pearl.
Nobody, to my knowledge, has attempted to do anything like this before. No, this is one of a kind.
Black Pearl is, without a doubt, the most unique and best sailing vessel of her type. Every day we go out on sea trials or sailing, it still, gets my heart going.
By building on the work of the inspirational pioneers of the past, adapting and making discoveries of their own, the engineers are succeeding in making the impossible possible.
To be part of a project that is so groundbreaking like the Black Pearl is super exciting. And I can't wait to continue on and make this one of the most famous boats ever to sail the seas.
This is Lhasa, the spiritual home of Tibetan Buddhism. This city in the clouds is one of the highest, most inaccessible on Earth. Situated on the vast Tibetan plateau, it is surrounded by not one, but 3 mighty mountain ranges.
Before the 1950s, there weren't even any roads to get to Lhasa, just meandering mountain paths that took months to get through and only in good weather. But the Chinese government came up with an audacious scheme to connect this ancient province with modern China.
This is the highest railway on the planet. Specially designed high-altitude locomotives climb to over 5,000 meters above sea level to cross the Tibetan Plateau, the highest and largest mountain plateau on Earth.
Our locomotives can pull 3,700 tons of cargo, or 20 passenger carriages. It's the most advanced technology in our country.
The engineering is extraordinary. 675 bridges and 10 tunnels to cross the frozen wilderness that's known as the roof of the world.
Whenever I see the train passing through the Tibetan Plateau, I feel extremely proud.
From Beijing and Shanghai in the east, trains run to the city of Golmud, the start of the high-altitude line. From here they begin their climb, crossing the formerly impenetrable Kunlun Mountains to reach the immense frozen Tibetan Plateau. At this altitude, the air oxygen content is half that at sea level, and temperatures can descend to -30. The railway reaches the world's highest station at the Tangula Pass, a staggering 5,068 meters above sea level, before making its way to Lhasa.
This is the Qinghai Tibet Line,
a railway which at first people thought was impossible. It's called the Heaven Road, and honestly, that's what it is.
It's the most audacious railway project ever imagined and comes with some enormous challenges.
How do you build on terrain that's frozen solid in winter and boggy marshland in the summer? How can a train be powered at altitude that's normally the preserve of aeroplanes? And how do you communicate with trains when they're in the middle of this vast wilderness? But perhaps the biggest challenge is how do you keep everyone breathing?
At this incredible altitude, oxygen is in short supply. Dr. Zhu Xinxian is in charge of the railway's medical unit.
On the Qinghai-Tibet Railway between Golmud and Lhasa, the average altitude is over 4,000 metres. It's an area of extremely low atmospheric pressure. There's only around 50% oxygen in the air here compared with the mainland.
The human body is not designed to cope with such low oxygen levels. It can lead to potentially fatal altitude sickness.
The most common symptoms of altitude sickness are headaches, vomiting and confusion. It's vital that correct oxygen levels are maintained and any deficit is dealt with immediately. In severe cases where the body's starved of oxygen, it can cause swelling of the brain or lungs, which can be fatal.
These unique trains are specially engineered to protect their passengers as they travel through this beautiful but brutal landscape. Ding Weiyan is the senior engineer.
In here is the oxygen generator, which pumps oxygen into the train carriages. These prevent oxygen shortages at high altitude and make passengers feel more comfortable. Inside, there is an altitude sensor to determine the oxygen levels outside and oxygen concentration sensors to monitor the levels in each passenger compartment. The train is made up of 16 carriages, and each of these carriages has its own oxygen generator, like this.
The passengers also have access to oxygen masks, which they can use if they're having difficulties.
Well, if you're just sitting here, then it's all right. But if I climb to the top bunk bed, then I notice that I have some shortness of breath.
As an extra precaution, the railway posts a medical team on every train.
There's a doctor and a nurse on board all the passenger trains. They carry oxygen and heart monitors, oxygen cylinders and a full medical kit. Once they're on the train, they do a patrol every 3 hours to check on passengers.
These extra measures on board ensure safe passage for the 2 million travellers who make the journey every year. But the team who built the line didn't have these luxuries.
Construction workers are at a high risk of altitude sickness and hypoxia, a severe lack of oxygen. Doing physical work means your body uses up oxygen very quickly. That made this an extremely difficult project. At first, we thought there was no way it could be completed.
They would need to turn to a machine from the past to defy nature and build across the roof of the world. Humans have never let a lack of air stop them from going to the most extreme environments. Mountaineer George Mallory lugged a 14-kilogram oxygen tank up Mount Everest. Ancient Greeks used diving bells to explore the depths. But the oxygen didn't last long, and the bell could tip over. And when railway pioneer Isambard Kingdom Brunel wanted to bridge a deep, fast-flowing estuary, he sunk giant metal caissons and pumped in compressed air to create a pressurised environment to build the foundations. But while the engineering was sound, it wasn't so great for the workers. Dr. Gary Smurden is in southwest England at the site of Brunel's masterpiece, discovering how experts in engineering and medicine came together to solve the problem.
So here we have the Royal Albert Bridge, a fantastic feat of engineering.
Most of the people who travel across the top of this bridge do not have the faintest idea about the effort and the suffering that went into building this bridge, because the feat of engineering to get that pier built down into the rock bed of the river was very new at the time, very dangerous, and they didn't really understand what they were doing. These workers were moving into a pressurised environment every day to do their digging and their engineering, and then coming back to the surface. There were 25 workers. One died, 2 became paraplegic, and all of the others became ill due to what became known as caisson disease.
With 19th century engineers wanting to build ever more impressive structures, a way to treat workers who came down with caisson's disease had to be found. In 1876, American inventor Daniel Kelly submitted a patent in Chicago for a compressed air bath, a machine that would hold the key to treating workers with caisson's disease. The body contains nitrogen gas. When the pressure increases, this gas dissolves into the blood and tissue. But when the body returns to normal pressure, it becomes a gas again. If bubbles of nitrogen gas form, they can gather in joints and tissues, causing serious problems. Kelly's machine was a forerunner of the hyperbaric chamber.
Any problems, just put your hand up, say stop, and we'll take it from there.
Lovely, see you on the surface.
Whilst the condition affecting the caisson labourers was very different from what the Chinese workers were suffering from, this amazing machine holds the key to solving both problems. An air compressor creates pressurised air which is stored in a giant tank. It's slowly pumped into the airtight hyperbaric chamber, recreating whatever pressure environment doctors need to treat their patients. This was the key to treating caisson's disease, giving doctors the ability to reduce those deadly bubbles in the blood.
So here you are, we're in the chamber now. The door is shut. My colleague Chris is at the controls, and he'll soon be pressurising me and getting me down to the equivalent of 30 metres.
And the machine itself can actually be used to demonstrate the very problem it was built to solve with a simple experiment.
So with me here in the chamber, we have an empty bottle here that's full of air, and another bottle that's full of carbonated water. We'll see what happens to them on the way down.
Stand by, blowing down the Comex.
The empty bottle contains air at normal sea level air pressure. So as the pressure in the chamber mounts, the bottle collapses.
Okay, that's you at 30 metres, Gary.
Okay. I'm sat here at 30 metres. One of the biggest changes is my voice. That extra density of the gas causes it to pass differently of my vocal cords, and I speak in a very strange manner.
The water, which was carbonated at normal air pressure, has completely lost its fizz.
And there we have a glass of carbonated water. At this pressure, the gas molecules are dissolved in the liquid, but the gas is still in there.
This water represents blood in the body.
So when we go back to the surface, you will see bubbles will start to appear. Now that's exactly what was happening to these caisson workers. When bubbles will start to appear in your blood and in your tissues, as a human, you're in trouble.
It was discovered that the key to avoid bubbles forming was a slow ascent, giving the body time to equalise. This machine allowed doctors to simulate a slower controlled ascent, saving the lives of caisson workers.
Oh, because here we are, back on surface again. It's nice to be out. Now we know how to come back up safely. As you saw, it's a slow ascent. In the old days, take the top off the valve and reduce the pressure, and people bubbled inside them, and that's what caused all the problems. But now I've been down, I've come back up to surface, absolutely no problems at all. Feel the same as I did when I went down.
In China, the team building the railway realised that this 150-year-old chamber could be put to a different use.
On the 29th of June 2001, the build began of the highest section of the railway. This was the base hospital for the construction team. We provided a lot of medical personnel and support. This hyperbaric chamber was used frequently.
The construction team went through 120,000 bottles of oxygen each year, but even that wasn't enough.
There were many critically ill patients during the construction of the railway. Our medical staff were first on the scene to give initial treatment and, if necessary, to transfer the patient to the hyperbaric chamber. These chambers were vital. They saved patients' lives.
When you're working at 4,000 meters altitude, getting back down to sea level isn't easy. But by placing workers suffering from altitude sickness into hyperbaric chambers, they could effectively simulate a move straight back down to sea level, meaning treatment could start immediately.
Engineers installed 25 chambers at strategic locations along the 1,100-kilometre line.
During the construction of the railway, the success rate for saving lives from acute altitude sickness was 100%. There were no fatalities. This line is a milestone in the history of railways. I'm proud of it, and I'm very proud of being part of the medical team during its construction.
This machine helped keep the 100,000 workers who spent 5 years building this inspirational railway safe. With construction crews hard at work to link Lhasa to the rest of China, the biggest engineering challenge still lay ahead.
If the ground melts below your foundations, you're in real trouble. A railway line is at risk of collapse, derailing any trains trying to use it.
Mount Everest, the highest mountain in the world. The Himalayas make up the southern edge of the world's largest mountain plateau. Stretching 1,000 kilometers north, the Tibetan Plateau is the breathtaking setting for the highest railway on Earth.
In the past, people thought a railway to Lhasa could never be done. It's one of the most remote cities in the world. But this didn't stop the Chinese engineers, and the engineering challenges they faced were immense.
The city of Golmud sits at 2,800 meters in the foothills of the Kunlun Mountains. To link it to Lhasa, engineers needed to find a way to run rails across the permafrost, the permanently frozen ground of the 2.5 million square kilometer plateau beyond. Wang Xingchang is Professor of Engineering at the Railways Research Institute that was tasked with achieving the impossible. He regularly makes the 8-hour round trip from Golmud to the heart of the plateau to monitor the ground conditions.
The area we're in now is typical of the Tibetan Plateau. It's called no man's land. 2 or 3 meters beneath us is permafrost, which is permanently frozen ground. It's incredibly cold here. The annual average temperature is between -2 and -7 degrees. It's these low temperatures that create the permafrost on the Tibetan Plateau.
Building anything in this environment isn't easy.
Frozen ground can actually provide the perfect foundation for building on, but with one important condition: it must remain frozen. If the ground melts below your foundations, you're in real trouble. A railway line is at risk of collapse, derailing any trains trying to use it.
So how do you keep hundreds of kilometers of ground frozen solid enough to build on? For inspiration, the engineers turned to another frozen territory 7,000 kilometers away. Known as the last frontier, Alaska is America's northernmost state. Straddling the Arctic Circle, it covers a staggering 1.7 million square kilometers. When the largest oil field in North America was discovered in Prudhoe Bay, a 1,300-kilometer pipeline down to the southern port of Valdez was required to export the oil. The problem, just like in Tibet, was that they needed to build on endless expanses of permafrost. Local civil engineer Doug Goering is aware just how hard this can be.
So this is the type of vegetation that's typical of permafrost terrain in interior Alaska. If you take a
stick and you push it down into the moss layer, you find that all of a sudden you hit something hard and it just won't go any further. What I've hit is the top of the frozen layer of ground. And so that frozen layer is roughly this far below the surface of the moss. Trying to build any kind of engineering structure on this type of permafrost results in major challenges. If you try to build a warm structure like a house or a building, you can imagine that the heat from that building is going to work its way into the ground. It thaws the ice in that ground out and it becomes a mushy mess. The house foundation typically fails.
And when you're trying to build a pipeline that will carry warm oil, those problems are compounded.
Normally, an oil pipeline would be buried, but anywhere where the ground is frozen, the pipe has to be physically separated from that frozen soil because, of course, it carries warm oil. That warm oil would melt the frozen ground and cause structural problems, cause the pipe to deform, buckle, and probably would have caused oil leaks.
So they built it above ground. This is the Trans-Alaska Pipeline, an $8 billion creation that carries up to 2 million barrels of oil a day across the entire state.
As you can see, it's a very large pipe, roughly 1.3 meters, 48 inches in diameter. It's full of oil. It's been full of oil since the late 1970s. The design focused on an elevated pipeline to keep the warm pipe away from that frozen ground.
But the foundations for the support columns still needed to rest on solid frozen ground. If it melted, whole sections of pipeline could collapse. Luckily, one man had an answer. In 1963, nuclear physicist George Grover developed a system to transfer heat that would be crucial for engineers trying to build on permafrost.
You can see that each of these vertical support members are capped by two finned sections. Those fins sit on top of a device known as a thermosiphon. These thermosiphons are used to ensure that the ground that the vertical support members go into remains frozen. The vertical support members rely on that frozen ground strength to hold the pipe up.
A thermosiphon is essentially an empty tube which goes through the marshy bog down to the frozen ground. At its base is a liquid refrigerant with a low boiling point. When the temperature rises in the ground, the liquid absorbs the heat, starts to boil, and then evaporates, dissipating the unwanted heat through the tube and into the atmosphere, keeping the ground around the foundations cool.
What I have here is a canister of butane, which is similar to the refrigerant that's used in the thermosiphon. And what I'm going to do here for a demonstration is get a little bit of liquid butane into this plastic bag. So you can see that I have liquid in the bag here. What happens at the base of the thermosiphon is that liquid boils. And you can see that when I add heat by putting my fingers on this bag, that I get pretty vigorous boiling of the butane. This is the same thing that's happening at the base of the thermosiphon. In this case, the butane is collecting heat from my fingers. In the case of the thermosiphons, the refrigerant collects heat from the permafrost and pulls heat out of it, dumps that heat into the atmosphere.
Over 100,000 thermosiphons help to keep the oil flowing.
This pipeline project really is an engineering marvel. It's been stable for on the order of 40 years. Really, I think it's safe to say that the engineers who designed this solved the permafrost challenge.
The permafrost challenge has not beaten the team in Tibet either. Here they've used the thermosiphons on a massive scale, stretching as far as the eye can see to cross over 500 kilometers of permafrost.
These thermosiphons are the best way to solve the problem. It's a great solution. Its main function is to decrease the temperature of the ground and prevent the permafrost from melting. This is the part that releases heat. And this is the middle section, and the working part is underground. We use 2 rows of thermosiphons on the side facing the sun and 1 row on the side which doesn't face the sun.
Over 25,000 thermosiphons have been installed. But with the heat generated from passing trains, the thermosiphons alone aren't enough to keep the ground frozen and the foundations solid. The track is also raised off the ground on a crushed rock embankment. This low-tech engineering works by letting the cold wind flow through the gaps between the rocks, dissipating any heat coming from the trains above.
By using these measures, we protect the railway by keeping the ground cooled up to 15 metres away from the track. This prevents the permafrost from melting and sinking the railway.
But for an 11.7 kilometre stretch of the permafrost zone, in the heart of the plateau, neither of these measures could help.
We're now at the Chimawa River Upland Plain Natural Reserve. This is all wetlands. The biggest feature here is the hydrothermal lakes. This is a natural occurrence of frozen soil.
Whilst in the winter this area is frozen solid, the heat from the hydrothermal lakes means it's all a boggy marshland come summer. So this is the incredible solution. At over 11 kilometres, it's the longest bridge over permafrost in the world.
Most of the frozen soil is melted here. A rock embankment wouldn't be stable, so we built a bridge. The bridge is supported by pile foundations which are inserted deeply into the ground. In this environment, a bridge is a much better solution than an embankment. The biggest difficulty for us building this kind of bridge is working in winter. During summer, the atmospheric temperature is too high. If we built during this season, we would risk causing the permafrost to melt, making it too unstable.
Working through winter at temperatures down to minus 30 degrees, engineers achieved the impossible and completed the final, most difficult part of the line to Lhasa.
Building a railway in the permafrost of the Tibetan Plateau was one of the biggest engineering challenges in the world.
With the groundbreaking line complete, engineers still had another major hurdle before any trains could use it.
Regular locomotives just wouldn't be able to cope with the lack of oxygen. They wouldn't get anywhere near Lhasa.
The Tibetan Plateau is known as the roof of the world. Crossing it is the highest railway on the planet.
The engineering that's gone into this project is mind-blowing. It was almost impossible to conceive of a railway running at this altitude. It's an extraordinary feat of human ingenuity.
To construct this £3 billion line, engineers overcame huge hurdles. But coming up with a locomotive that could handle the altitude almost scuppered their ambitions. Across most of the China railway network, electric locomotives are used, which draw their power from overhead cables. The Shanghai to Lhasa Express uses these for the first part of the 47-hour, 4,300-kilometre journey across the country. But when the train reaches Golmud, it runs into trouble.
In the isolated high-altitude plateau, extremely low winter temperatures combined with lightning storms means that electricity supply cannot be guaranteed. So they can't install the overhead cables necessary for electric trains.
Normally, railway engineers would turn to a regular diesel locomotive.
Combustion engines need fuel and oxygen to work, but at these altitudes, there's just not enough oxygen to give enough power to the engines to haul the huge trains up the steep gradients required.
Internal combustion engines draw air into the combustion chamber to mix with fuel. The piston compresses it, then the spark plug ignites it. This controlled explosion forces the piston back down the cylinder. But as oxygen levels drop, so does the force of the explosion and the power produced.
Regular locomotives just wouldn't be able to cope with the lack of oxygen. They wouldn't get anywhere near Lhasa.
To get trains to run at such high altitudes, the engineers needed to look to the skies. Mechanical engineer Dan Dickrell is exploring Pikes Peak, one of the highest points in America's Rocky Mountains. It was here, in 1918, that a landmark experiment changed engine design forever.
Driving this really muscly car up one of America's most iconic highways is quite exciting from both an engineer and an auto enthusiast perspective. The terrain is twisty. It's a wild ride for sure.
But as the road climbs, the amount of oxygen in the air falls.
I've reached the halfway point of Pikes Peak. For my body, I can sense the lack of oxygen through my lungs. My lungs are telling me there's not enough oxygen in this air. I cannot perform at peak efficiency. I can feel that lack of oxygen at this altitude, and so can the automobile. The bottom was really snappy. It's starting to get a little bit more sluggish.
At the 4,302-metre summit, the oxygen is almost 50% lower than at sea level.
All right. I can really feel it. Lightheaded, do not feel great. Now on the way up, the internal combustion engine inside my car, it could feel it too.
This problem plagued early aircraft pioneers, who found the higher they took their machines, the more their engine's power faded. And during World War I, the ability to fly high became a matter of life and death. The higher a plane could get, the smaller the chance of it being detected by the enemy. Just like the engineers in China, they had to find a way for their engines to cope with lower oxygen levels, so they could go higher than ever before. To help the US Army Air Force solve their lofty problem, they drafted in steam turbine engineer Sanford Moss.
Sanford Moss developed a revolutionary piece of machinery that would force more air into the airplane engine, essentially turbocharging it.
Moss's turbocharger was a total game changer. Instead of just being wasted, the engine's exhaust gas is used to spin a turbine, which in turn powers a compressor which draws in air, compresses it, cools it, and pushes it into the combustion chamber. This high-pressure mix, when ignited, dramatically increases the engine's power. To demonstrate the difference it makes, first we need to see how an engine performs without it.
This is going to serve as my cylinder. Inside the cylinder, we're going to put a mixture of fuel and air. Instead of gasoline, I'm going to use butane. Now what I'm going to do is I'm going to take this butane and inject it into my cylinder. And 2 metal electrodes are going to serve as a spark plug. I'm going to introduce 2 alligator clips that will provide electricity in 3, 2, 1. Cool. All right, now we're going to repeat the same demonstration, except this time I'm going to turbocharge the cylinder. To do that, still need some fuel. Now this time we're going to introduce a slightly different cork, because this one has a valve in it. That's going to allow me to pressurize the cylinder, just like a turbocharger would. We lock down, give it a few good pumps. So now I've got my pressurized cylinder. Let's repeat and see what the effect has on it. In 3, 2, 1, go! Whoa, nice! Oh, that one flew much, much higher. The turbocharged cylinder worked much better in terms of explosive release of energy, just like a turbocharged engine would.
In 1918, Moss and his team came here to carry out their first high-altitude tests. He put his new turbocharged engine on the back of a truck and attached it to a giant propeller. The output had been 230 horsepower. But with his new invention, it was boosted to 356 horsepower.
Three years afterwards, a biplane fitted with a MOS device broke the altitude record, flying higher than any other airplane had flown before. Turbochargers exist all over the place. Really impressive pieces of technology.
In China, engineers have fitted MOS's turbocharger to special locomotives to give them the power to cross the high-altitude Tibetan plateau. At Golmud Station, locomotive engineer Shen Deji is monitoring the switchover.
This train has just arrived from Beijing to the east. It's an electric locomotive, powered from the overhead cables. After the crew have disconnected all the wires, it will be pulled out so that the new locomotive can come in.
With the passengers eager to continue the next 14-hour leg of their journey to Lhasa, the train crew must move quickly.
This is our solution to the high-altitude problem. It's a tailor-made plateau diesel locomotive, especially designed for the Qinghai Tibet line. It's about to be connected to these carriages.
These turbo diesel engines provide 6,000 horsepower to pull either 20 passenger carriages or a whopping 3,700 tons of freight at speeds of up to 120 kilometers an hour.
I had the honour of driving the first train to cross the plateau to Lhasa. So whenever I see this incredible advanced locomotive coming into Golmud, I feel excited, very excited. If we'd not managed to build this turbocharged locomotive, so many people just wouldn't be able to get to Lhasa. I feel very proud of this solution.
But the engineers still face another major hurdle. The single-line design makes reliable communications essential.
With high-speed trains travelling in opposite directions in some of the most remote locations on Earth, how do you ensure you can communicate with them to keep them safe?
The highest railway in the world runs to Lhasa Station. Trains on this line are specially engineered to cross the frozen tundra of the Tibetan plateau. Undercarriages are sealed to protect against frost damage. And even the windows are specially designed to cope with sub-zero temperatures.
The windows are equipped with a special heating device. It prevents the glass from freezing and cracking as the train travels along the cold parts of the Golmud to Lhasa line.
These incredible advances make this previously impossible journey possible for passengers like Gregor and Marianne, tourists from Holland.
Yeah, it's definitely amazing. I'm reading a book right now about a woman who's traveling in Tibet, I think about 20 years ago. And it was so different. You had to do everything by foot or with a jeep. And if there were mud floods, then you couldn't go any further. It's really a totally different setting to just cruise through the mountains in a warm train.
The 1,142 kilometers of high-altitude railway between Golmud and Lhasa includes a staggering 675 bridges and 9.5 kilometers of tunnels, including the highest railway tunnel in the world, the 1,338-meter-long Fengguoshen Tunnel, drilled through a permanently frozen mountain.
Building this line really pushed the boundaries of engineering. But with a £3 billion price tag, They simply couldn't afford to build two lines side by side, one for each direction, so they had to settle for a single line. This presented engineers with a new challenge. With high-speed trains travelling in opposite directions in some of the most remote locations on Earth, how do you ensure you can communicate with them to keep them safe?
So, how could an innovation from 19th century railway pioneers help inspire the engineers in China? The early 1800s was boom time for Britain's railways. Thousands of miles of new tracks were laid. But with more trains, they needed a way to communicate. Early systems relied on flags being waved by hand.
Come on!
Or from horses galloping alongside. But with more trains travelling further and faster than ever before, these systems were totally insufficient. Something had to be done. Engineer Kate Mulcahy is at miniature Wonderland in the German city of Hamburg, the largest model railway in the world. 1,300 trains with over 10,000 carriages crisscross this huge attraction, where they have a similar problem: keeping trains safe.
Luckily, an ingenious new form of technology was about to change the way the world communicated, setting in motion a telecommunications revolution.
In 1837, William Fothergill Cooke and Charles Wheatstone struck upon a brilliant concept.
Here I have a compass, an electric wire, and a lantern battery. The breakthrough that Cooke and Wheatstone discovered was that by using these simple ingredients, you could send messages over really long distances. It works like this. If I attach one end of my electric wire to the positive terminal on the battery, and then attach the other to the negative, I create a complete circuit. This induces a magnetic field which should deflect the needle on my compass to the right. If I reverse the terminals, so I remove this one, now attach it to the negative, this one now to the positive, what you'll see is the needle now deflects to the left. By using the simple method of electromagnetic deflection, Cooke and Wheatstone had discovered the first ever form of electronic communication.
The first test took place between two London stations, Euston and Camden Town. A telegraph wire was laid in a tube alongside the track with a special device at each end.
Cooke and Wheatstone built this instrument, the 5-needle telegraph arranged on a grid of letters. Now in my version, my construction here, this bit represents the sending element, and then this bit over here represents the receiving element. These rods in the middle represent wires. Now because this telegraph, the sending one, is connected in the circuit to this telegraph, when I move this needle one way, the action is mirrored in the receiving telegraph over here. So for example, if I wanted to spell out, say, the word stop, I start with the letter S. So on my sending, I'll move this needle so it points towards S, and I'll move this needle so it points towards S. And then the person on the receiving end will look for where the points of those needles converge. I then need to move the needles so that I can get them to converge on T.
This device enabled its users to spell out words and send them down the wire.
Their feat of engineering brilliance was to send the first communication electronically on the railways.
The needle telegraph started a telecommunications revolution. Adopted by the railway network initially, it soon went round the world.
Eventually, Cooke and Wheatstone streamlined this system into just one needle that through a series of movements could create a coded message. This system of signalling lasted on the railways well into the late 1930s.
In China, they've taken this 180-year-old concept and given it a 21st century makeover. Third-generation railwayman Wang Jianmin is deputy manager of the Golmud depot.
Between Golmud and Lhasa, we use satellite positioning signals. You won't see a single trackside signal on the Golmud-Lhasa line. We use the satellite positioning signals due to the tough weather conditions and 4,000-metre high altitude. This is a great piece of technology. It's a massive leap forward.
The train control system is run from a control room at Xining Station, with global positioning satellites determining the train locations. All signalling is virtual. Instead of wayside signals used by Cook and Wheatstone's system, all information is communicated directly into the train cab, where an onboard computer terminal displays up to the second information to the driver.
The advanced technologies implemented along this line are unique in this country. They are the only reason that we can provide Tibet with the Heaven Road Railway that's been so important for their economic growth and social development.
The Golmud to Lhasa line has transformed travel across the Tibetan plateau.
Business increased quickly once the Golmud to Lhasa line opened. Just in the last year, we've dispatched over 1 million passengers. And the goods we have transported by rail have sharply reduced the number of lorries on the road. Lifestyle products, building materials and daily necessities such as oil are basically all transported by rail now.
Building a railway line across the roof of the world was never going to be easy.
When we were young, we didn't think there would ever be a railway between Golmud and Lhasa. I think it's a milestone in the history of global railway.
The unprecedented and ambitious project stands as testament to the tenacious perseverance of the human spirit.
If this special locomotive didn't exist, so many passengers wouldn't be able to get to Lhasa. So I feel very proud of this train.
Go! Whoa, nice!
By building on the work of the inspirational pioneers of the past, upscaling and breaking new ground themselves, the engineers have succeeded in making the impossible possible.
The Qinghai Tibet Railway is the greatest engineering achievement in the world.